So good afternoon everyone, welcome back to this channel and let's start the Maha Revision of Fluid Mechanics for GATE 2025. How are you all? Good evening everyone. So type in the chat box. कैसे आप सब लोग? Are you all studying well? GATE exam सिर्फ 3 महीने बाकी है, sorry 3 हफ्ते बाकी है ना, so only 3 weeks. I am good, मैं बहुत बढ़िया हूँ. आप बताइए आप सब लोग कैसे हैं? Good evening everyone. Good evening. चलिए, so you all fine? Nice. Okay, so let's directly start this Maha Revision. So पहले इस सेशन स्टार्ट होने से पहले मैं आपको कुछ चीज़ क्लियर करना चाहता हूँ. So firstly इस सेशन में मैं कोई डेरिवेशंस नहीं कर सकता हूँ, जो मैथमेटिकल डेरिवेशंस होता है वो नहीं कर सकता हूँ. ठीक है, पहला चीज़ ये है, क्योंकि ये सिर्फ महा रिविजन सेशन है एंड अगर मैंने मैथमेटिकल डेरिवेशंस कर सकता, इफ आई डू दैट देन इट विल डेफिनेटली गेट स्ट्रेच्ड. ओके, लेकिन सिर्फ 3 हफ्ते बाकी है, सो आई डोंट वांट टू वेस्ट योर टाइम एट दिस पॉइंट. ओके, दूसरा चीज ये है कि मान लो कि मैंने कुछ पॉइंट बताया था एंड उसका कॉन्सेप्चुअल एक्सप्लेनेशन चाहिए, तो डेफिनेटली प्लीज आस्क मी इन द चैट बॉक्स एट एनी पॉइंट इन दिस फुल लेक्चर. यू कैन स्टॉप मी and ask me in the chat box. ठीक है, I'll definitely respond for that. Then second point is this. Then third point, when I give you some questions, please do attempt those questions. Okay, and if you have any doubt, anyway we'll keep solving the questions. Okay, so चलिए, first before this we have started this third session which is like fluid mechanics for today, and this is the complete schedule जो आपने Apup sir or firstly this Shivam sir has also displayed to you. So we are at day 3 and today we are going to have this fluid mechanics. And कुछ बच्चे मुझे पहले बार देखते हैं, so I just want to quickly introduce myself. मैं कौन हूँ, मैं क्या कर सकता हूँ. So my name is Vinay. Okay, and obviously this is the credentials list. Okay, so I have already ranked 4 of XE and previously I was also a officer at Hindustan Petroleum Corporation Limited HPCL, and I was in BRC, Baba Atomic Research Center, Scientist C, and so I have cleared this with a rank of 38 and I do my MTech in thermal engineering, and these are the subjects that I teach generally. Okay, so engineering, mathematics, उसके साथ fluid mechanics, thermodynamics, both basic and applied thermodynamics, heat transfer. So normally जो thermal related subjects होता है वो मैं पढ़ाता हूँ. ओके, एंड आज हम करने वाला है कि फ्लूइड मैकेनिक्स डेफिनेटली. ओके, एंड फ्लूइड मैकेनिक्स के साथ जो हाइड्रोलिक मशीन्स का पार्ट होता है, टर्बो मशीन्स का, वो भी कर सकते हैं. ठीक है, सो विल see in a detailed way what are the topics we are going to cover in today and also what are the upcoming sessions as well. Okay, so if you see the list of the topics that I'm going to cover today, so पहले हम fluid and its properties discuss करेंगे, क्योंकि fluids के बारे में अगर पढ़ना है तो so we should know how fluids behave. So पहला chapter जो है वो बहुत important है, and then we'll look at pressure and its measurement. Okay, मतलब ये तीनों chapters मिलकर एक ही topic बन सकता है कि hydrostatics. Okay, so this is hydrostatics. ठीक है, so अगर आपको चाहिए तो ये तीनों चैप्टर मिल चुके हैं. So pressure and its measurement, then hydrostatic forces, buoyancy and flotation. Okay, and 5th chapter is differential analysis of fluid systems. क्योंकि मैं फ्रैंकम वाइट की बुक काफी अच्छा बुक है फ्लूइड मैकेनिक्स का, so उसके हिसाब से इंडेक्स देता हूँ. So control volume analysis and then incompressible internal viscous flows and external viscous flows. Internal viscous flows में हम Navier-Stokes equation, सारा मोमेंटम इक्वेशंस जो होते हैं वो डिस्कस कर सकते हैं, एंड उसके साथ when you derive the basic equations, हम उस बेसिक इक्वेशंस को स्पेशलाइज्ड फ्लोस, और मोर देन स्पेशलाइज्ड काफी अच्छा वर्ड है कि सिंपल फ्लोस. ओके, सो थोड़ा सा सिंपल फ्लोस को इस इक्वेशन सॉल्व कर सकते हैं. देन वी लुक एट एक्सटर्नल विस्कस फ्लोस विच इज लाइक बाउंड्री लेयर्स, ड्रैग, लिफ्ट, ऑल दिस कॉन्सेप्ट्स. देन turbulent flows उसके बाद, and dimensional analysis, and then I'll also give you some basics of potential flow. मतलब complex potential अभी नहीं पढ़ाता हूँ क्योंकि XC का काफी इंपॉर्टेंट है वो, लेकिन अभी टाइम हम बहुत ऑप्टिमाइज कर सकते हैं. So I'll teach you about the potential function, stream function, and छोटा मोटा basic flows होता है वो हम कर सकेंगे. Then compressible flows and of course inviscid compressible flows. ठीक है, so compressible flows में जो टॉपिक अनकंप्रेसिबल फ्लोस काफी इंपॉर्टेंट है क्योंकि हर एक साल एक क्वेश्चन आते हैं यहाँ से. सो विल लुक एट दिस इनविसिड कंप्रेसिबल फ्लोस, एंड लास्ट में प्रिंसिपल्स ऑफ टर्बो मशीन्स. ओके, सो जहां में ऑयलर्स इक्वेशन, इंपल्स एंड रिएक्शन प्रिंसिपल्स, जो वेलोसिटी ट्रायंगल्स होता है वो, एंड देन एप्लीकेशन ऑफ दीज थिंग्स टू टर्बाइंस लाइक पेल्टन व्हील, फ्रांसिस टर्बाइन, कैपलन टर्बाइन, ये चीज भी हम डिस्कस कर सकते हैं. ठीक है, फाइन. या आई विल रिड्यूस द स्पीड, दिस इज जस्ट क्विक इंट्रोडक्शन, सो इसलिए मैंने फास्टली बोल रहा हूं. सो देन ऑब्वियसली आज की सेशन में मैं प्रॉब्लम्स काफी कम क्वेश्चन सॉल्व कर सकता हूं क्योंकि ये बेसिकली रिवीजन सेशन है. सो कल हम महा अभ्यास भी कर सकेंगे इसके साथ. सो 9th January at 7 PM we'll start अभ्यास of fluid mechanics. Okay, so जिसमें पूरा aim ये होता है कि question solve करना, and we'll try to put as many new questions as possible, and we'll try to do very nice conceptual questions in this Maha Abhyas session. So anyhow tomorrow we have the Maha Abhyas. So आज की session में हम काफी कम questions solve करेंगे, लेकिन जो conceptual clarity होता है वो बहुत deeply we discuss करेंगे. Okay, then we also have most expected PYQs in English, क्योंकि PYQs काफी बार repeat होते हैं and last moment में PYQs solve करना काफी important है. So that's why we'll look at PYQs and we'll try to solve some tough or critical or very repeating kind of PYQs in this particular sessions. Okay, so going straight away, if you look at the weightage, normally thermal module का weightage 24 marks होता है, पूरा thermal module मिलके, उसमें से fluid mechanics का weightage 7 to 9 marks होता है, ठीक है? So 7 to 9 marks, and normally if you look at the distribution of the marks, okay, ऐसा होगा. So if you look at the big share, the lion's share of these marks, differential analysis of fluid systems, control volume analysis of fluid systems, इनकम्प्रेसिबल इंटरनल विस्कस फ्लोस, इनकम्प्रेसिबल एक्सटर्नल विस्कस फ्लोस, ये जो 4 चैप्टर्स है इस सब्जेक्ट की हार्ट जैसा है, ठीक है? सो दीज 4 चैप्टर्स होल्ड ग्रेटर देन 70% ऑफ टोटल वेटेज इन फ्लूइड मैकेनिक्स, ठीक है? सो ऑफ कोर्स these questions will also come, like if you see fluid and its properties, pressure and its measurement, hydrostatic forces, मतलब जो hydrostatics है वहां से भी questions आ सकते हैं, but not very frequently, ठीक है? So if you look at these things, the 4 chapters will be like a very big, क्योंकि काफी लोग मुझसे पूछते हैं कि सर what are the important topics and all, so these 4 chapters generally have very high frequency of questions in GATE exam, ठीक है? So these are the quick things that I thought of mentioning before starting the session. Fine, so are you all okay till this point? सेशन का ड्यूरेशन डिपेंड्स, मुझे लगता है कि 7 to 7.5 hours मे बी, ठीक है? एंड आई विल गिव यू सम लंच सम डिनर ब्रेक आफ्टर वी फिनिश कंट्रोल वॉल्यूम एनालिसिस, क्योंकि ये जो बाकी चैप्टर्स होते हैं उसमें से टर्बुलेंट फ्लोस थोड़ा सा छोटा ही चैप्टर है, देन डायमेंशनल एनालिसिस आल्सो हैज सम लिमिटेड कंटेंट, सो इसकी वजह से 6 चैप्टर्स के बाद मैं डिनर की ब्रेक दे सकता हूँ, ठीक है? फाइन, सो शैल वी ऑल स्टार्ट, आर यू ऑल रेडी? बट डेफिनेटली एक ही चीज इंपॉर्टेंट है, जो लोग एग्जाम देते हैं मैकेनिकल और एक्सी में, ओके, आफ्टर दैट इफ यू आर नॉट एबल टू परफॉर्म वेल बाय सम सोर्सेस एंड देन इफ यू सी दिस वीडियो डेफिनेटली यू विल गेट, ओके, क्योंकि मैंने 8 बार गेट निकला था, सो आई नो व्हाट क्वेश्चंस कैन कम डेफिनेटली, ओके, और व्हाट क्वेश्चंस हैज हाई फ्रीक्वेंसी ऑफ अपीयरेंस इन एग्जाम्स, सो वो सारा क्वेश्चन सारा कॉन्सेप्ट्स मैं आज डिस्कस कर सकता हूं, ठीक है? फाइन, चलो लेट्स स्टार्ट विथ the first chapter, fluid and its properties. Definitely, so fluid क्या हो सकता है? You can type quickly. मैंने सोचा कि definitions लिख के आता हूं, लेकिन आपके पास definitely you know you want to write the things, you want to say the things in the chat box. तो बताओ fluid क्या होता है? What is a fluid? अगर पता है तो हमको mechanics पता है, so then we can definitely close this lecture. Which can flow is called fluid, but बढ़िया. So let's see, anything, any substance that deforms continuously, under shear stress, and bracket में however small it is, जितना भी छोटा हो, डेफिनेटली इफ देयर इज शियर स्ट्रेस फ्लूइड स्टार्ट्स flowing, okay, so however small it is, definitely. And normally these fluids involve, wah badhiya, which has continuous deformation, substance that can bear small amount of shear force, it can't bear, yeah of course. अरे भाई सबको लगता है कि गेट रैंक आएगा इस बार, आप सबने सही डेफिनेशन दिया था, बढ़िया. तो जस्ट सी, सो दिस इज ए फ्लूइड, एंड फ्लूइड्स की लिस्ट में 2 टाइप्स की सब्सटेंसेस आते हैं, जो लिक्विड्स एंड गैसेस, करेक्ट? सो सबको पता है. सो इन केस ऑफ सॉलिड्स, इफ यू सी द डिफरेंस बिटवीन दिस सॉलिड एंड फ्लूइड, ओके, सो सॉलिड्स कैन रेसिस्ट shear stress with finite deformation, correct? So with finite deformation, but whereas fluid can't resist shear stress in static condition, can't resist shear stress in static condition, okay. सो सबको पता है, मान लो कि आपके पास एक ब्लॉक है, ठीक है, ओ ब्लॉक है लेकिन इनविजिबल है, ठीक है, सो यू हैव ए ब्लॉक, मान लो कि आपने कुछ shear force अप्लाई किया था, देन दिस विल डिफॉर्म, ओके, एंड डिपेंडिंग ऑन दिस टाउ दिस गामा इज फिक्स्ड, ओके, बट नाउ इफ यू लुक एट ए फ्लूइड, मान लो कि आपने अगर फ्लूइड का ब्लॉक लिया था, देन at time t equal to 0, if these are the particles, okay, let's fix this base for the time being, then if there is shear stress with the time, these layers keep moving, okay, so at time t equal to 0, t equal to t1, t equal to t2, if you see this gamma keeps changing, so this is gamma 1, then this is gamma 2, this is gamma 3, so यहाँ जो important चीज होता है कि rate of shear strain, correct, so this is rate of shear strain, so d gamma upon dt, but here you know tau is equal to some shear modulus times gamma, यहाँ जो gamma है वो finite है, ठीक है, so इसलिए we full class you'll use both Hindi or English language, yeah only English, we'll see as you move, okay, so in this case we have some finite deformation, इसके लिए shear stress को directly tau this gamma से relate कर सकते हैं, but in case of fluids you have a continuous shear, so that's why this is the case which is important, okay, so rate of shear strain is important in this case, and हम देख सकते हैं कि like how this d gamma by dt is related to the velocity profiles, okay, so we'll do that later. Now coming to the concept of continuum, पहले जो मैं fluid mechanics की analysis कर सकता हूँ, उससे पहले एक चीज बोलना चाहता हूँ कि हम जो fluid mechanics का analysis कर रहे हैं वो सब continuum की approximation में कर रहे हैं, ठीक है, so continuum which tells you matter is present at every point, matter is present at every point, okay, so normally in case of liquids continuum holds good in general, and in case of gases we have something called Knudsen number. Knudsen number. So what does Knudsen number tell you? Knudsen number less than 0.1. अरे वाह, इतना भी पता है. So then fantastic. So if you look at Knudsen number, then Knudsen number is lambda upon L. Lambda is nothing but the mean free path, and this LC is nothing but characteristic dimension. Characteristic dimension. अब आप मुझे एक चीज बताइए, मान लो कि मेरे पास एक कंटेनर है, ठीक है, लेकिन उसमें सिर्फ 3 पार्टिकल्स है और मे बी सम पार्टिकल्स, ठीक है. नाउ मीन फ्री पाथ टेल्स यू द एवरेज डिस्टेंस ट्रेवल्ड बाय द पार्टिकल, ओके, द एवरेज डिस्टेंस ट्रेवल्ड बाय द पार्टिकल बिफोर 2 सक्सेसिव कोलिजन्स, करेक्ट. मान लो कि इस मॉलिक्यूल went under one collision, then after hitting one molecule what is the distance traveled to hit another molecule is the mean free path. Now मान लो कि मेरे पास सिर्फ 4-5 particles है, then molecule has to travel large length or less length for collision, बताओ. मेरे पास सिर्फ 4 particles है, ठीक है, तो if a molecule hit one other molecule, then to hit another molecule the molecule should travel large distance or less distance, large distance, है ना. So मान लो कि अगर this lambda if it's large, okay, which tells you it's large, right. So if this lambda is large, which means number of molecules are small in this, okay, and there is no continuum, because अगर मान लो कि number of molecules कम है, then you don't have enough matter at every point, so that's why large lambda will signify to large Knudsen number. So large Knudsen numbers will go for rarefied gas flows actually, okay. So for continuum approximation, for continuum Knudsen number should be less than 0.1 actually here, okay. So this is the validation, yeah, sorry, 0.01 to 0.01 for continuous flows, 0.1 is for transition flow, so 0.01 is the condition for the validity of the continuum in case of gases for Knudsen number, okay. Clear to all of you? Yes, यहाँ तक सबको clear है या नहीं, बताओ जल्दी. यहाँ तक सबको clear है या नहीं? Yeah, it's done. Now let's see the Newton's law of viscosity. So क्या होता है बताओ? What is Newton's law of viscosity? फटाफट. What is Newton's law of viscosity? Quick. Mu into du by dy. Good. और कुछ? Tau is equal to mu du by dy. Mu du by dy. Still something mu du by dy. Directly proportional to weight of shear strain. Why? Wow. Others? Fantastic. Internal resistance by one layer to another. ठीक है. So let's see. If you have a plate, for example, okay, and if you have some fluid flow, then at any section you can have the velocity profile, okay, and this velocity profile can be function of, let's say in 2D, if I am talking, this is gamma u of x comma y and v of x comma y, whatever, you have the velocity profile, okay, means you have the velocity ui plus vj, okay. So Newton's law of viscosity tells you that tau is proportional to d gamma upon dt at a point, okay, because test acts at a point. So this tau is proportional to d gamma by dt, and d gamma by dt is nothing but shear strain rate, okay. So this is called shear strain rate, okay. मेरे क्लास में, ऑफलाइन क्लास में एक बंदा था 3 साल पहले, ओके, मैंने पहले एसएसआर लिखा था, उन्होंने बोला कि एसएसआर आजमौली, ओके, वो नहीं है, shear strain rate है ये, ठीक है. सो shear strain rate, और इट्स ऑल्सो कॉल्ड एज rate of shear strain. Rate of shear strain, okay, and we will see after some time, okay. लोग है, ठीक है, एसएसआर देख के बोलता है कि एसएसआर आजमौली, बाकी जो बंदा है, you know, I'll tell you so many nice things in between the chapters, ठीक है. So this is d gamma by dt, and एक चीज मैं बोलना चाहता हूं, if you want to equate this proportionality constant, you have some constant into d gamma by dt, correct. So k क्या होता है, tau divided by d gamma upon dt, okay. Now what does this k tell you, okay, this k, what does it tell you? If you want to create one unit shear strain rate, what is the effect you have to put in terms of this tau, okay. If you want to create one unit of shear strain rate, for example, if tau is high, this k is also high. If tau is low, this k is also low. So k signifies something, which is that k signifies resistance to inertia of the flow, inertia of the fluid, you can say inertia of the fluid. काफी टाइम्स लोग बोलते हैं कि दिस k is given the name dynamic viscosity, of course पता है सबको. So k is nothing but mu dynamic viscosity, ठीक है. And many times people define dynamic viscosity as the property of the fluid which resists its own flow. Need not be. If initially fluid is static and if I start moving the fluid, then that will also resist the motion, okay. Or if I am trying to stop the fluid but fluid is moving, then it's trying to resist the restness, okay. So that's why whatever the inertia maintained by the fluid, the property which tries to disturb that inertia is called this dynamic viscosity, okay. Then if you quickly look at units, sometimes 1 mark questions आते हैं GATE exam में. So if you look at mu, SI units, Pascal second, correct, or you have Newton second per meter square. ये होता है कि SI units. MKS क्या होता है पता है किसी को? Come on, टाइप कर दो चैट बॉक्स में. MKS units क्या होता है जल्दी, क्योंकि काफी बार क्वेश्चंस में MKS में भी देते हैं. So this is poise, is it? This is not exactly poise. MKS में poise नहीं है भाई. No, poise MKS का यूनिट नहीं है. No 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 no, poise is not MKS unit man. देखो एक बंदा ने लिखा कि पॉइजन, बाद में एक बंदा रेशियो भी लिखो, हो जाएगा. स्टोक्स CGS, हाँ, MKS यूनिट होता है कि kg per meter second, ठीक है, kg per meter second. And if you look conversion, 1 Pascal second is same as 1 kg per meter second. इसका मतलब यह है कि मान लो कि आपको क्वेश्चंस में डेटा kg per meter second पे दिया तो कुछ कन्वर्जन नहीं करना चाहिए, ठीक है. यू कैन डायरेक्टली यूज वॉट एवर द डेटा दे आर गिवन इन kg per meter second, okay. And you can show this very easily. It's a very simple thing. 1 Newton second per meter square, 1 Newton mass into acceleration into second by meter square. So this gives you 1 kg per meter second. So 1 and 1, no conversion. Okay, so it's the same thing. And if you look at CGS units, then you have gram per centimeter second. Okay, so gram per centimeter second. So this gives you, sorry, not gram, Newton second per meter square. So dyne second per centimeter square. Yeah, this is better. Dyne second per centimeter square, or this is also same as gram per centimeter second. This is called as poise. Okay, 1 poise is equal to 10 power minus 1 पास्कल सेकेंड. ठीक है, इसका मतलब यह है कि मान लो कि आपको क्वेश्चन में यूनिट्स पॉइज में दिया था, तो देन यू हैव टू मल्टीप्लाई 10 पावर माइनस 1 और 0.1 इन टू डू द कैलकुलेशन. ओके, दिस इज पॉइज, नॉट दिस. ठीक है, बिकॉज आई हैव सीन काफी लोग ने पॉइज लिखा था, तो पॉइज इज नॉट द एमकेएस यूनिट, इट्स अ सीजीएस यूनिट. फाइन, you can see the conversion actually. ठीक है, now let's see, you understood something that tau is proportional to is equal to mu times d gamma upon dt. Okay, now this is Newton's law, this is Newton's law, of course. Okay, now what is d gamma by dt? Okay, let's see if you are looking in the xy plane, for example. ठीक है, so if this plane, whatever you are looking is 2D xy plane, then you will see this d gamma x, if tau xy is equal to d gamma in the xy plane, then d gamma of xy by dt is nothing but half times of, sorry, it's just a tensor form, so dou u by dou y plus dou v by dou x. This is the shear strain rate. Okay, so when this is the shear strain rate, and जो लोग आप du by dy बोलते हैं, okay, so then what you get? If you have this plate, okay, and if you have fluid, so if you have this fluid, then if flow is only in the y direction, okay, means flow is only in the x direction, and this is changing with respect to y. Matlab, if you have the velocity profile only changing with y, okay, and there is no v component of velocity, okay, then if there is no v component of velocity, this term will blow up. That's how these two are equal. You write mu dou u by dou y, or since u is depending only on y, dou u by dou y is same as du by dy. That's how you get mu du by dy. Okay, अगर मान लो कि किसी ने पूछा था कि न्यूटन्स लॉ ऑफ विस्कोसिटी क्या होता है, okay, then you should not say tau is equal to mu into du by dy, क्योंकि mu into du by dy is a special case. Understood? So general case जो होता है कि tau is proportional to rate of shear strain, and rate of shear strain का expression ये होगा. Clear? Yes or no? क्योंकि मैंने देखा था कि काफी लोग ने म्यू इंटू डी यू बाई डी वाई लिखा था चार्ट बॉक्स में, तो इसलिए मैं थोड़ा सा क्लैरिफाई करना चाहता हूं. फाइन, ओके, सो आई होप इट्स क्लियर. सो देन ऑब्वियसली फॉर स्मॉल गैप्स, ओके, फॉर स्मॉल गैप्स और इन थिन गैप्स, यू कैन से फॉर स्मॉल गैप्स, I will say thin spaces. Thin spaces, u is only a function of y. So this implies tau is equal to mu into du by dy. Okay, so that's what you would get actually here. Fine. Quiet flow. Yeah, of course. Repeat once. Yeah, definitely. Normally, the expression for the rate of shear strain in the xy plane is given by du by dy plus dou v by dou x. Okay. Now, if you have a thin gap, what happens? See, I'll define. मान लो कि आपके पास thin gap है, ठीक है? Then, if there is a bulk flow of fluid in this gap, तब क्या होता है? If you look at average v component of velocity, this will be very small. Correct? क्यों? मान लो कि एक particle इस तरफ जाए, okay, but this spacing is very small, then this particle cannot have this v component of velocity for a large time. Got it? Did you all understand this? For writing this expression, you need not be a linear velocity profile. Okay, for writing this, you need not be linearly varying. Okay, u should be just a function of y, that's all. But I'll tell you why, if you have a thin gap, why velocity profile is linear. Because when you have this fluid, if this gap spacing is very small, okay, if this gap spacing c is very small, for example, okay, not tending to 0 but small, then this particle cannot travel in this y direction for a long time, correct? Whatever the flow is taking place, wo jo flow hai, this flow should effectively happen only in the x direction. Okay, so which means v will die down firstly, so you have only u, and this u also cannot change with respect to x much, because the no changes are happening in the y direction in a short span. So whatever the velocity profile you have, see, if you have a curve, okay, but a small curve, then if you try to connect this with a straight line, the difference will be very small. Yes, correct? Yes or no? सबको समझ में आया या नहीं? If you have a curve in a small gap, but if you try to match that curve with a straight line, the straight line and the curve will almost look similar. Yes? So that's why in thin gaps, we can by default take the flow is having linear variation. Got it? सबको समझ में आया या नहीं? Did you all understand why we have thin gap? The velocity profile approximation can be made linear. Yes? Correct? Because the curve and the straight line matches. That's why this expression is often used for linear velocity profiles. But in general, for writing this formula, you need not have a linear velocity profile. This is good enough, because mathematically you get the same thing. Okay, then let's move forward to some extent. So once you have this, okay, tau, we'll see why physically tau comes up and all. But before that, I just want to ask you one, okay, fine, reasons for mu. I think all of you know by this time, reasons for mu in liquids is due to molecular cohesion. Cohesion, correct? Q, molecules are spaced very closely, and within that close spacing, if one layer try to move, the other layer, because of cohesive forces, it won't allow. Okay, but in case of gases, this is due to molecular momentum transfer. Momentum transfer. And molecules के बीच में momentum क्यों transfer होता है? Because collisions happen. Okay? Collisions की वजह से molecular momentum transfer happens, and then that's the reason for the gases. Because in gases, if this molecule is trying to move in this direction, okay, then this molecule experience restriction because of collision from some other molecule. Okay, so that's why the molecular momentum transfer, or the random motion of the molecules, basically is responsible for the gases. Okay, and in liquids, this is also because of molecular cohesion. Now clearly liquids practically incompressible, because you'll see high bulk modulus. We'll look at these things. Okay, practically incompressible, then that's why mu of liquids depends mainly on temperature, because pressure cannot change the molecular spacing and the cohesion, of course. Correct? क्योंकि मान लो कि आपके पास molecules है, then if you apply pressure, the molecular change in the movement is very small, okay, or the molecular spacing change is very, very small. That won't affect the molecular cohesion, and that's why liquids do not experience much change in dynamic viscosity because of the pressure actually. Okay, but with temperature, what happens? The volumetric expansivity of the liquids are comparatively high, so that's why depending on temperature, the molecules will try to pack very loosely, and because of which cohesion falls. Okay, so as temperature increases, okay, dynamic viscosity of the liquids decreases, and you have a lot of laws to show this, like mu of liquid is proportional to A into e power minus bt, where in this case b is positive. Okay, so you have a lot of laws which tells you this, but in reality the concept is, as temperature increases, the dynamic viscosity decreases because of drop in the molecular cohesion actually. Okay, then compared to gases, so if you see in gases, mu gases, तो what happens? Any idea? मान लो कि एक गैस है आपके पास एंड आपने टेम्परेचर बढ़ा दिया, then what happens here? Yeah, I'll share this document, it's okay, no issue. But tell me what happens here? Increases. क्यों increase होता है? Because this will increase because molecular momentum increases. सबको पता है कि kinetic energy of gases is proportional to square root of absolute temperature, correct? So this is kinetic theory of gases. Kinetic theory of gases, okay? So if you have kinetic theory of gases, which tells you that if you increase this temperature, kinetic energy of the gas molecules also increase, okay? मान लो कि इस रूम है, ठीक है, एंड रूम में दो बंदा हूं, ओके, मैं और दूसरा एक बंदा है, फॉर एग्जांपल, एंड लेट्स से वी आर वॉकिंग and colliding. Impact, molecular momentum transfer will be less. But in the same room, instead of walking, if we are running, okay, randomly, then when collision happens, it will be more damage, correct? Like if two vehicles are hitting at zeros, like almost 3 kilometers per hour speed, nothing happens almost. But if they are hitting at some 130 kilometers per hour speed, damage is big, okay? So the same thing here, as you increase the temperature, kinetic energy of the gas molecules will increase and molecules will move at higher kinetic energies, means higher velocities, and the impact would be powerful. So that's why this mu gases will increase, okay? Now here also mu of gases doesn't vary significantly with pressure, okay? काफी लोग मुझसे ये पूछते हैं कि सर प्रेशर कैन डेफिनेटली ब्रिंग डाउन द साइज ऑफ द मॉलिक्यूल्स, ओके, सॉरी द साइज ऑफ द गैस, ओके, मींस द वॉल्यूम ऑक्यूपाइड बाय द गैस, molecules get close spacing or more spacing, then why pressure do not affect? Because this pressure change can bring the molecules close or away, but the spacing of the molecules, the molecular cohesion is very less in gases, okay? So the main reason for mu in gases is not molecular cohesion. So that's why even though because of the pressure, if molecules come close, the cohesion forces are not good enough to change the viscosities, okay? But if you increase the temperatures, ultimately molecules will increase and this mu will increase. So mu gases in general is proportional to square root of T absolute, okay? You have lot of laws like Sutherland law, for example, Sutherland law, which tells you mu by mu naught is equal to T naught plus or T plus S by T naught plus S whole power 3 by 2 into T naught by T, of course, okay? So this is Sutherland's law, and S is a constant, you have all this stuff, okay? But in general, the basic idea is this mu, since it gets affected by temperature and kinetic energy depends on square root of T absolute, so mu also depends on square root of T absolute, okay? So that's why if you increase temperature in case of gases, then dynamic viscosity will increase, whereas in case of liquids, the dynamic viscosity will decrease actually. Clear? Yes or no? Did you all understand why even pressure can bring the molecules close, but it cannot affect dynamic viscosity? Yes or no? Fine? Yes? Now, let's move to one more thing. Concept of kinematic viscosity. Okay? So, why do you need kinematic viscosity? Dynamic viscosity है, and हमको काफी headache भी है इसके से. So, why, when mu is there, then why nu? Anyone? बस यही पूछना चाहता हूं, बस इसी लास्ट पार्ट है इस चैप्टर में, ठीक है, जहां से मैं क्वेश्चंस पूछता हूं. तो बताओ. You already have mu, you have lot of formulas, all the headache is there, then why again nu? Because it comes too many times. Okay, so why it comes so many times then? Mu is only for linear velocity, right? This tau is equal to mu into dou u by dou y plus dou v by dou x. This can be any velocity field. Change in direction. Now, look, Okay, fine. It comes so many times. Okay, why it comes so many times? Let's see. So normally when there is a fluid flowing, okay, मैं बस 2 मिनट कॉन्सेप्ट एक्सप्लेन कर सकता हूँ. If there is some flow, okay, nu is equal to mu by rho, okay, and what does this tell you actually? Density signifies inertia. Inertia, okay. So this basically try to maintain the inertia. And mu is one property which resists the inertia. Inertia, okay, it resists the inertia actually. Like for example, मैं सिर्फ एक ही चीज पूछना चाहता हूँ कि मान लो कि आपके पास 2 बॉल्स है, ओके, एक है कि कॉटन बॉल लेकिन एक है कि स्टील बॉल फॉर एग्जांपल, ओके. दोनों बॉल्स का मास सेम है, लाइक लेट्स से देयर आर सम 100 ग्राम्स एंड 100 ग्राम्स. 100 ग्राम्स का कॉटन बॉल है एंड 100 ग्राम्स का स्टील बॉल भी है. सो इफ आई हिट यू with both the balls at same velocity, in which case you will get more hurt, steel या cotton? Mass, दोनों का mass same ही है and I am trying to hit with the same velocity, okay. Then which has higher impact? Steel, correct. So steel will hurt you more definitely, correct. क्यों? Because steel की density ज़्यादा है, correct. So if steel has more density, then ultimately it is difficult for you to stop an object coming with a high inertia, okay. Density signifies inertia. Mass same है तो force तो same लगेगा. Is it? Are you sure? Generally not, because it also depends upon the time at which it's stopping. So if you take the general case, then the 100 grams cotton ball and 100 grams steel ball, if they travel at the same velocity, you will get impact with the steel, because this steel has high density, and when things have high density, it's difficult for you to stop relatively, okay, because high density means high inertia. So when the mass is concentrated at a small point, see, if that's the case, if they make same impact, let's say you take a bullet, okay, instead of taking the bullet, you can make a big cotton ball which is of a same mass and you can hit with a cotton ball, but that do not have any impact, okay. Area increases, whatever the reasons concerned, okay. So if there is high inertia, then it troubles you. So whenever you are moving, okay, then this property is trying to maintain the flow and this property is trying to stop the flow. And when you have two contradicting properties, the ratio is what? ये तो full course है, but definitely it's a one shot, okay, full course but in one shot, clear. So this is mu by rho. Now let's see, this ratio is very very important. जब आप दो properties deal कर सकते हैं and those are contradicting properties, then definitely the ratio is very important, okay. Like जहाँ ये momentum diffusivity है, this is also called as momentum diffusivity. वैसे आपको thermal diffusivity भी पता है ना. So alpha is equal to K by rho Cp. This will try to hold the heat, this will try to throw the heat, okay. So that's why again contradicting ratio, this is thermal diffusivity. फिजिक्स तो सेम ही है दोनों केसेस में. सो थर्मल डिफ्यूजिविटी, क्लियर. सो दिस अलोन डजंट डिसाइड द फ्लो. लाइक इफ यू हैव, आई विल जस्ट टेल यू वन स्मॉल थिंग, okay. So if you have this, then depending on this of the fluid, this changes, okay, because you can change these two things depending upon the discharge. You can change the pipe diameter, so accordingly V average can get adjusted, but this cannot be there. Now tell me one thing, बस सिर्फ एक ही चीज सॉल्व करना चाहता हूं. How come mu is greater? We'll see, okay, just a second. Mu need not be always greater, because generally substances have density more than one, so that's why this mu is greater than this nu, okay. But in reality, if you check, I'll just ask you one question. Let's say you are going on a bike, for example, okay. You are going on a bike, you are going at 100 km, or firstly, you know, some nice guy maybe 30 kilometers per hour, okay, and suddenly he applied brake at this point. Then tell me, will he stop smoothly or will he stop in a very rough way? Just tell me this. You're going at a low speed generally and you applied brake, then will you stop smoothly or will you stop very rough? You'll stop smooth, good. But let's say now I made this 130, then generally at low speeds you'll stop smoothly, okay. But if you make this 30 to 130 and if you apply brake, then obviously you'll stop very rough, correct. What is the difference? In this case, this speed with what you are going, you have some inertia, and this is the resistance to the flow. Now, if inertia is high, means if you are traveling at high speed, and if there is a restriction, the case is rough. If out of these two, if you have this as high quantity, means your inertia is high, okay, then definitely this nu is low, and if you put nu as low, this Reynolds number is high. That's how this rough stopping at high inertia corresponds to turbulence. Okay, clear? The same thing, analogy, of course. Got it? If this guy is high, then definitely this is low. If you put low here, this quantity increases. Okay, that's why the flows with high inertia signifies turbulence in reality, whenever there is a obstruction in the flow. But the flows with low inertia, like creeping flows and all, you don't see any turbulence. Reynolds number is much small in that cases. Okay, now let's go quickly. Units. SI, if you check peacefully, you'll get meter square per second. This is same as MKS units. Okay, and in CGS, you have centimeter square per second, or this is also called as Stoke, and 1 Stoke. Okay, because you see centimeter square, if you convert, you will get 10 power minus 4 meter square. So 1 Stoke is 10 power 4 meter square per second. That's all. Okay, sorry, 10 power minus 4. Yeah, so it's very simple. Like this can be written as 10 power minus 4 meter square per second. So 1 centimeter square per second, which is Stoke, is equal to 10 power minus 4 meter square per second. Very straightforward. Then coming to nu of gases, this scales to T absolute power 3/2, because nu is mu by rho. Then this mu scales to T absolute power half, and by, if you take the gas to be an ideal gas, okay, so for ideal gas, rho is P by RT, so you have P by R into T absolute. So anyhow, pressure doesn't have much effect for a given substance, R doesn't change, so nu of gas is proportional to T absolute power 3/2. Okay, that's what you have. Clear? Math short term course for XC, yeah, definitely. Like last year, I'll take, जब पहले मैकेनिकल का एग्जाम होने दो, so उसके बाद XC के लिए मैं एक्स्ट्रा सेशंस लेता हूँ. Okay, like extra topics of fluid mechanics, maths. ठीक है? No issues. Then, so this is the story of this kinematic viscosity. Fine. And normally, if you check the standard cases, mu of water is greater than mu of air, and nu of water is less than nu of air. This is because since density of water is much large compared to density of air. Okay, so because of this. Mic issue. Sound is coming. Why? Everything is good. It's okay. Mic में थोड़ा problem है, but I hope it's fine now. Is it? It's okay now. Good. Maybe some wire would have been there. Chalo. So let's see. Let us look at some applications of viscosity, standard applications of viscosity, which all of you might have known by this time. If you have a shaft, okay, and if you, fine. So let's see. So if you have a shaft, okay, like this, and if you want to pull this at some velocity, okay, and this spacing h1, h2 is very small, then, you know, basically if you take a velocity profile at this point, 0 to this and 0 to this, so clearly you have the velocity profile. So F is equal to tau times of, let's say the shear stress acting at this point is tau 1 and shear stress acting at this point is tau 2. If area of contact is same, then you know F is equal to tau 1 into A plus tau2 into A actually here. So F is equal to mu1. Now since this gap is very small, you can assume linear velocity profile and du by dy, all these things if you write. So in this case, velocity is changing from 0 to v in a gap of h1. Here velocity is changing from 0 to v in a gap of h2. Okay, so mu1 v by h1 plus mu2 v by h2 multiplied with area. That's all. Okay, so this is the force what you need for pulling off this block, right? And definitely, you know, if you change these positions, then definitely this h1 h2 will change and F changes. Correct? Yes or no? Is this clear? If I take this gap to be h, and let's say this is h2 for example, then h minus h2 is h1 for example. If I log this, then depending on h1 h2 values, this f can change. So I can find a value of h2 where the function f is minimum. Okay, because this is a function of this h1 can be written as h minus h2. So for fixed mu1 mu2 spacing v a, f is a function of h2. Okay, so for f minimum, df by dh2 should be 0. Okay, you can do this, and if you do the complete story, you will get h2 is equal to h by 1 plus root of mu2 upon mu1. That's what you would get. Okay, or mu1 upon mu2, I think. Yeah, mu1 upon mu2. So this is the location where you should have the plate such that the force required is minimum. Anyway, you might have seen all these things. Then similarly, if you have a block, okay, which is one of the PYQ in mechanical. So if you have this block, then the velocity, terminal velocity, if you look at v, for terminal velocity, okay, sigma f, let's say this direction is the s direction, sigma fs is 0. Okay, for the block. So repeat this from starting. Which one? This one. Okay, so you have a plate, okay, and on the top of the plate you have one fluid, and on bottom you have another fluid, and दोनों fluids अलग है. ठीक है, so you have mu1 and mu2 being the dynamic viscosities. Then if you draw the free body diagram of the plate, you will have tau1 and tau2. So if this plate has to move at uniform velocity, plate में जो net force होता है वो 0 होना चाहिए. Correct? So if you make sigma fx is equal to 0, taking this as the x direction, you will get this equation. Fine? You will get this equation. Okay, and when you have that equation, then obviously these are the results. This is a function of single variable, you know how to differentiate and all. So if you differentiate, you will get this as h2 where things are minimum. Okay, so let's see in this case, if you draw the free body diagram of the block, fine. So definitely you have for this angle theta, mg sin theta, and fluid is in contact, so tau times area. So these two should balance each other. So mg sin theta is equal to tau into A, and what is tau? Mu into du by dy. This clearance, this is liquid film of thickness h, let's say. So if that thickness is very small, then you can assume linear velocity profile in this. So if you have a linear velocity profile, then this can be written as v upon h. Okay, that's all, into area. So clearly mg sin theta, so if you want v, mg h sin theta divided by mu a. It's a very straightforward PYQ which came in mechanical, of course. So it's just one line equations. Okay, all the equations that you do are one liners where the force, driving force should balance the resistance. That's all. Okay, because if this block has to move at uniform velocity, net force acting should be 0. Done. So the block travels in this direction at a velocity v. Okay, it's fine to all of you. Come on guys, everyone, type it in the chat box. Good so far? Clear to all of you? वेरी सिंपल स्टफ. ओके, इतना ज़्यादा दिक्कत नहीं है इसमें. देन let's move forward to some more examples. So this is a shaft where you have a bearing. So this is some bearing. So I am showing you only half of the shaft. Okay, so this is the axis. So you have a shaft of diameter d, basically it has some diameter d and some length l. So what is the force you need to pull this shaft at a uniform velocity? मैकेनिक्स से भी सॉल्व हो सकता है ये क्वेश्चंस, डेफिनेटली. वही है ना, ये सब्जेक्ट का नाम है कि फ्लूइड मैकेनिक्स. तो हम जो मैकेनिक्स का क्वेश्चन सॉल्व करते हैं, लेकिन उस मैकेनिक्स के क्वेश्चंस में कहीं भी फोर्स के लिए, लेकिन कहीं भी मूवमेंट के लिए हमको फ्लूइड मैकेनिक्स का नॉलेज चाहिए बस. ठीक है. देन लेट्स सी इफ यू हैव दिस शाफ्ट. ओके, सो वेयर दिस इज ओनली हाफ ऑफ द डायग्राम यू कैन सी. सो देयर इज शाफ्ट एंड देयर इज ए वेरिएबल बेयरिंग, वेरिएबल क्लियरेंस बेयरिंग. यहाँ जो क्लियरेंस है कि H1 एंड यहाँ जो क्लियरेंस है कि H2 of course. Okay, then if you look at the force, F is equal to pi mu u dl upon H1 minus H2 into ln H1 by H2. Clear? So this is the force which you need to pull the block at a uniform velocity. Clear? I'm not deriving this, as I told you, no derivations, but if you want I can do obviously, but it's not like if I'm not doing, I don't know that, but at this point I don't want to spend time in doing the derivations. Okay, variable thickness वाला. आप लोग ने स्ट्रेंथ ऑफ मटेरियल्स में एक क्वेश्चन कर सकते हैं ना. इफ यू हैव ए शाफ्ट ऑफ डायमीटर d1, then d2, then delta elongation is 4pl. if you pull with a force p and if this length is l, 4pl upon pi e d1 d2. E is the Young's modulus. You know this formula, right? I think last class में अपूर्व सा भी किया था. टैपर्ड बस. सो वैसा ही है, लेकिन यहाँ बार जो स्ट्रेट है बट द क्लियरेंस इज टैपर्ड बस. ओके, सो इफ यू सिंपलीफाई यू विल गेट दिस रिजल्ट, पाई म्यू udl by H1 minus H2 into ln H1 by H2. That's the expression for pulling this shaft at a uniform velocity capital U. Okay, something similar. Fine. Okay, so I'll now simplify the case for bearing with variable clearance. Okay, and then for shaft in uniform clearance, for shaft in uniform clearance. So you all know that the force is pi mu udl upon c, correct? Yes or no? Do you all know this? If you have a uniform shaft and uniform clearance, the c is constant all over, then the force required is pi mu udl by c. Many of you might have seen this formula by now, correct? Yes or no? समझ में है या नहीं? समझाया या नहीं? Tell me. Do you all know this expression? What is C? Clearance. C is clearance between shaft and bearing. Clear? क्या हम 2 मिनट लेके चेक करेंगे कि यहां ये आएगा ना या नहीं? Because we know for a more difficult case, so shall we spend some 1.5 minute to see whether you can get this expression from this or no? क्या हम चेक करेंगे सिर्फ ये किया 2 मिनट लेके? Pi is pi, mu is dynamic viscosity, d is diameter, l is length of the shaft. Okay, c is the clearance. बस देखिए, I want to teach you one thing, one good interesting thing actually. आपके पास एक शाफ्ट है, ठीक है? मतलब मैं एग्जैक्ट ड्राइंग्स नहीं कर सकता हूं, बट आई विल जस्ट शो यू सम ब्यूटीफुल थिंग्स. ओके, okay, So because of which this shaft is moving at a speed u. Okay, then the force which you need is F is pi mu v or u dl upon h1 minus h2 into ln h1 by h2. Okay, this is the case. But now let's see if this h1 and h2 are same, for example. Okay, and you have oil in between, of course, you know, you have a lot of viscous oil which is sitting inside. So this is the viscous oil. Then for h1, for a constant clearance, of course you can do using fluid mechanics knowledge, but let's simply see C is equal to h1 is equal to h2. Okay, then can I take h1 common here by h2? If you take common, h1 by h2 minus 1 into ln h1 by h2. Correct, this is what you have exactly at h1 equal to h2 in this expression. If you put h1 equal to h2, this becomes ln 1. Okay, so 0. We will cover all 14 chapters 100%. I guarantee that. Okay, so the only thing is you should pay attention. Knowledge is never for free. Okay, you should pay attention. Clear? So if this h1 and h2 are same, this becomes 0, this also becomes 0. Yes? Correct or no? Tell me. If you put h1 equal to h2, this becomes 0 and this also becomes 0. Yes? So when you have 0 by 0, what is the thing you will do? When you get 0 by 0, L-hospital, correct? Let's apply L-hospital. And h1 coming very close to h2 implies x tends to 1. Okay, so if you look at this expression, limit x tends to 1 ln x by x minus 1, 0 by 0 form. So you differentiate this 1 by x by 1, which is 1. That's all, which means this bracket becomes 1 when h1 and h2 are very close. Then that's how you have pi mu v dl by clearance. That's all. This term becomes 1. That's how you get this expression. Okay, got it? It's a 0 by 0 form. You have applied L-hospital and then you figured out log by this clearance term, the difference in the clearance term. This ratio fits to be 1, and so here if you have this ratio as 1 when h1 is coming close to h2, you have only pi mu u dl by h2, but h1 h2 c all are same, so that's why you get the expression. Okay, yeah, I'll take Maha Abhyas tomorrow. Okay, so this is one question. Then still you have a cylinder. So if you look at, if cylinder is released from rest, okay, if cylinder is released from rest, okay, then the velocity profile will go something like this. It becomes asymptotic. Okay, so this is V terminal. So again, how do you calculate V terminal? So what is the physics behind it? So if you see the physics behind it, initially when you drop the block, okay, then the shear stress acting on the block because of this fluid thickness is very small. Okay, but as the block starts accelerating, this viscous stress will also start accelerating. Understood? So you can see clearly, initially when you leave the block, here the velocity gradient in this oil is very small. Okay, but as this block keeps increasing its velocity, you will have a larger velocity gradient. So because of which mu into du by dy, so the du by dy term increases. Okay, so the weight, gravitation will be there, but viscous effects will also be there. So if you look for V terminal velocity, how can you do this? Weight of the block mg should be balanced with, so if this block is of mass m, then that should be balanced with the viscous forces. Okay, so what is the viscous force? Shear stress mu into du by dy. So V by the clearance h into area of solid fluid contact, which is pi dl. That's all. Okay, so V is equal to mgh by pi mu dl. For V terminal, okay, so you have this as the terminal velocity in this case. Fine. F net is equal to 0 and you do all the analysis, you will get V is equal to mgh by pi mu dl. That's all. Clear? Then let's go to one last case maybe in this. So you have the cone, the torque, rotating elements. Okay, so torque required to maintain constant omega. Constant omega. Okay, which means again net torque acting about the z axis is 0. If you take this as the z axis all over, then this torque is given by, if you have this as diameter d, the base diameter, then T is equal to pi mu omega d power 4 by 32. What is the clearance? H sin theta. So this is the expression for the torque which makes this conical shaft rotate at a uniform angular velocity. Okay, so this T is equal to pi mu omega d power 4 by 32 h sin theta, and in case of uniform shafts you don't have this sin theta. Okay, so simply it's pi mu omega d power 4 by 32 c. So what is the power then? Power required is torque into omega, which is pi mu omega d power 4 by 32 c sin theta. That's all. Okay, so these are the expressions for the torque and the power which are needed. Again, these things are very simple to derive, but I'm not doing the derivations as of now. Okay, just giving you the expressions. Clear? Fine. So let's see if it's clear, then let's move forward. This is the last thing. So if you have a sheet of radius r actually in this, okay, and h is the clearance on both the sides, then tau torque required to maintain uniform omega or uniform angular velocity. Basically this omega symbol is given. Fine. So T is equal to pi mu omega, d power 4, or if you call this as diameter d, so d power 4 by 32 times h into 2. That's what you have. Okay, so this is into 2 clearly. x1 by sin theta. Yeah, in the previous case it's 1 by sin theta, but here you have no sin theta actually. This into 2 is because oil is on both the sides. Okay, so it's filled with oil on both the sides actually. So this is with the oil on both the sides. So 2 because oil is on both the sides. So then obviously what is power? Pi mu omega square d power 4 by 16 h. That's the power actually. Okay, so just you can take these expressions. Many of you might have seen these derivations in fast track, in in crash course, in other elaborative sessions and all. So right now I'm just giving a quick recap of what you have learned. Okay, then so let's see if that's the case. I would like to solve one question at this point. So can someone tell me this? Maybe I'll give you some time to solve this. 2 minutes or 2.5 minutes. Okay, come on, solve this and enter the answer in the chat box. Two coaxial cylinders 250 mm high have a liquid in between them. The outer cylinder has internal diameter 100 and the internal cylinder has external diameter of 97.5. Viscosity which produces a torque of 1 Newton meter upon inner cylinder when outer one rotates at 90 rpm. Come on, do this. Solve this question. If you want derivations, then I can post it in my Telegram channel. Like in the beginning, I have shown you my Telegram channel link. So if you are there, then I can maybe post it if you want. The derivations of all these things. Okay, normally I do them in a paid batch, I mean the full course classes, because we have ample time, but right now it's small. So come on, do this. Okay, I'll post it, no issues. Come on guys, check up, solve this question. Make sure, try one thing clearly, the inner cylinder is fixed, okay? Outer one is rotating in this case. Okay. So last 15 seconds, sort of. Any luck? किसके पास आंसर है लेकिन टाइप करने का मतलब इतना कॉन्फिडेंट नहीं है? चलो, done. Okay, so let's see, let us solve this question. There are two coaxial cylinders. Okay. And similarly, you can see two coaxial cylinders. Okay, so we have fluid here in these gaps. So what you have done, you have fixed the inner cylinder. Okay, you have fixed this little fellow. So let's say this is DI. Okay, and this is DO. Then, and these are of some length L. Now, when inner cylinder is fixed, you want to rotate the outer cylinder. Okay, so now let's see, there is some torque which you have applied, some torque T. So when this rotates at 90 rpm, find the viscosity of the liquid. Good. So let's see, since torque is given, can I say torque is equal to force, viscous force. Okay, viscous torque is equal to viscous force into, from this center of rotation, from this axis of rotation, what are the points which are rotating? So these points, correct? So this distance is half of the outer diameter, correct? So this is d outer divided by 2, because the torque is always applied from force into the radius from center to the point of rotation. So which is Fv into d outer by 2. Now how do you get this Fv? That's the question. So this torque Fv can be written as mu or shear stress tau v into area of solid fluid contact. Okay, so where is the area of solid fluid contact? This complete circumference at all these points, like if you see the outer cylinder, at all these points the fluid is subjected to shear. Okay, so pi times d outer into L into d naught by 2. So this is the area, pi d outer into L is the area of the solid fluid contact. Do you remember, in case of the shafts where the outer one is fixed and inner one is rotating, you will multiply pi dl. Do you all remember this? Yes or no? Correct? if you have two shafts, out of which if the outer one is fixed and the inner one is rotating, then you write pi dl, where d is the diameter of the shaft. Okay, so you should always take that area into the consideration where your fluid solid contact is there and the area is rotating. Okay, that happens at outer radius here. So pi d outer l. Okay, so now let's go for the shear stress. So shear stress कैसे होगा? Mu into velocity gradient. So velocity gradient कितना होगा? यहाँ जो velocity है वो 0. At all these points the velocity is 0 because of no slip condition. ठीक है? And at all these points velocity की वैल्यू कितना है? d outer by 2 into omega. करेक्ट? मान लो कि ये shaft omega speed से रोटेट हो रहा है. So the velocity at phi at all these points is d naught by 2 into omega. So mu into यहाँ जो velocity है ये 0 and यहाँ जो velocity है d naught by 2 into omega and ये clearance ये कितना होगा? So clearance C is outer minus inner diameters by half. करेक्ट? अगर मान लो कि आपने इस 2 भूल गया then definitely answer goes wrong. Okay, because the gap between these two is only the radial clearance, but the difference in the diameters gives you the diametral clearance. Okay, so that's why mu into then velocity gradient d naught by 2 into omega by minus 0 upon d naught minus d inner by 2 actually. So this is the velocity gradient. So mu into du by dy ये होगा कि shear stress into pi d naught l into d naught upon 2. So ये होगा हमारा expression. Okay, and now everything is given. We should figure out what is the values of dynamic viscosity. That's all. Clear? यहाँ तक सबको ठीक है या नहीं? Are you all clear till this point? Because I know अगर मान लो कि मैंने outer cylinder fix किया and inner cylinder को rotate किया तो आप सबको पता है डायरेक्ट फॉर्मूला सब्स्टिट्यूट करके आंसर देते हैं, लेकिन थोड़ा सा ट्रिकी आया तो कैसे सॉल्व करें? Fine. So let's see. So if you simplify this, then let's see you need mu. Okay, so mu is equal to torque divided by पहले इस टर्म को d naught minus d inner and 2 is also there, so 2t d outer minus d inner divided by d naught pi d naught cube l pi d naught cube into l. Okay, so pi d naught cube l by omega. Omega is also in the denominator. बस इसको calculate करना पड़ेगा. So 2 into what is the torque that you need? Torque of 1 Newton meter. Kind people, आसान values दिया था. D outer minus D inner. So 250 mm high. So this length L is 250 mm. इसका मतलब यह है कि 0.25 meters, 1/4 meter. D outer ये कितना है? Have a liquid in between them. Outer cylinder has internal diameter of 100 mm. तो ठीक है, D outer is 100 mm. इसका मतलब है कि 0.1 meter. And D inner ये कितना होगा? And the internal cylinder has external diameter of 97.5 mm. ठीक है, so 97.5 mm. So 0.0975 meters. Clear? So this is D inner. Length is known to you. Find the viscosity of the oil when the outer cylinder rotates at 90 rpm. So N is 90 rpm. So obviously omega pi N by 30. So which is 3 pi radians per second. Bas. So these are the input values. So just substitute करके calculation कर लो, हो जाएगा. So D outer minus D inner. So 0.1 minus 0.0975 upon pi D outer cube L 0.25 into omega, which is 3 pi. Okay, so you will have mu in SI units, which is in Pascal second. Okay, so what are the units they are asking you in the question? Find the viscosity of the liquid. Okay, I would have specified more, but I hope all of you understood how did I get this. D for the velocity which is in motion, 100%. Okay, wherever there is motion of the elements, so at that junction what is the diameter? That should be taken always. Clear? So if you simplify this, let's take a calculator quickly. 2 into 1 into 2 into then 0.1 minus 0.0975 this value divided by 0.1 cube divided by pi square So pi square into 3 times of 0.25, 0.75, 0.75 into 10 power minus 3. So this value, this is mu, 0.675 Pascal second. That's the answer. Okay, 0.675, 0.67 या 0.067? मैंने कुछ गड़बड़ किया? नहीं, 0.675 feasibly looks very nice for oil. मुझे नहीं लगता है कि ऑयल को 0.01 से नीचे आ जाएगा, because liquids, oil is a liquid, no, obviously, so liquids have some feasible range. Because air की dynamic viscosity ही 1 centipoise, mu of air is 1 cp, so which is 10 power minus 3 Pascal second, 0.001 Pascal second on an average. Okay, and obviously if you write 0.06, which is almost like 6 times denser, no, that's not the case. So practically 0.06 is wrong. Okay, 0.675 Pascal second. Good. तो सबका समझ में आया या नहीं? इस क्वेश्चन कैसे सॉल्व करना है? ओमेगा फॉर्मूला, ओमेगा here. So omega is 2 pi n by 60, which is nothing but pi n by 30. Okay, pi rpm by 30. Clear? That's all. Fine. Is this okay to all of you? You put 0.1 where? कहाँ? 100 mm मतलब 10 centimeters ना? So 10 centimeters is 0.1 meter. No, this session is for mechanical, okay, not for XE. Okay, XE topics gets covered obviously, but not the case. 0.1 cube as 0.001. That's what I have replaced. Yeah. जब मैंने कैलकुलेशन किया था is 0.001 is nothing but 10 power minus 3 or 0.1 whole cube, whatever. Fine. So let's see. Okay, so solve this question. It's also a good question actually. विस्कोसिटी के बारे में काफी चीज सीखा हमने, तो 3 मिनट्स देता हूं मैं, ठीक है? चलो सॉल्व करो. mu1 and gap of h1, mu2 gap of h2, mu3 gap of h3. So there are 3 fluids and force F is there. XE के लिए अलग से कुछ सेशंस होगा क्या? या डेफिनेटली मैकेनिकल एग्जाम के बाद होगा वो सेशंस. .1 cube is not 0.0001. Okay, only 2 zeros will be there and third will be 1. Clear? If you want I can show you maybe 0.1 cube, 2 zeros आते हैं, ठीक है? चलो सॉल्व करो इस क्वेश्चन. In case the painting is light, so mu3, mu2, mu1, okay, h1, h2, h3, and there is some force on this plate. Fluid is moving. Hey, it's okay, yeah, no issues. Mistakes can happen. Come on guys, half of the time is done. Yeah, I remember you, man. Prasenjit Das. विजय बैच में है ना आप? कोई दिक्कत नहीं, मैकेनिकल का एग्जाम होने दो, उसके बाद मैं जो एक्स्ट्रा टॉपिक्स है यहाँ, सो उसके लिए एक एक्स्ट्रा सेशंस लेता हूँ. ओके, मैथ्स के भी और फ्लूइड मैकेनिक्स के लिए. फ्लूइड मैकेनिक्स के मैं और संदीप सर या मैं और शिवम सर, हम तीनों में मिलके करेंगे. एंड मैथ्स आई विल डू अलोन, नो इश्यूज. Last 15 seconds, guys. Come on. Okay, done. So let's see. You have three fluids. Okay, first, second, and third. So let's read the question. Fluids of viscosities mu1, mu2, mu3 are contained between two plates. Assume linear velocity distribution. Each plate 1 meter square in area. The thickness are h1, h2, h3. Force applied on the upper plate is 100 newtons. Velocity of the upper plate. Okay. Here no velocity is given, so assume this is static. Okay. So solution. Assuming bottom plate is static. Now tell me, if in each layer, if you have, say, a topic first time, but this is a very, I mean, not with three fluids, but at least 1, 2 fluids is like a very often thing. Okay, so let's see. In this case, this is one interface, interface 1. This is interface 2, and this is plate. Okay, where you have. So let's see. In this three interfaces, or basically in the three domains, you have linear velocity profile. Okay, if you have linear velocity profile and u is changing only with v, only with y. Okay, so this is y direction, let's say. So this is with y. Okay, then u has linear variation. Then can someone tell me what is tau variation? If tau is equal to mu into du by dy, because the spacings are all very small in general, 0.2 mm, 0.25 mm. So for tau is equal to this, and if u is a linear variation, then can someone tell me what is tau value? Tau should be constant in a given domain, correct? So this tau is uniform. Tau has to be uniform. But tau being uniform doesn't mean that the velocity gradient should be same. Okay, because depending on the thickness and depending on this mu, velocity variations can happen. That's what you see. The lines will have different slopes, of course. Okay, and slope multiplied with mu denotes the shear stress, of course. Okay, so at this interface, if this interface has to move at a uniform velocity, then for interface 1, to have uniform velocity, the shear stress acting at this point from the bottom part and from the top part has to be same. Yes, will you all agree? मैं बोल रहा हूं कि मान लो कि इस फ्लूइड लेयर यूनिफॉर्म वेलोसिटी से ट्रैवल करना पड़ेगा, देन द बॉटम शियर स्ट्रेस विच इज एक्टिंग एंड द टॉप शियर स्ट्रेस विच इज एक्टिंग शुड बी सेम. दैट्स व्हाट माय आर्गुमेंट इज. Correct? So this tells you, if you for example take the interface here, then the shear stress at this point and the shear stress at this point both should be equal in magnitude. Okay, so therefore tau 1 should be equal to tau 2. So what is tau 1? Mu1 into, let's say this velocity of the interface is v1, for example. Okay, so v1 by h1 is equal to mu2 v2 minus v1 by h2. Correct? This is what you have. Similarly, if you look at this second and third interface, okay, so if you look at this second and third interface where you have the interface number 2, at this point here the velocity is v. Okay, and here this is velocity of interface 2, actually here. So if you have this velocity of interface 2 here, or v2, you call this for example v2, then similarly for this interface to move at uniform velocity, for interface 2 to move at uniform velocity, tau 2 should be same as tau 3, okay, and this tau 3, which is the shear stress at which is uniform in this layer, this shear stress acting at any of this point can be written as this F divided by the area of contact, okay. So this tau 3 can be written as F3 divided by area actually here. So what is F3? Let's see. F3 is equal to A into tau 2, and what is tau 2? Mu 2 times V2 minus V1 by H, correct? This is what you have, and of course you can see they are asking you the velocity V of the upper plate, so you need this. So this tau 2 can also be written as, or let's see, this tau 2 can be written as mu 2 V2 minus V1 by H2 mu 3 V of the plate minus V2 by H3, correct? So this is what you need. Yes or no? Can you all understand these things? Yes? So please type in the chat box. Is this okay to all of you? So basically shear stress should be equal at interface 1 and 2 and also at interface 2 and 3, but since the velocity profile is linear, then you have a constant tau, so these things all should be same. Yes? Now also you have one extra feature. This tau 3 can be written as F3 by A. You know F, you also know what is A, which means you know this value, this value, basically you know this value actually. So let's see, in this equation mu1 is known, h1 is known, mu2 is known, h2 is also known, and this v1 minus v2. So if you solve this equation, you will have some equation in terms of v1 and v2. Relation between v1 and v2 is there here. Similarly, in this equation you will have relation between v plate and v2, and you can connect this v plate to this value, okay. So F by A, F3 force on plate, let's say. So force on plate is equal to tau 2 into area, and area of contact in each case is 1, okay. So each of the cases has 1 meters per second square area. Can you explain again? Yeah, I can explain. So see, if this interface has to move at uniform velocity, the shear stress which is acting, yeah, I'll brief, see carefully. There is one interface here, okay, and इस interface uniform velocity से जाना चाहिए. Then if this interface has to move at uniform velocity, the bottom shear stress and the top shear stress should balance each other, and net shear stress acting or net shear force acting on the layer should be 0, correct? Yes? That's how I got this tau 1 equal to tau 2. Okay, and if even this layer has to move at uniform velocity, same thing, the stress balance should happen. So tau 2, let's say you have tau 2 and tau 3, so this should also be same. So that's how you get this. Clear to all of you? Yes or no? Yes or no? Fine. V plate minus V3 नहीं होगा. V1, V2, V plate. Okay. There is nothing like V3. V3 is nothing but the V plate actually. Velocity of the third interface. Okay, others? Clear? So you have these equations, one equation, second equation, and also you have one more equation. This F plate, force acting on the plate, is equal to 100 times 100 Newton. The velocity of V of the upper plate is dash. So firstly you can write V2 in terms of V1. So let's see, V1 times of mu1 by h1 plus mu2 by h2 times h2 by mu2. is V2. Okay, so this is V2 actually here. And similarly, if you look at V plate in terms of V2 and V1, so this can be written as V plate is equal to, so what is V2 minus V1? V2 minus V1 can be written as, so V2 minus V1 can be written as mu1 by mu2. First of all, mu2 by h2. Let's simplify this equation little carefully. V plate minus V2 is equal to mu2 by mu3 into h3 by h2 into V2 minus V1. Okay, now you can write V2 minus V1 in terms of, you can write V2 minus V1 in terms of this. Okay, or directly you can write V2 minus V1 in terms of V1, and again you can also replace V2 in terms of V1. Since F is known to you, you will be left with only one unknown in this equation. Will you solve this? I'll leave it. The job is very simple. You have three equations. One is this, second is this, and third is this. You know area, you know F3, so you have tau 3. So three equations for V1, V2 and V plate. That's all. Three equations, three unknowns. Will you solve carefully? Okay, it's just substitution of values. Three equations with three unknowns. If you solve, you'll get interface 1 velocity, interface 2 velocity, velocity of the plate. That's all. Okay, first equation, second, sorry, this is second, and this equating tau 3 is equal to F3 by A is the third equation. That's all. Okay, so just solve this. You'll get three equations with three unknowns. It's a linear system. You can solve. Clear? Well, I'll post the answer after some time, maybe the exact answer, because right now I don't have the exact answer key for this, but this is the way to solve this. Okay, 0.583. Yeah, if many of you are getting 0.583, I think then it should be the correct answer, but it's a straightforward question. Okay, now after it's only maths. Basically equating the shear stresses at the interfaces is fluid mechanics. Okay, so let's see. Let's go to three last concepts in this case. Non-Newtonian fluids, which is one very important topic, to be frank. Okay, so fluids which obey Newton's law are called Newtonian fluids, and fluids which do not obey this Newton's law are called the non-Newtonian fluids. So basically fluids that doesn't obey Newton's law of viscosity. So how can these things be modeled? You know, we have Oswald de Vallis model. It's okay if you need not remember this name very much, but the equation tells something like this. Tau is equal to tau naught plus A into du by dy whole power n, of course. Okay, so the shear stress at any layer in any fluid which is in motion is given by this equation. It's a power law model, of course. As you can see, there is some power of this dynamic viscosity. Okay, and this is only when u changes with respect to y again. Clear? So this is the Oswald de Vallis model. Okay, getting scared by looking at this? No need to scare. Okay, things are simple, man. ठीक है, कोई दिक्कत नहीं. अगर कुछ इश्यू हुआ तो एक बार बता दीजिए चैट बॉक्स में, मैं डायरेक्ट रिजल्ट देता हूँ. Yeah, okay, I'll tell you, let this chapter gets finished. Okay, maximum it takes another 20 minutes. We can finish off this chapter. Fine. So if this is tau naught, so tau naught is called yield shear stress, or it's also called as threshold shear. Okay, then generally all fluids start motion or sets into motion at tau naught tends to 0. Means for a very small shear stress, they immediately starts setting into motion, of course. Okay, only result brief, otherwise session is long. Yeah, that's what I am going to tell you now. Okay, so if you have tau is equal to 0, so if you make this tau naught very small, of course there is a limitation, we'll come back. So tau is equal to A into du by dy whole power n. This A is called flow consistency index, index, n is called flow behavior index. Okay, so this n is called the flow behavior index. Now this tau can be written as a du by dy whole power n minus 1 times du by dy, correct? Now if you want to generalize this as some Newton's law of viscosity form, if you take this term as like eta, okay, then this can be written as tau is equal to eta times du by dy. Yes or no? Now this looks very straight close to Newton's law of viscosity, and this eta is called apparent viscosity here. Okay, yeah, so which is not fixed because changing depending on du by dy, eta changes. So therefore eta a du by dy whole power n minus 1 is called apparent viscosity. Now let's look at many things where people have seen. So if you plot tau and du by dy, okay, then can someone tell me if tau naught is 0, a equal to mu, n equal to 1, what does this equation tell you? Tau naught is 0, a is equal to mu, the dynamic viscosity of the fluid, and n is equal to 1. What does this equation, if you put a equal to mu, n equal to 1, what do you get? Newton's law again, correct? So Newton's law for simplified version. So you have some equation like this, tau is equal to, sorry, now this is y axis, this is x axis, okay. Now if n is constant, if let's say n is not changing, okay, then this is of the form y equal to mx, so it should be a straight line. So this is Newtonian fluid where you have tau naught is equal to 0 and n is equal to 1, of course, okay. But now if you see, I'll ask you one thing, if you take eta a into du by dy whole power n, okay, now tell me for n greater than 1, as du by dy increases, what happens to eta? Any one of you? If n is increasing, if n is more than 1, and if du by dy is increasing, then what happens to eta? Decreases or increases? N is positive power, okay, n is more than 1, okay, n minus 1, sorry, this is n minus 1, yeah, this is n minus 1, no, because it's apparent viscosity, so n minus 1, of course it increases, correct, because when n is more than 1, this n minus 1 is positive, so if du by dy is increasing, then this whole term increases, clear? So we have some set of fluids where the slope increases with du by dy. If you see, if you draw tangents here, the slope of the tangent keeps increasing, which means you can see this eta value increases in this case, okay. And this set of fluids which you have shear stress increasing, tau increasing with du by dy, are called shear thickening fluids. Why I am stressing on this topic is because lot of questions turn up. These are also called as dilatant. Similarly, this is n greater than 1, tau naught is equal to 0 and n greater than 1. Similarly here, if you take n less than 1, you will get a fluid with decreasing slope, okay. So initially slope is high, but later they keep flattening up, okay. The slope becomes, the tangent becomes flat, and these guys are nothing but, so we have pseudoplastics, and they are also called as shear thinning fluids, okay, where if you try to disperse them fast, you will see more resistance, okay. कुछ explain भी बता दीजिए, definitely देखिए, this is slope of this curve, correct? Eta is nothing but slope on tau versus du by dy axis. Now for fluids with n greater than 1, okay, मान लो कि एक fluid है जिसको n value 1 से ज्यादा है, then this term, if you keep increasing this du by dy, this n minus 1 is positive, so this term also increases, correct? Eta is the slope, so eta denotes the slope of the tangent, correct? So if du by dy is increasing, eta should also increase, which means the curve should be in such a way where if you increase du by dy, the steepness of the curve should also increase. That's what this actually. Okay, कुछ एग्जाम्पल बता दीजिए इन वे में प्रिंट होगा. Okay, see these cases where you have shear thickening fluids. Let's say if you have a wet sand, okay, normally beaches होते हैं. So if you go to a wet sand, or normally if you see wet sand where there are some sand particles in water, if you try to move the sand slowly, it's easy for you to move the sand, okay? But let's say if you try to push the wet sand very fast, you'll feel lot of resistance, correct? Yes? Have you experienced this? Wet sand, it's easy to disturb it when it's when you try to disturb it slowly, but if you try to disturb it very fast, you'll feel it so difficult. Okay, so lipstick is not, of course, this class. We'll see rice starch. Okay, so we have these examples, but anyway, you'll see this is a big set of examples which I have given here, so you can later copy peacefully. Okay, so these are the examples, some set of examples for non-Newtonian, examples of Newtonian and non-Newtonian. Okay, whatever, toothpaste, butter, rice starch, what all you see, you can find them all this. Basically I have framed this list by looking at Munson. Okay, then Frankenwright, some examples are there again. Then again in IGQE there are some examples. Okay, I take a screenshot. No issues. Okay, we can have this PDF. Okay, so don't worry. Then let's see. But there are few fluids where initially if you start applying shear stress, for some time you don't see any deformation. Okay, for some part there is no deformation, and then after they obey Newtonian type. So these are called Bingham plastics. Tau naught not equal to 0 and n equal to 1. So you have Bingham plastics here in this case. Okay, and this line corresponds to ideal solid. Why ideal solid? Because whatever the shear stress you keep applying, you won't see any U, means there is no flow of particles, and this line corresponds to ideal fluid, of course. Or you can say eta is 0. Clear? So this ideal fluid, of course. Fine. Yeah, these are the Bingham plastics, and these fluids, they depend on velocity gradients, and there are some set of fluids which depend on the time basis. So if you look at the time basis ones, these things basically. Okay, so if you have time on x-axis, eta on y-axis, then in some cases they increase and in some cases they decrease. So basically these are eupectic, where they are also called as time thickening. Means if you just leave them, with time they get thick. Okay, like cement. Okay, you mix cement with water, you make it like a semi-solid, and then you leave it. Then with time what happens? Ultimately this becomes so hard. Okay, so then after you cannot deform it, so eta increases. Like you can see gypsum in water I have given as one of the examples, and similarly this is thixotropic. Time thinning fluids. Okay, so these are the set of fluids. Normally in XC and all they can ask you so many times these things. Chalo. So we have bulk modulus. Of course you have two things, adiabatic and isothermal. So normally if you see ES and ET actually here. Okay, so what does the bulk modulus denote generally? Minus 1 by, okay, V or minus of dp upon the volumetric strain. Okay, you might have known by this time. So if you are maintaining at isentropic conditions, this is isentropic bulk modulus. Isothermal conditions, then you can have this. Okay, so yeah, ES, ET, these are the adiabatic and isothermal. Now let's see if you look at this one. Okay, if you want to, if you have a substance, so this is substance of mass m, and if you apply some differential pressure dp on this, okay, then this volume changes by dv. Now imagine if I ask you, if you are applying some pressure difference on a substance and if the volume is changing, okay, for changing that volume, if your pressure difference is high, okay, if the pressure difference you have to apply is very high, then is it easily compressible or difficult to compress that? Come on, tell me. There is a substance and you want to compress it, and at the point of compression you have to apply a high delta P. Then is it easy or difficult to compress this? Difficult to compress, correct? So for creating 1 unit volumetric strain, if this is high, this is also high. Okay, so this implies high E implies low compressibility. Okay, so if you want to decide whether a flow, whether a substance, whether a fluid is compressible or not, you will look for the bulk modulus value. If bulk modulus is high, then the compressibility is low actually. Okay, so compressibility again, so compressibility K is equal to 1 upon E. If this is isentropic, this is also isentropic. If this is isothermal, this is also isothermal actually. Okay, then to check whether a flow is compressible or not, we check Mach number. Okay, so incompressible fluid is something different from incompressible flow. Okay, we'll talk about these things again. So I'll give you one question again because we have some time to talk it. So solve this question. I'll give you some time. Solve this question. All the liquids in general are hard to compress. The compressibility effect, variation in density, may become unavoidable at great depths in the oceans due to enormous pressure increase. At a certain depth, the pressure is reported to be 100 megapascals and average bulk modulus is about 2350 megapascals. Taking the liquid density at the free surface to be 1030, density at specified pressure is dash. Come on, solve this. Bulk modulus is indirectly proportional to compressibility. Okay, if E is high, that means you are applying a large delta P. Okay, which means the compressibility is low for the substance. Solve this question. Good evening, Sharma. (996.21) definitely no. No, it's not going to be 996.21 definitely. Man, they are asking about the density. Okay, when you get some values, please check how 0.0413 can be density of water, that too of seawater. 43.829 107.4. गाइस मैं एक चीज बोलना चाहता हूं आपको. मान लो कि गेट एग्जाम पे आपने किसी क्वेश्चन सॉल्व किया था, ठीक है, एंड एक वैल्यू आया, देन यू शुड लुक एट द फिजिकल feasibility of the value. Okay, make this a habit that checking physical feasibility of the answer will avoid entering wrong answers. Chalo, let's see. solution. If you have a free surface which is at O naught and Z naught is 0, and at some location you have some pressure at Z, you have P. Here this is P1 and this is P2 for example, or P naught let's say, and you have P naught and P, of course let's say this is P, and density here is rho. They have given you the bulk modulus of water. So given P naught is equal to how much? So 100 megapascals on the, at certain depth pressure is 100 megapascals, average bulk modulus is this, and surface density is rho naught. Okay, so on the top let's see, you have 1 bar or 1 atm pressure. So what is 1 atm? 101.325 bar. Okay, and 1 bar is equal to 100 kilopascals. So 101.325 into 100 kilopascals. So this can be written as 0.101 megapascals. Okay, so this is the pressure on the surface, at the surface. Clear? Approach same था, लेकिन बहुत दोनों approaches सही है क्या? चलिए, let's see. This is P naught and this is P. Okay, so if this is P, then what is P? 100 megapascals. ठीक है, and what is the bulk modulus? You got bulk modulus is 2350 megapascals. Rho naught is, what is rho naught? 10. So density on the surface is 30 kg per meter cube. So what's the density at that location? Okay, so now let's see. You all know that delta P or dP by dV by V, this can also be written as dP upon d rho by rho, correct? This is what you know. So E can be approximated as, you can say approximation as dP P2 or P minus P naught by rho minus O naught by rho naught actually. Okay, now you need this density value which tells you rho is equal to rho naught plus P minus P naught by, okay, so this can be written as rho naught plus rho naught into P minus P naught by bulk modulus. That's all. Okay, so this is the equation straight away from this. So if you solve 1030 1 plus, so let's put both the things in megapascals. So 1 plus P minus P naught 100 minus 0.1 by 2350. That's all. Okay, so if you solve this, you have density at that point as some value, then 100 minus 0.1 99.9 divided by 2350, this value plus 1 into 1030, so 1073.78. So that's the variation in terms of density. Clear? 1073.78 or 1074, but this value is an approximated value. Okay, in reality if you want to do this question, you should do it this way. So this is approx. So then what is the exactness? Let's see, or else I think I have some question here. So exact should be solved like this. Exact is E is equal to rho dP by dO. So dO upon rho is equal to dP upon E, rho naught to rho, P naught to P. So in this you have only one unknown, which is this, but both give you almost the same result because this is linear approximation of this. Okay, we should integrate. We should actually do by integration 100%, but this also gives you the same idea. The reason being, if you observe this expression carefully, rho is equal to rho naught into 1 plus delta P by E, correct? So if you see that by integration, let's see, because some of you have asked, okay, so if you see integration of this ln rho upon rho naught is dp, which is p minus p naught by e. So what is rho? Rho naught into exponential of p minus p naught by e. Even if you do this, you will get almost the same answer in this case. Okay, rho naught, which is 1030 into exponential of 100 minus 0.1 by 2340, whatever, correct? 2350. Okay, it's not 40, 2350. So if you simplify this expression, you will see again 99.9 by 2350 exponential e power x into 1030. So 1074.7. Okay, so this is exact answer, and this is approximation, which is 1073.7. so there is almost 1 kg per meter cube difference. Okay, but in exam you can do anything. In fact, better this, you do this, but if you see this expression, rho is equal to rho naught times, if you expand this is e power x, so 1 plus delta p by e plus delta p by e whole square and so on infinity. And if you take linear approximation till this, so this is linear approximation that you have exactly this. Okay, rho naught, if you take common, 1 plus delta p by e, so whatever the answer you got there, that's the linear approximation. That's why a small value difference is there. Okay, but in fact this would have been the exact value, and normally in case of liquids this e is very high, so that's why the value comes very small. Delta p by e is almost how much? By 2 factorial and so on. Okay, did you all understand why both the values are very close to each other? Okay, this happens exclusively if you do for liquids, but if you have gases, then this es can be changing, so that's why this is the best accurate way to do the question. Got it? Okay, Ritik? Good. So one last concept, which is surface tension, then after we can start manometer measurements. So surface tension, so first of all this is a binary property. Fine. So if you have binary property, then it depends on substances at the interface. Substances at the interface. Okay, so clearly, like sigma of water air interface at around the common value is 0.073 Newton per meter. Okay, so this concept of cohesive forces, adhesive forces, imbalance between cohesion and adhesion, all this story is known. Okay, I need not draw the sphere of influence again and explain, right? So this is due to sigma is due to imbalance between cohesion and adhesion, right? So which is again a standard theory that all of you know. So when these cohesion forces and adhesive forces are not balanced, you have the surface tension. Okay, if cohesion is dominating, you will see capillary fall. If adhesion is dominating, you will see capillary rise. Okay, so let's see some applications, whatever we have consequences. Then first, droplets, or basically if you see a mass of water or any liquid in general, a mass of any liquid stabilizes in spherical form. Spherical form, correct? And why this? Because this has minimum surface area. Clear? So you have the minimum surface area, so because of which the rain drops, whatever you see in the form of a droplet. Okay. The second, washing clothes with hot water is effective. Correct? Why? Because when you heat the water, like as I told you, the molecular cohesion decreases. Okay. So when cohesion decreases, then water particles will not enter the fine pores of the fabric very easily. Okay. So if you have the cloth fabric like this, okay, so if you have the fabric like this, then if there is some mud particle here, initially water cannot penetrate in because the cohesion forces being strong, the water molecules are held very tight. Okay. But when you mix surfactants and detergents basically, or if you heat water, by some source if you decrease the cohesion, okay, then ultimately water can easily penetrate there and water can go and touch the dirt, so dirt will go off. Okay. That's why liquid detergents are costly than compared to solid detergents, because liquids can get mixed easily, molecular impingement can be easy in case of liquids. Okay. Then Young-Laplace equation, Young-Laplace equation. So if you have a fluid body, ultimately it sets up a differential pressure, and PO minus PI n sigma into 1 by R1 plus 1 by R2. So what are these terminologies? N, number of active interfaces, sigma is the surface tension at the interface, R1, R2 are principal radii of curvature. Principal radii of curvature actually. Okay. So these are principal radii of curvature, and like for example, if you take things like bubbles and all, the radius in one direction and in the perpendicular direction both are same. Okay. So therefore you have, like for bubble, if you have a bubble like this, so let's say this is liquid. Okay. Inside you have air, outside also you have air, then this is one interface and outside you have the second interface. Okay. So n equal to 2, R1 is equal to, let's say if the bubble is of radius r, R2 is also r, because in bubble any two perpendicular directions you take, you will get the same. So P in and PO is 2 sigma 1 by r plus 1 by r, which gives you 4 sigma by r, which is 8 sigma by d. Okay. This is for bubble. So similarly you can write for different objects, because if you have a droplet then only one interface. Okay. If you have a liquid jet, then R2 tends to infinity, you have all these things, so you get this different expressions. Okay. 2 sigma by d, 4 sigma by d, whatever, depending on this equations, this Young-Laplace equation actually. Okay. And obviously one last case is wetting phenomena. So if adhesion is greater, then this implies wetting. Okay. Like if you have a flat surface, okay, and let's say if you put a droplet here on this, then if this drop has to, fine, so let's see, so if this drop has to spread on this surface like this, means if the drop has to wet the surface, then what happens? The molecules here should be attracted more towards the surface than to maintain this. Okay. So that means adhesion would be strong, and the contact angle, if you see contact angle at this point, okay, so you have the contact angle in the wetting case. So this is the contact angle theta, which is this. So you have capillary rise, fall, these things. Okay, where if adhesion is strong, then capillary is important in GATE exam. Generally questions come up. Okay, so capillary rise or fall, and let's say normally for a tube, okay, this is D, and if you have some liquid, you have the meniscus. So if this is H, okay, so H is equal to 4 sigma cos theta by rho f GD. Okay, that's what you have. You do the standard analysis. Basically this analysis comes from weight balance with the surface tension force. Okay, similarly for not only circular pipe, any geometry like between plates, whatever is there, you can do the same analogy. One thing that I just want to tell here, मान लो कि आपने इस फॉर्मूला से कैलकुलेट किया था, and H is, let's say this is H dash out of the tube. Okay, not this, sorry, this is H, and let's say this total length of the tube available is H dash. For H greater than H dash, let's say you calculated using this formula and you got H as some 7 centimeters, but the tube length is only 5 centimeters, which is outside the water. Will the liquid overflow? Yes. बताओ, मान लो कि आपने H कैलकुलेट किया था इस फॉर्मूला से, एंड जो वैल्यू H के लिए आया था, so that is more than this H dash, which is length of the tube outside the water. Then will the liquid overflow because of capillarity? No, correct. So liquid doesn't overflow. क्यों? Because जो capillary raise होए, that is because of the adhesion forces. Okay, and इस point के बाद there is no glass, so no adhesion, no capillary effect. Got it? So these things clear. So with this we conclude the first chapter, pressure and its measurement. I'll give you one question. If you wish to do, you can do. So this is anyway homework or basically practice question, just for practice. Okay, just you do it in your free time, in your tea time somewhere. So we finished the first chapter with this. Clear? I understand काफी lengthy हो गया, but still there are questions which come up very frequently. Okay, on this. And जो analysis मैंने आपको दिखाया था वो last 15 years का था. Fine. So let's move to next chapter, pressure and its measurements. So anything to ask from the first chapter? यहाँ तक सबको क्लियर है या नहीं, बताओ. थोड़ी हिंदी भी बोलियो. ओके फाइन, ठीक है. तो पहला जो चैप्टर हुआ था वो क्लियर है सबको या नहीं? क्लियर? यस, ऑल क्लियर. चलो सेकेंड चैप्टर, कॉन्सेप्ट ऑफ प्रेशर. So second, third, fourth are little small chapters. So intensity of external compressive, normal compressive load. Okay, so if you have an object, for example, then if you have dA, for example here, okay, this is dA, let's say at this point this is dA. Then if you have normal force which is dF, okay, then area in elemental form is a vector. Then P, limit delta A tends to 0, del F by del A. Okay, area in the elemental form is a vector. Clear? Mu of liquids greater than gas. टॉक वाला क्वेश्चन आते हैं क्या? Maybe there's a chance. Mu of liquids greater than gases. Obviously because molecular cohesion is highly dominating than compared to molecular momentum transfer. Okay. Little confusion in dyne. Dyne is nothing but 1 Newton is equal to 10 power 5 dynes. Dyne is the CGS unit of the force. Okay. So this is pressure. So if you see, this pressure is due to direct external load, and this is due to internal resistance. So this is due to internal resistance, of course. Okay. So because many times I have seen in interviews also students say, what is pressure? Force by area. What is stress? Force by area. Then what is the difference? वैसा पूछते हैं, ठीक है. लेकिन स्ट्रेस जो होता है कि वो इंटरनल इफेक्ट है. मान लो कि आपने एक स्पेसिमेन पे किसी स्ट्रेस किसी लोड अप्लाई किया था, देन द इंटरनली द मटेरियल विल ट्राई टू रेसिस्ट द लोड, सो तब स्ट्रेस होगा. ओके, एंड देन pressure is because of the direct external load that you have. Now let's see if this is stress due to internal resistance. So obviously if you look at the stress matrix, you have sigma xx, sigma xy, sigma yx, sigma yy. लगता है कि आप ने ऑलरेडी कॉम्प्लेक्स स्ट्रेसेस पे पढ़ाया था. सो वी हैव दिस सिग्मा xx, सिग्मा xy, sigma yx and sigma yy. Okay, and this is a symmetric tensor. Normally stress is a tensor, of course. So this is symmetric. इसका मतलब यह है कि sigma xy is sigma yx, and if both the subscripts are same, यानी कि sigma xx, sigma yy, these are compressive, these are normal stresses, and sigma xy, sigma yx are shear. If these two are not equal, then it's shear stress, and if they are equal, it's normal stress. Okay, then Pascal's law and hydrostatic law. So पहले Pascal's law देखेंगे. What is Pascal's law? So in a static fluid, P is uniform at all, P is uniform from in all directions, at a given point, So if you have a liquid, for example, okay, so if you have a point, then the pressure is uniform in all the directions. Let's say minus P. P is the magnitude, minus sign denotes it's compressive. Okay, so this is what you have the Pascal's law is. Okay, ये question से test series में बहुत बार पूछता है, correct. So one small doubt here, what is the deviator of stress tensors? I'll tell you. Let me come for the 7th chapter, Navier-Stokes equation, then I'll tell the deviatoric part. Okay, basically it denotes the change in volume. Okay, sorry, the change in shape. Okay, not the volume, the change in shape. So anyway, we'll see. So this is the shear the normal stress. Okay, since the fluid is in static condition, it cannot hold any shear stress. Okay, it can have only normal stress, but that normal stress is uniform in all the directions. Now let's see, if you write the state of stress at a point in static fluid, so this is hydrostatic state of stress. Hydrostatic state of stress, the stress tensor is nothing but minus P, 0, 0, minus P. Because fluid is static, so no shear stress. So these elements are zeros. Off diagonal elements, all of the diagonal elements are zeros. And जो diagonal elements होता है, जो normal stress values, that's minus P. Like you fix any two directions, x, y, for example. Here you have the pressure value minus P. Here also you have minus P in both the directions. So that's why this is the stress. Now for this stressed condition, can someone tell me principal stresses? What are sigma 1, sigma 2 values? Again minus P, correct? Because you apply this sigma xx plus sigma yy by 2 whole square and so on, you will get minus P. Okay, so normally if you look mathematically, these are physically principal stresses and mathematically eigenvalues. Mathematically, maybe I'll write here, principal stresses of a stress tensor are mathematically eigenvalues of sigma. Okay, that's why if you see Mohs circle will be point, yeah, we'll see whether it's a point or not, but in general normally if you have a stress tensor, okay, जो eigenvalues आप calculate कर सकते हैं वो these are exactly the principal stress values. Okay, so sigma 1 sigma 2 is minus p, and maths में मैंने आपको एक चीज पढ़ाया था, like if you have a upper triangular or a lower triangular or a diagonal matrix, then eigenvalues are nothing but the principal diagonal elements, like you see minus p comma minus p are the cases. Okay, and what is the radius? Radius होगा कि 0. Mohs circle. Okay, so if you look at Mohs circle at a point, Mohs circle for the state of stress at a point in static fluid. Is a point. So if you have the axis sigma and tau, okay, then you just have a point here, that's all. Radius equal to 0, and this is obviously minus p. Okay, this length is p, so this point is minus p comma 0, that's all. Fine, which is a very frequent question in exams. So let's see, then you have something like the hydrostatic law. Hydrostatic law. So hydrostatic law क्या होता है? So dp by dz is equal to, or basically dou p by dou z. Let's see, the pressure gradient along the vertical direction is minus density of the fluid times g normally, okay, where z is in the upward direction. Clear? So if z is in the upward direction, then dou p by dou z is equal to minus rho f into g actually, and normally in the vector form you have rho x bar minus del p is equal to 0, and x is body force per unit mass. Body force per unit mass. Okay, and if you have only gravity, for only gravity, this x is minus g times k cap. Okay, that's all. And you know what is gradient, obviously. So you know gradient, you know this vector is x, so clearly rho x minus del p is equal to 0, which gives you, if you just write it, minus g k cap minus gradient of pressure dou p by dou x I dou p by dou y j plus dou p by dou z k is equal to 0. So this tells you in a static fluid there is no pressure gradient in the x direction, no pressure gradient in the y direction. Dou p by dou z plus, okay, there should be density here, multiplication, rho is there, so is equal to minus rho f g. So this equation and this equation is same, so this is the vector form of this, absolute. Okay, anyway, it's a difference. Del p is the pressure difference, so obviously you can take the difference in the gauges or difference in the absolutes, no issues. Okay, so this is what we have. Then let's move forward to measurement of this pressure. Okay, pressure, okay, pressure variation in various media. So if you see incompressible flow field or incompressible fluid, sorry, no flow, it's a static fluid. So in incompressible fluid, can somebody tell the variation with the depth? Can someone tell me what is the variation with depth? If you have an incompressible fluid, means if density is constant, then what is the variation? Linear. Okay, so this is linear. Isothermal compressible fluid. So in case of isothermal compressible fluid, what is the variation? Anyone? Come on, quick. Exponential, correct? So this is non-isothermal compressible fluid. So what is the variation? Power law variation, correct? So this is power law kind of variation. So then you have a lot of things where this pressure calculations can be done. So one of them is manometers, of course. Okay. So firstly, you can, for P absolute greater than P ATM, okay, P absolute is written as P gauge plus P ATM local, correct? And for P absolute less than the local atmospheric pressure, you can say, so P ATM local, P absolute is nothing but P ATM local minus P gauge, right? You might have seen these things, and that's how we calculate the absolute pressures to substitute in any of the formulas to solve the questions. Okay, then so you have a lot of manometers where you have the straight forward manometers. Okay, then after inclined, all this has their own effects. Like inclined tube will give you better accuracy. You know, this inclined tube is based on this principle. See, based on, let's say if I give you two lengths, okay, उसमें से एक है कि 7 centimeters and दूसरा है कि 70 centimeters for example, and you made the measure, but I didn't tell you that this is 7 centimeters and this is 70 centimeters. Okay, मैंने जो random lengths दिया था. Then if you measure the lengths, in which case you will report the value more accurately. Okay, you have two lengths, 7 centimeters and 70 centimeters, but I did not give you these dimensions initially. Okay, then if I ask you to measure what are these dimensions, then in which case you report more accurately? Come on, tell me. In which case you report more accurately? Ultimately in 70 case, correct? Why? Because as a human we do certain errors. Okay, so whatever the difference in measurement you make, that will not make much difference here in this case. Okay, so it's always better to have a larger length to measure. So in such case, मान लो कि आपके पास 0.1, 0.2 है, okay, and it's a static fluid. Now you also have 0.3 here. Now clearly P2 is equal to P3 and this vertical separation is H, for example. Okay, this vertical separation is H, then and this length is L. So let's say this angle is theta, sine theta. Okay, clearly P2 minus P1 is same as P3 minus P1. Why? P2 and P3 are same. It's a static fluid and 2 and 3 are on the same horizontal level. So clearly pressure is same between them. Okay, pressure is same. So since P3 minus P2 is same as P2 minus P1 is same as P3 minus P1, then instead of measuring this H can be written as L into sine theta, right? Is equal to rho f g h, which is rho f g L sine theta. Now you know what is the angle theta. Now comparatively H से ज़्यादा L की वैल्यू, H से comparatively L ज़्यादा होगा, correct? So when you measure L, definitely the accuracy in the measurement increases. Okay, so that's why the inclined tube manometers has come up, and then after the U-tube, basically the differential tube manometers to get the pressure difference, then inverted tube, all these things has come again. Okay, this angle theta generally lies between 30 degrees, something like that. Okay, you should not keep this theta very L. So we have this sensitivity of 1 by sine theta. So sensitivity is basically H by L, so which is 1 by sin theta actually. Okay, so initially what is the scale you have and by what amount you are enhancing this. So H by L gives you the sensitivity factor, and that's equal to 1 by sin theta in this case. Okay, so clearly then you have the inverted tube manometers and all for accuracy. So solve this question, I'll give you some time. Mercury manometer is connected to a large reservoir of water as shown. The ratio of HW by HM. Okay, so this is HW by HM. Manometric fluid is mercury, this is water. To do this, 2.5 minutes. Quick. Kindly teach the advantages and disadvantages of U-tube manometers, inverted tube, differential tube, etc. Where these are most suitable to use. Okay, I'll teach. This question finish कर लो, then I'll teach. अरे कुलदीप साहब भी आ गया. Hello sir. $70, 26.5. But it's 70 times. मुझे लगता है कि 70 नहीं है. Maybe it's possible. चलो. This is HW, HM and HM. Okay. Fine. So let's see. From this manometry, you can see this is the bottommost interface. Okay. This is the level of the water, which is here. Fine. That's the level of the water actually. And this gap is 2 HM and this is fully water. So let's see solution. From manometry, this point is A and this point is B, of course. Okay, so PA should be same as PB, right? And what's PA? So whatever is the pressure at this point and uske साथ this complete water head. So PATM local plus rho water GHW. This should be same as. Now coming to here, there is atmospheric air and this dimension is known to you, but neglecting the air column. So neglecting air column, neglecting air column, that's very small column compared to the other liquids. So PATM local plus, now you have water and this is of 2 times HM actually. Okay, so sorry, here you have HW plus HM. Okay, so HW till this point plus here also you have water, so plus HM is equal to PATM local plus, then you have mercury up to this 2 HM height, so rho Hg G times 2 HM of course. Okay, so this is the equation. So let's solve this. If you have 2 hm, then G also gets cancelled in the other terms. So rho W times HW plus HM is equal to rho Hg times 2 times of HM, and you need HW by HM. So divide this full equation with this HM. HW by HM is equal to 2 times rho Hg by rho W minus 1. Okay, and this is nothing but specific gravity of Mercury, so which is 13.6. So 2 times of 13.6 minus 1, this is 27.2 minus 1, 26.2. That's all. Okay, so HW by HM is 26.2 actually. That's what we have. Clear? It's 26.2. Fantastic. 27.2. You forgot to subtract 1. Akash. Got it? अगर आपने इस 1 भूल गया तो बस इस ये पूरा चीज करने के बाद भी आंसर गलती हो जाएगा. ठीक है? So it should be 26.2. A very straightforward question. So ठीक है. Let's go to next question then. So solve this question. Two ends of a differential manometer are connected at 2 points on a horizontal pipe carrying oil. The manometer shows difference in mercury level of 20 centimeters. Specific gravity of oil and mercury are 0.8 and 13.6. The density of water is 1000 and acceleration due to gravity is 9.81. ये तो पता है. At same 2 points, the difference in pressure. Very simple question, but of course गेट में ऐसा questions भी आते हैं 1-2 marks के लिए. तो चलो solve करो. मैं सिर्फ 2 मिनट देता हूँ. Okay, 2 मिनट. Looks like it's very nice question and easy question, of course. Options जो आया था वो काफी interacting options. B. चलो जब तक आप सॉल्व करते हैं तब तक मैं डायग्राम बनाता हूं इस क्वेश्चन का. सॉल्यूशन. You have a pipe. So then you have 2 points जहां आप मैनोमीटर कनेक्ट किया था. Okay, so you have the manometer. So normally if there is nothing, pressure drops in this sense. So यहाँ जो pressure है वो high and this is low. And you have mercury here, so this is Hg. Okay, and you have oil. Some oil is flowing, so definitely this is oil. Oil. Okay, the manometer shows difference in mercury level of 20 centimeters. So this is 0.2 meters. So this is 20 centimeters, so 0.2 meters. Okay, so then calculate this. So definitely if you, it's a very simple question again. One and point A and point B here. Okay, so PA is equal to PB. So which tells you the pressure at this point 1 and 2 if you take, then P1 plus density of oil into G into 0.2 is equal to P2 plus density of mercury into G into 0.2. That's all. So P1 minus P2 would be density of Hg minus density of oil into G into 0.2. So this would be in pascals. Okay, so if you solve this question, then what do you get? 13.6 and 0.8. So 13,600 minus 800. Okay, into 9.81 into 0.2. So 23247,360. Is it? Density of mercury is 13.6 and oil is 0.8 and the difference is 20 centimeters, which is 0.2 meters. So 13,600 minus 800. So this value into 9.81. So this value into 0.2. So 25113.6 pascals. So this value is equal to 25113.6 pascals. Okay, and normally if you see there is an option 25113.6, but if you see the value is asked in pascals, so this is a straightforward value in pascals. Okay, so C is the correct answer. Obvious, right? So C is the correct answer. Chalo, let's move to the next question quickly. Manometers का question है ये. So this is a good question actually, मतलब थोड़ा सा अच्छा question भी है. चलो solve कर दो इस question को, 3 मिनट देता हूँ. A manometer is made of a tube of uniform bore. Bore मतलब area of cross section. Bore diameter. So this is diameter, and the diameter is such that 0.5 centimeters cross section, with one limb vertical and other limb inclined at 30 degrees to horizontal. Both of the limbs are open to atmosphere. Initially it is partly filled with a manometer liquid of specific gravity 1.25. Now additional volume of 7.5 centimeter cube of water is poured in. So how is oil height 0.2 meters? This manometer deflection is 20. So the deflection between these two is 20. Okay. So whatever is the gauge from here to here of the oil, same will be oil here to here. So this oil gauge and this oil gauge gets cancelled. Okay. Or in fact, if you see this, if you take as x, okay, then यहाँ जो LHS में density of oil G into x, RHS में भी density of oil G into x. So दोनों terms cancel होगा. Clear? Got it? मान लो कि अगर मैंने x height column लिया था, so दोनों sides x density of oil into G into x, दो terms cancel हो जाएगा. So that's why I did not write them. ठीक है? Solve this question. ये काफी अच्छा क्वेश्चन है. मतलब जो मैनोमेटर का कॉन्सेप्ट होता है वो सारा क्लियर होगा इस क्वेश्चन को सॉल्व करने में. जस्ट अ सेकंड, एक पॉपअप आया था. Okay, yeah. So the 48 seconds. 4. Is it? Maybe possible. सिक्स सेंटीमीटर्स. ओके, वन ने बताया कि 4, फनी मोहन 6, बाद में क्या होगा 8, 10, 12. चलो लेट्स सी दिस गॉट डन. सो इनिशियली देयर इज एन इंक्लाइन ट्यूब मैनोमीटर. ठीक है, फाइन. सो दिस इज द मैनोमीटर. सो इनिशियली इसमें लिक्विड है, पार्शियली फिल्ड. ठीक है, सो व्हेन both ends are open to atmosphere or both ends are open to same pressure, then liquid level will be same. ठीक है, so you have some liquid like this. Okay, now what you have done is this area is of 0.5 centimeter square. So जो area of the cross section है इसका, so this is 0.5 centimeters square. तो ठीक है. Okay, and what is the specific gravity of this liquid? Specific gravity Sg of the liquid, ये कितना है? So let's see. Sg of the liquid is 1.25. Okay, so this is 1.25. Fine. Then let's see what you have done. If now an additional volume of 7.5 centimeter cube of water is poured into the inclined tube, so you started pouring 7.5 centimeters cube of liquid water. Now मैं आपसे एक क्वेश्चन पूछना चाहता हूं, मान लो कि एक स्पेसिफिक ग्रेविटी का लिक्विड है and then you started pouring water. Will this interface of liquid and water stay here or will it come down? 0.5 is not dia, 0.5 centimeter square is given, you see, 0.5 centimeter square cross sectional area. Okay, diameter is uniform. Yeah. This will come down. क्यों? क्योंकि left side pressure यहाँ PATME होगा, but here there is a high pressure, so the liquid will push. Correct? So interface आएगा यहाँ तक. So this liquid will now come here. लेकिन एक चीज मैं जानना चाहता हूं, मान लो कि इस डिस्टेंस x है, ठीक है, तो ये कितना होगा? Any one of you? And this angle is theta, of course. If this come down by x, ये कितना होगा? Pipe is of uniform cross section, correct? So अगर पाइप यूनिफॉर्म क्रॉस सेक्शन है तो इफ ड्रॉप इज x, ये कितना होगा? x ऑब्वियसली, करेक्ट? क्यों? ये भी x होगा, बिकॉज वॉट एवर द लिक्विड दैट केम डाउन, द सेम लिक्विड विल ऑक्यूपाई द सेम लेंथ बिकॉज पाइप इज ऑफ यूनिफॉर्म क्रॉस सेक्शन, करेक्ट? x ही होगा ना? क्यों? पाइप यूनिफॉर्म डायमीटर का है, तो जब एक यहां से x डिस्टेंस फ्लूइड डाउन मूव है, then definitely it will also move x on this side. Yes, and you have water here now. बाकी जो स्पेस है यहां, so इसमें water है. So let's say this is some length L, for example. So that's the interface, okay? And this fluid has moved up because of the pressure difference. Now again it got adjusted. So let's see, if you take this line, okay, to apply the static pressure balance, okay? So let's say this is 0.1 and this is 0.2. So from manometry, P1 is equal to P2, okay, and this is A, which is 0.5 centimeters, and this is volume of the liquid poured. So this is volume of water which you poured actually, okay, volume of water. Then what is P1? Now let's see, if this length is x and this is theta, this length कितना होगा? X into sin theta, correct? This length would be x into sin theta, yes, because slant length is x, so then the vertical length, corresponding length, is x sin theta if this angle is theta, okay? So pressure at this point, this is open to atmosphere, so P ATM local plus density of this liquid, okay, so density of liquid, some manometric liquid, so rho m g into x plus x sin theta. So this is the pressure from the left. So what is the pressure from the right? P ATM local plus, if this is L, then the vertical height is L sin theta, correct? So the vertical height at this point is L sin theta, okay? So this is L sin theta. So plus density of water G into L sin theta. This is what you get from the manometry. So again, ये दोनों cancel कर दो. So G also gets cancelled from the remaining terms. So once you cancel this G, you have rho m into x times 1 plus sin theta is equal to rho water into L. L कितना होगा? Tell me. What is the length occupied by the liquid water? Which is nothing but volume of the water, what you add by the area, correct? So V water by area into sin theta. That's all, okay? And you need the amount of liquid rise in the left limb. So x का value चाहिए हमको. So rho W by rho manometric into volume of water by area of cross section into sin theta by 1 plus sin theta. That's all. सब चीज पता है हमको. So let's see. We know theta, we know volume, we know area of cross section, we know these two things. Okay. So density of water is 1000. Density of this liquid, manometric liquid, is specific gravity is 1.25. So 1250. Then volume of water which is added. Volume of water which is added is 7.5 centimeter cube. So this is 7.5 centimeter cube, and area is 0.5. This is dimensionless. This is also dimensionless. So x will be in centimeters. Okay. Then sin theta. What is theta value? So theta is 30. Okay. So inclined at 30 to the horizontal. So if theta is 30, this is half divided by 1 plus half. So 3 by 2. So this is 1 by 3. So 3 in the denominator. So let's see what we can do about this. 1000 into 7.5. So 1000 into 7.5 is 7500 divided by 1250 into 3 into 0.5. 1250 into 3 into 0.5 actually. Okay. So 4 is the actual answer. So 4 centimeters is the rise in the left limb. Got it? Very nice question, right? Conceptually जो अच्छा क्वेश्चन है. ट्रिग्नोमेट्री ये सब मैथमेटिकल फॉर्मूलास यूज करना पड़ेगा. So the rise in the left limb because of pouring water in the right limb is 4 centimeters. Okay. Is this fine to all of you? So all of you just confirm. Is this okay to all? Yes. It's a very good question, right? Just by pouring water on the side, we have the length x. How can we say that the length x goes down in inclined limb is equal to x size in the vertical limb? This complete fluid, sorry, this complete tube is of uniform cross section. Okay. Then if this volume of liquid is coming down, then the same volume has to go up. Okay. Because density is same. Density of liquid here and here is same. Okay. So if densities are same, the volume displaced by the fluid should be same as the volume change in this case, and if the volume change is same, then obviously the length should be same because pipe is of the tube is of uniform cross section. Okay. So then let's see. I'll give you one question which is again a practice question. Okay. So this is an unsolved question in S.K. Somsa's book. So practice question. I'll give the answers for these practice questions towards the end. Okay. No issue. So you have this practice question. So it's a nice manometer. It's a simple question, not very tough question, but you have to do the calculations little carefully. That's all. Okay. So just do them. Where PDF will be given in the Telegram channel. I'll try to upload, or else definitely in the link below the description you'll find it. Okay. Yeah, just balance this between here and here, you'll get the answer. A very straightforward and simple question, nothing to be worried much. So with this we conclude the second chapter. Okay. Fine. So is the first two chapters clear? Any doubts to anyone? Someone has asked me regarding the advantages, right? Yeah, sorry. So if you see, inverted tube manometers has higher accuracy, better accuracy actually. Okay, because again the deflection length will increase, and normally in case of inverted tube manometers, see if you have an inverted tube manometer, which I think I have the diagram here maybe. Yeah. So in this case, let's say if the fluid is flowing in this direction, for example, then this is manometric fluid. So rho manometric, and this is density of the fluid which you have flowing in this pipe, rho f, for example. Okay. So in case of inverted tube manometers, In case of inverted tube manometers, rho m should be less than rho f. Okay, and definitely the difference between rho m and rho f is small in this case. So as a consequence, the measuring length, the deflection जो होता है वो ज़्यादा होगा compared to the normal U-tube manometers. Okay, so that's why normally more sensitive, then right normal U-tube manometers. So better accuracy. Okay, so the accuracy would be better actually in this case. Clear? So this concludes the second chapter actually. So if you have any questions, you can ask me, or else I'll move to the third chapter. The density concept of U-tube and inverted tube is also awesome of yours. Thank you. Okay, so normally the density, the deflection in this case of inverted tube manometers is like 12 to 13 times of normal U-tube manometers. Okay, so that you have better accuracy in measurement. Chalo, hydrostatic forces. Is the first two chapters clear? Everyone, comment in the chat box. If they are clear, then we'll go for the third chapter, hydrostatic forces. All of you, everyone who is in live, type in the chat box. Are things clear till so far? Yes. Good. So let's move on to this hydrostatic forces. Okay. So एक चीज पता चला कि as you move deep inside the fluid, pressure changes. Okay. So if pressure is changing, then what is the force exerted on the surfaces? Okay. So पहले हम plane surface से start करेंगे. So definitely, you know, if you have a plane surface like this, I'll just give the important or the salient points again. Fine. So let's see, you have this area, and let's say you have the free surface of the water somewhere here, maybe. Okay, and this is area A. Fine. Then so मान लो कि आपने एक फोर्स को स्पेसिफाई करना पड़ेगा, तो कितना पैरामीटर स्पेसिफाई करना पड़ेगा? मान लो कि मैं एक फोर्स स्पेसिफाई करना चाहता हूं, सो कितना पैरामीटर स्पेसिफाई करना चाहता हूं मैं उस फोर्स का? 3. करेक्ट. सो वो 3 क्या होता है? पहले होता है कि मैग्नीट्यूड, सो व्हाट इज द मैग्नीट्यूड ऑफ द फोर्स. दूसरा होता है कि डायरेक्शन. ओके, एंड तीसरा होता है कि पॉइंट ऑफ एप्लीकेशन. करेक्ट. सो यू नीड फोर्स, मैग्नीट्यूड, डायरेक्शन एंड पॉइंट ऑफ एप्लीकेशन. सो ये तीनों चीज हम कैलकुलेट करना पड़ेगा. सो कैसे कैलकुलेट कर सकते हैं? देखिए, सो लेट्स से इफ दिस इज द सेंटरॉइड C of this, then if this is at a depth h bar from this free surface, okay, why free surface? क्योंकि जब हम इस एनालिसिस कर सकते हैं उस टाइम पे assumption ये है कि if this is PATM, then liquid is only on one side. Okay, second side is again PATM local. तो इसलिए to maintain this equations and whatever we derive, this should be PATM obviously. So this should be h bar. Okay, so you calculate the hydrostatic force. Fh is nothing but rho f g area, or rho f g h bar times area, and this is of course the pressure at the centroid, gauge pressure at the centroid multiplied with area. Then definitely you know the direction which is normal to the plate, normal to the surface clearly. So this is the direction. So this is F hydrostatic force. Okay, so this is F hydrostatic. Then if you look at the depth which is here, so this would be H star and this is H star, you can see. So if you see, this point will again reflect something like this. Okay, so this point is CP, center of pressure, and the good thing, these two lie on the same vertical line. Okay, so these two lie on the same line that is parallel to the plate actually. Okay, so this is center of pressure, so CP is center of pressure actually. Okay, so this is C, and how do you get this H star? H star is nothing but H bar plus Ixx sin square theta upon A into H bar, correct? So this is how we calculate the things. So obviously Ixx वो axis क्या होता है? This is the axis. Okay, so parallel to this configuration axis, and this is the xx, the moment of inertia is what you have. Okay, so you got the magnitude, you know the direction normal to the plate, and you also know the point of acting of this plate, because if you know this depth H star, then definitely you know this length, so clearly you can understand that it should be just vertically below the centroid and at a horizontal spot which is exactly this. Okay, so that's how you specify this H star, which is the depth of center of pressure. Depth of center of pressure actually here. Okay, and now coming to like the standard geometries like rectangle, triangle, you know the moment of inertia, you can calculate all these things. Yeah, yes or no? तो बताओ, मान लो कि मैंने एक रेक्टेंगल दिया था, सो मोमेंट ऑफ इनर्शिया पता है कि BH⁵12 अबाउट द सेंट्रोइडल एक्सिस, देन यू कैन डू दिस कैलकुलेशन. सही है ना? मान लो कि एक ट्रायंगल दिया मैंने, सो BH⁵36, यू नो द थिंग्स. एक सर्कल दिया मैंने, πd⁴/64, सो सब फॉर्मूलास पता है. नॉर्मली आई डोंट रिमेंबर दिस फॉर्मूलास, सिर्फ रेक्टेंगल का याद होता है मुझे, 2h/3 होता है कि फ्री सरफेस से, बट लेकिन मान लो कि दूसरा किसी और सरफेस है. ओके, सो सर्कल, ट्रायंगल, तो मैं कैलकुलेट कर सकता हूँ, एंड कैलकुलेट करने में इतना दिक्कत नहीं होगा. मैक्सिमम इट टेक्स 1 मिनट टू डू, है ना? सो मान लो कि मैंने एक रेक्टेंगल दिया था एंड आई टोल्ड यू दैट द वर्टेक्स इज टचिंग द फ्री सरफेस, तो हो जाएगा आराम से. फाइन. सो लेट्स सी सम क्वेश्चन इफ वी कैन डू. ओके, ऑल क्वेश्चंस आर फ्रॉम कर्व्ड सरफेसेस, तो ठीक है. देन लेट्स सी कर्व्ड सरफेसेस. सो इन केस ऑफ कर्व्ड सरफेसेस, बेसिकली इफ यू हैव ए कर्व्ड सरफेस, ओके, you have a water level here, then fine, so you have a surface like this. Okay, it's a curved surface. Then if you take dA, then ultimately the force would be acting normally here, so which is F hydrostatic. Okay, so if you take x, y and z directions, okay, x, y and z directions, then F, the hydrostatic force whatever we have, can be written as Fxi Fyj plus Fzk actually here. Okay, then what about Fx? Yeah, you can do per hit, no issues. Okay, but maybe we will not discuss open channel flow in detail. Apart from that, all other things we can discuss. Okay, so you have Fxi cap plus Fyj cap plus Fzk cap. So Fx is nothing but OFG Ax into Hx bar. So what does this quantity gives you actually? Okay, this Ax is projection of curved surface, projection of curved surface onto a plane perpendicular to x axis. And what is Hx bar? Depth of centroid of free surface, depth of centroid of projected area, from free surface, okay. इसका मतलब क्या है? So मान लो कि force in x direction, yeah, of course, okay. So this is force in x direction, which is in this direction. So rho f g ax into hx bar. So which tells you this ax is the projection of this surface onto a plane perpendicular to x-axis, and hx bar is the depth of centroid of that projected area from the free surface, okay. And I'll give you one important point actually here. If you see, normally in general, we deal this Fy to be 0. The reason, if you project the area onto plane perpendicular to y-axis, you will get a very small area, okay. Like for example, let's say you have a gate like this, okay, a curved surface like this, okay, and it is into the board for 5 meters. Let's say into the board it has 5 meters. Now if I define the coordinate system x, y and z, the projection of the curved surface, I have lot of confusion in this, okay. कितने लोगों को इस कॉन्सेप्ट पूरा डिटेल में पढ़ना चाहते हैं? Because there are many cases. If you want, I'll teach, no issues. I just thought of revising, but it's okay. If you have confusions, you can ask me. Anyway, I'll do one thing. जब हम क्वेश्चन सॉल्व करते हैं, जब सारा कंफ्यूजन क्लियर कर सकता हूं, ठीक है? ओके, सिद्धार्थ and Nidhi, whatever the confusions you have, I'll try to clear them when we solve questions, ठीक है? I'll give you some cases also, definitely. So in this case, if you have a curved cylinder, for example, okay, so let's say I put my hand like this, okay, curved cylinder kind of thing. If you project onto y-axis, this is the area what you will get, correct? And generally surface has a very small thickness. This area ay will be almost 0, so that's why Fy will also tend to 0. Clear? So that's why majority of the times you will be focusing on horizontal force and vertical force. That's all. Clear? And Fz, if you calculate, this exactly becomes weight of fluid supported by the surface. Supported by the surface actually. Okay, so normally क्या होता है? When you have this Fz, the area projected perpendicular to z axis, which means the exact projection of this surface onto horizontal plane, correct? Multiplied with depth of centroid is nothing but this height. So z times dA will give you the elemental volume, and when you multiply with density you will get Fz, and G will give you weight. Okay, that's all, weight of the fluid which is supported. I'll give you one point which is helpful to you at this location. Normally जब आप ये एनालिसिस कर सकते हैं, okay, so you have the plate and there is a fluid like this, okay. जब आप ये एनालिसिस कर सकते हैं, यहां जो प्रेशर है कि PATM लोकल, एंड यहां जो प्रेशर है वो भी PATM लोकल, करेक्ट? एंड इसके हिसाब से हमने सारे फॉर्मूलाज डेराइव कर सकते हैं. रो एफ जी ए h bar, where h bar is, when this is PATM, this is also PATM, so this is h bar, correct? This is what we do. But sometimes क्या होता है कि मान लो कि आपके पास प्लेट है and the surface is here, but this is not a free surface. इसका मतलब यह है कि यहां जो प्रेशर है PATM local, but this liquid, normally in case of some pressurized chambers and all, the gates will be subjected to this. So यहाँ जो प्रेशर है वो P1 which is greater than PATM local. Okay, तो तब हम क्या कर सकते हैं? We should develop an excess column of fluid such that you reach PATM again here. Correct? So मान लो कि P1 is greater than PATM local, then if you create a static fluid above this, okay, so if you create a static fluid above this, then as you move up, pressure कम होता है, correct, and finally you touch a point where the pressure is exactly same as PATM local. Yes or no? Physically are you getting the idea? आप जो formulas यहाँ substitute कर रहे हैं वो valid है, validity ये है कि यहाँ PATM and free surface also should be from PATM. But if you have a case where P1 is more than PATM, then in that case we should go for excess fluid column of height h or some height. We'll see how to calculate that height, such that if you go by a sufficient length, your pressure keeps reducing from P1 and eventually you will touch PATM, and here also you have PATM. So this H1, which is here, this H1 is P1 by rho Fg, and to apply that formula you should start measuring your H bar from this point. Okay, so this is your H bar to substitute in this and to calculate H star, all the things. Did you get the idea? Normally in case of closed cylinders and all this happens. So where you have the opening or this edge connected to a higher pressure, so to get this equivalent to this PATM, you will construct a pseudo fluid column. It's called pseudo fluid column normally. So जब तुम ये fluid pseudo fluid column construct करते हैं, then P keeps decreasing and you touch PATM local definitely here. Okay. Y sin theta, which is nothing but H. Okay. Is this idea clear to all of you? If your surface is not at free surface level, then you constructed extra column. Fine. So let's solve one question again based on this idea. So solve this question. A 4 meters long quarter gate. So this is long, 4 meters means this gate has some 4 meters length out of the board and radius 3 meters and of negligible weight, is hinged at this point A. Okay, hinged about its upper point A. So there is a hinge here. Maybe it was not shown. So there is a hinge at this point. Hinged at this point A, as shown in the figure. The gate controls the flow of water over the ledge at B. So there is a ledge at this location B, and this gate controls the water flow about this, where the gate is pressed by a spring. So normally क्या होता है, यहाँ जो water है, so इस gate को tilt करने के लिए कोशिश करते हैं, correct? Because hydrostatic force would be acting somewhere, maybe somewhere at this point, something like this. So this hydrostatic force or the water will try to push the gate, so the spring is maintained to close this gate. Okay, the water level is up to A, so up to this point of the gate, and the spring keeps the gate closed. Which one or more of the following statement is or are correct? The geometry is very simple. It's a 4 meters long gate and you have 3 meters like this radius, and it's controlled by this spring. Okay, then the spring force acting on the gate to keep the gate closed lies between these values. Okay, so there's a difference. The line of action passes through the center of the quarter circular gate at an angle 23.24 degrees, 28.24 degrees. Correct. So solve this question. I'll give you 5 minutes to solve. Solve this question. After 2 minutes, I'll change the options. So first thing, in a nutshell, if you see, what is F spring? That's one point of interest, and theta, angle of resultant hydrostatic force. F hydrostatic. That's all. You calculate these two. I'll display the options in the last 30 seconds. Okay, come on, do this. Maybe I'll display the options so you can figure out. B and C, maybe. B and C. Vishaka Singh is happy. B is correct, okay, but it's MSQ. Okay, all of you are telling B and C. Fine. Do this last 20 seconds. Chalo. So let's see. Solution. So if you have this gate, okay, fine. There's a hinge. So if you draw the free body diagram, you have the hinge reactions Rx, Ry. You have this F spring at this point, okay, and some force. But definitely you know something. मान लो कि ये सर्कुलर गेट है, so definitely any normal to any of this point, okay, आपके पास काफी points है, but the normal to any of this point will definitely pass through radius, correct? Sorry, will pass through the center. Yes or no? Why? Normal to a circle is nothing but a radius. Yes? Can I say this? The normal to the circle is always a radius. सही है ना? Normal is perpendicular to the tangent. Okay, so it's normal. So definitely whatever the point it is, but definitely it will pass to the center. इतना पता है मुझे. ठीक है? Then, so what I can do is, let's see. And this is radius because it's a quarter circle exactly. Can I resolve the force? Right now I don't know what is the force actually. So I am resolving it as Fh and F or Fx, let's say, horizontal force, and Fy, vertical force. Like how जहाँ मुझे hinge का reaction नहीं पता है, so I have decomposed it into, resolved it into two parts, Rx and Ry. वैसा ही Fh भी मुझे पता नहीं है अभी कि कौन सा एंगल पे होता है, so I am resolving it into Fx and Fy. Okay, now under equilibrium, if this gate has to stay where it is, then this is point A and this is point B. Summation of moments about point A, maybe you can take counterclock sense to be positive. This has to be 0, correct? with respect to A, whatever the moments are there, all those moments should definitely cancel out, तब gate static condition में होता है. Yes, can I say this? Definitely I know my resultant force will pass to the center, but I don't know what is the angle as of now, but I know that it definitely passes to the center. So मैंने क्या किया था, मैंने resolve किया fx and fy बस, ठीक है. So let's see, यहाँ पर 5 forces है, rx, ry, fx, fy and f spring. So these are the 5 forces. उस 5 forces में 3 forces are passing to the moment center. So we have only 2 other forces. So fx into the moment arm, so this is also radius, into r minus f spring into r is equal to 0. So this gives you r and this r gets cancelled. So what is fx or f spring is nothing but the horizontal force fx. Okay, and what is the horizontal force? So you project this gate onto a plane perpendicular to x-axis. Okay, so if you see, this is the gate. So if this is the gate actually, and this is the x-axis, it is 4 meters long. Okay, so if you project this onto plane perpendicular to x-axis, can someone tell me what would be the geometry of this projection? तो बता दो मुझे, what would be the geometry of projection onto perpendicular to x-axis? Rectangle, right? So it should be a rectangle. So अगर आपके पास एक rectangle है, then this height is radius and this is length, which is something. What is the length they have given you? The gate is how much long? The gate is 4 meters long. Okay, so it's a 4 meter long gate. So clearly you have 4 meters. Fine, that's the case. So if you have 4 meters long gate, then this is the projected area and this is free surface. Clearly they have given it's a free surface. So the centroid at this point G, so what would be hx bar? Hx bar is 2 meters, sorry, 3 by 2, 1.5 meters. Okay, radius is 3. Okay, or r by 2, whatever. So this is r by 2, you can write for the time being r by 2. Okay, so that's r by 2. So fx, the horizontal force, is nothing but rho f g ax, which is the projected area. So r into 4 into hx bar is r by 2. So f spring is equal to 2 rho f g r square, which could be equal to 2 into, it's a water, so 10 cube, 9.81 into radius square, which is 9. So if you check the options are in kilonewtons. Okay, so in kilonewton, so by deleting this 10 cube, you can write the answer in kilonewton. Okay, so f spring, which is the horizontal force, in kilonewton, 18 times 9.81, so 18 into 9.81, that's all. So 176.58 176.58 kilonewtons. So let's see, 176.58 is where, 176.58 is somewhere here. Okay, so this is wrong, A is wrong and B is correct option in this case. Okay, so B is correct. So it's a very straightforward way just to calculate the fx value. But if you want the resultant angle, you should not apply this h bar is equal to hxx plus I sin theta. You should not do this. Okay, because it's just the projection, it's not the absolute moment. So therefore, to calculate fv, I have another idea. Okay, because we know tan theta is equal to fy by fx. Okay, so but we got fx, but we don't know what is fy, so we should get fy. So how will you get fy? Let's see. You have this gate, okay, you have this circle, whatever, then I want to ask you one small thing. This is point A, this is point B, एंड जो फ्लूइड है वो इस तरफ है, ठीक है, एंड दिस इज ए फ्री सरफेस. कैन आई आस्क यू समथिंग? जब हम फॉर्मूला का एनालिसिस कर रहे हैं उस टाइम पे एक इंपॉर्टेंट एजम्पशन करता है कि whatever is the pressure here, same is the pressure on the other side of the fluid, other side of the plate or the surface actually, ठीक है. Now let's see, in this case the normal force is something like this, but instead of having atmosphere here and fluid this side, if you swap, if you bring air here and fluid to the other side, the force, the point of application, everything would be same except the direction, correct? Yes or no? In this side, the direction of the hydrostatic force is in this way. If there is atmosphere here and fluid here, the direction of the hydrostatic force would be towards down, but the magnitude and the point of application, everything would remain same, exactly the same. Yes? Agreed? Did you all understand this? Too? Now, let's see. So, if I exchange, for example, this Fv, Fy, it's positive because clearly this Fy is positive in this case, but to get the magnitude, what we can do is, let us calculate this weight of the fluid which would have been supported in this case. Okay, so how would you get that? This is R, this is also R. So if fluid would have been on the other side, okay, then weight of this shaded portion of the gate throughout the length. Okay, so Fy, density of water, G into this shaded area. What would be shaded area? Square, which is R square, minus this circle quadrant, pi by 4 R square, into the length of the gate, which is 4 meters. That's all. Okay, so that would be the Fy value, or Fv, whatever, vertical or Fy. Did you all get this idea? You can swap the liquid and atmosphere on either sides, then you will get the magnitude. There won't be any change in the magnitude. So physically, you know, because of the liquid presence on this side, the Fy will be positive, it will be in the upward direction, and the magnitude is just the case when you have fluid on the other side. So I have written this. Is this okay to all of you? It's a conceptually very nice manipulation. सबको समझ में आया या नहीं? Okay, so now obviously you can do the question. So rho W G, radius is 3, so 9 4s are 36 into 1 minus pi by 4. That's all. So this in some kilonewtons you can write kilo by deleting this density of water. You can write this kilo because that's 10 cube. So 1 minus pi by 4, let us save this value. Okay, so 1 minus pi by 4, so this value into 36, so 7.72 whatever, into 9.81, 75.788. That's all. Okay, you have Fx, you have Fy, so you know what is theta now. So tan theta is Fy by Fx. So what is Fy? 75.788 by Fx. So Fx कितना है? Let's see, 176.58. So what is theta? Let's do this in degrees. Okay, so this value 75.788 divided by the previous value, so it should be in degrees, and tan 23.23, so 23.23 degrees is what you have. Okay, so 23.23 degrees is the inclination of the force, resulting force at this point. Okay, so what are the force you have? This theta, so that's 23.23. So 23.2 is here upwards from the horizontal. So C is the correct answer. B and C are the correct answers in this case. Okay, come on guys, it's clear. 23.22, yeah, 23.2 whatever, close. This question gives you a very nice understanding of swapping the fluids, okay, which is a very good thing to do in fact. So if that's clear, then solve this question by your own now. This question, it's again a curved surface, you see, circular segment of radius r. Normally it's called the tenta gate, okay, where if you keep, there's a pivot here actually, so if you keep adjusting the pivot, this curvature means basically these 2 points can come close. Of course this is fixed, this point can come close or move. So you have the options. It's one of the questions similar to 𝐂𝐸_PYQ actually, okay. Something got stuck, just a second. Just a second guys, I think something got stuck actually, not responding. So solve this again. Come on, solve this question. Geometry question. Good. Option A. Of course, depth in the sense like into the plane, okay. Let's see. I'll mark this question, I'll mark this gate at points A, B and C, okay, and you want what is retained against a sluice gate in the form of a circular segment as shown in the figure. If rho and g are density and water and acceleration gravity, the upward force exerted by the gate on the water per unit width perpendicular to the plane of the figure, okay, or per unit depth perpendicular to the plane of the figure, whatever, okay, they have given clearly perpendicular to the plane of the figure. So let's see, I have A, B, C values. So let's see, you have a gate which is something like this, okay, and you have fluid up to here, fine. So this is point A, somewhere here is point B, and somewhere here is point C, okay. Now let's see, let me split this gate into two parts. One is part AB and another is part BC, okay. So this is part BC. If you look at part AB, Fy vertical force on AB is equal to, which is straightforward equal to this amount of fluid, correct? Yes or no? Directly, because you see, if this is the free surface, whatever is the weight of the fluid that is supported by this gate, exactly rho Fg, if I call this area as A1, rho Fg A1 into depth into the plane, which is like per unit depth, I think, right? That's what they have given, per unit depth. So into 1, that's what you would get, and this force acting on the gate is in the downward direction. So Fy on AB, part AB is rho Fg A1, and this is acting in the downward direction. Is this okay to all of you? Correct? The force acting on the gate AB will be towards down because you have the hydrostatic force acting in the downward direction. Okay, clear? It's very straightforward. Then coming to location B, this BC part, if you have this BC part, okay, which is this, and for this BC you have the fluid on the left and atmosphere on the right, okay. So which means, can I say, if I swap atmosphere and fluid, the force acting on BC, can I write this as, ultimately now the force will be in the upward direction, so clearly the force would be in the upward direction, and if I swap this atmosphere and fluid, and this line is not at, like, you'll see, this is BC, okay. So this is B and this is C. So ideally this surface is not at PATM, okay. So if you construct a pseudo column, again from this you will go back to this point, okay. So you have this where it has the free surface. Now if you try to analyze this by taking atmosphere here and fluid here, or if you swap, then the magnitude of the force will be nothing but exactly this area. If you call A2, then rho F G A2 into 1, but that will be acting in the upward direction, correct? Yes, सबको समझ में आया या नहीं बताओ? Rho F G A2 into 1, where A2 is this full area now, okay. Now this part is acting in the upward direction and this part on AB is acting in the downward direction. So F net on gate is equal to FBC minus FAB. So rho F G A2 minus A1, okay. So rho F G into A2 minus A1. So what is A2 minus A1? That's the question now, okay. So rho F into G into A2 minus A1. Look, A1 is this area which I have shaded in blue color, okay. This is A1 which I have shaded in blue. Now what is A2? A2 is something which I will shade in orange. When you do A2 minus A1, this part which is here this part which is here gets cancelled, correct? Because you see there is FH and FV, so it get cancelled, which means you just need this area of the gate. Yes, A2 minus A1 is nothing but the area of this segment ABCA. Yes, so this area is nothing but area of segment ABCA, that's all. ठीक है, सबको समझ में आया या नहीं बताओ जल्दी, so that I can write this area of the segment. So mathematically you figured out what is the area, so then just apply some trigonometry formula and get the answer. So how to get this answer? Let's say 2 times of, because it's symmetric, so F net is equal to rho f g into 2 times of. So how to get this shaded part, this orange part, or maybe this orange part? You see ये नीचे वाला जो orange part है, so इसको कैसे कैलकुलेट करना पड़ेगा? ये वाला, so this can be calculated as a full sector. So this is a full sector minus this triangle area. Okay, so if you see the full sector, this is theta, so theta by 2 pi into pi r square minus, so from this you should subtract, because this is the gate of radius r. Okay, then you should subtract this triangle area. So let's call this triangle as OC and this point is D. So OCD area you have to subtract. So this is r, you know this, and what about this length? If this angle is theta, this is r cos theta. So you have, you know, these two sides and also the angle between them. So half r cos theta into sin theta. That's all. So this is the area actually, because if you know 2, so A2 कैसे लिए वो repeat please. Yeah, definitely above. So if you have this gate, ideally the free surface of the gate, sorry, the surface of this gate is not at PATM, it's at some pressure. Okay, so if you want PATM, you should keep increasing this length. So if you want PATM, you should again go back to this level. So if you exchange fluid and air, then we have this area which is equal to the pressurizing area. So half into, if you have a triangle like this, okay, if this is A, if this is B, and if this angle is C, then half AB sin C is the area. So in this triangle, you know, this side r cos theta, and angle between them is theta, so half into r cos theta and sine of angle between them, so which is this value. So if you simplify, this pi and pi gets cancelled, then this 2 can cancel up in all the terms. So you have rho f g into, if you take r square common from both the terms, theta minus sine 2 theta by 2, that's all. Okay, so this would be the net force acting on the gate, so which is rho f g r square theta minus sine 2 theta by 2. So theta minus sine 2 theta by 2 is here. Option A is the correct answer. Okay, a very straight questions, but needs lot of understanding in understanding the hydrostatic forces. Okay, clear to all of you? Yes, it's in fact a question in XE. Okay, chalo, let's move. Then okay, we have one more question which I'll solve tomorrow maybe, because we have the Abhyas session again. So let's go for kinematics. One last part, okay? Let it get done. Buoyancy and flotation, then we can go for differential analysis. Okay? So Archimedes principle. Is the 3 chapters clear to all? Any doubt at any point? So please tell me if you have any doubt at any point, please let me know, I'll clarify. Naito, we'll start this 4th chapter. Kinematics का सबको इंतजार है सर, ठीक है? चलिए, सिर्फ एक ही चैप्टर है ना, ये भी छोटा चैप्टर है, मैक्सिमम इट टेक्स सम हाफ एन आवर, ठीक है. उसके बाद विल स्टार्ट व्हाट ऑल यू आर वेटिंग फॉर. इवन आई लव दैट, ओके, क्योंकि काफी सारा मैथ्स होता है, फटाफट करके जाता हूँ, है ना. पहले 4 चैप्टर्स में बहुत काफी ज्यादा एक्सप्लेनेशन देना पड़ेगा, ओके, बट लेकिन 5th चैप्टर से क्या होता है, काफी मैथमेटिकल चीज होता है, तो फट फट फट. चलिए, सो लेट्स सी आर्किमिडीज प्रिंसिपल. तो यह क्या बोलते हैं आर्किमिडीज हमको, इफ यू हैव ए फ्लूइड, okay, and if there is some body inside this or maybe some volume which is submerged, so this is submerged volume, then सबको पता है कि the buoyancy force acting would be rho f g volume submerged, correct. So whatever is the volume that is displaced by the fluid. Now let's see, if you have this rho f g v submerged, then the point of action, you got the magnitude, so this is magnitude, okay. Point of action is nothing but centroid of the displaced volume, good, of the displaced volume, ठीक है. So centroid of the displaced volume. Now, what is the direction of this buoyancy force? Come on, type in the chat box. Direction of buoyancy. Area of triangle कैसे लिया, नहीं समझा. देखो, we have r cos theta, you have r, and this angle is theta. So half into two sides, any two sides, into sine of angle between those two sides. So angle between these two sides is theta, so sine theta, ऐसा, ठीक है. Fine, that's how I have taken the area, ठीक है. वो sorry, Chikomono, nice name. In this upwards but not always up, yeah, basically if you see the direction of buoyancy, this is normal to lines of constant pressure, constant pressure. And जब fluid static होता है, then line of constant pressure will be horizontal, so buoyancy is vertical, but buoyancy force need not always be vertical. So जब तक lines of constant pressure horizontal होता है, तब तक this buoyancy force vertical होता है, ठीक है. But normally if the lines of constant pressure are inclined, which we will see later in the your lovable kinematics, we will see that. So then in such cases you will see the buoyancy will be at an inclination, clear, okay. In case of static fluid, the lines of constant pressure are horizontal, so normal to that will be vertical, clear. So that's how, again, for the buoyancy force, you know, magnitude, point of application and direction, you have the complete information again, okay. Then let's see standard applications of buoyancy, you know, ice floating on water, all this stuff. On water, okay. Then some solid objects being suspended at interface, so all these are standard applications of this, okay. Now let's see if these are the standard applications. I would like to give, before I go for the conditions for stability and all, we'll see, but I want you to answer this question, okay. The figure shows the 3 glasses P, Q, R with water and floating ice cube. Glass P has a solid ice cube, glass Q has an ice cube with a small solid steel ball inside it, embedded in it, and glass R has a ice cube with an air bubble. So this is an air bubble, of course, okay. After the ice cube melts, the level of water in glasses P, Q and R respectively, come on, don't do probability, okay. I am much better than you in doing probability, but do some fluid mechanics and answer, okay. After the ice cube melts, okay, that's what it's hiding. So do this. No probability, okay? You should do. Yeah. Remains same. Increases, decreases. Okay, a lot of people want to say A. Okay. Is it if some of you are telling A, then everyone is telling A? Optics, Langu. See. D. तो B भी बताओ ना किसी ने. A B C D चारों कवर होगा. आकाश D. ऑप्शन D पक्का कॉन्फिडेंट है लोग. Increases, decreases. Nobody told B, no? Yeah, A, C, D got covered. Somebody say B also, no? It will be done. We'll enjoy then. कोई नहीं बोलना चाहिए तो ठीक है. चलो. Anyway, let's see. First, this is a very simple case. So this is wrong. Why? Because everybody know if you have an ice cube, then if you melt it, okay sir, for your sake, thank you. Even want to say B for my sake. Good. So let's see. Everybody know that if ice cube melts, there is no change in water. Do anyone know why? Do anyone want to know why it should happen? किसी को पता चलना है क्या? Like क्यों? अगर this ice cube melts, then water level will not change. Same density. नहीं यार, ice और water का density अलग है ना. Do all know or do someone need clarification? Why? If you melt ice, water level remains the same. ठीक है? So if nobody knows, then if nobody want to know, then it's fine. I'm happy. So चलो, let's see. Case 1. If an ice block melting on water, if an ice block melting on water, if an ice block melts on water, the water level doesn't change. The water level doesn't change. Correct? Volume of water formed is equal to volume submerged. Exactly. Okay. So anyway, what is this meaning of sticker? Nidhi has put a sticker. Okay. Tired maybe. Chalo. Let's see. Case 2. If any solid or liquid inclusion is present in ice, then density of this inclusion of density rho inclusion, okay, so rho inclusion is present in ice, then 1, if rho inclusion greater than density of water, then water level decreases. If density of inclusion is less than, then water level increases. Do anybody want to know this? Okay, this you told you don't want to know. Good, I'm happy. This anyone want to know why? No, this also known. Good, then my life is easy. Okay, people want to know now. Good. Okay, take care. Okay, fine, I'll teach you. See, normally, okay, I'll spend some time on this. If you have water, okay, and if you have some ice cube, whatever, and let's say there is some inclusion in this, okay, this is inclusion, then this fellow is ice and water. Water, okay, so water, ice, inclusion. Now initially, let's say V submerged initially is some volume submerged, so mass of ice plus mass of this inclusion into G is supported by density of water G into volume submerged, correct? So in that case, what is the volume that's displaced by this ice plus inclusion DO? Mass of ice divided by density of water plus mass of inclusion divided by density of water, correct? This is the volume which is occupied. जो volume ice or this inclusion occupy कर सकता है, that's equal to this, okay? Equation 1. Second part, after melting, okay, so after melting, volume of this ice equivalent water plus volume occupied by the inclusion. So let's see, once this melts, then what happens? This inclusion will come and settle somewhere, okay, inside the water. Then this volume occupied by ice equivalent water is same as mass of newly formed water by density of water plus. Now when this ice cube melt and inclusion come and settle down, then mass of inclusion by density of inclusion is the volume which is occupied. Yes or no? Let's say if I have a steel ball, for example, okay, this steel and there is some liquid in some container, then if this ice melts, the steel ball will come and settle somewhere in the bottom. Yes or no? 2. Yes or no? मान लो कि आइस मेल्ट हो गया, तो तब जो स्टील बॉल है वो स्टील बॉल सेटल होगा ना. So if ball is settling, then what is the volume occupied by the ball then? This, okay. So this mass of newly formed water is same as mass of ice, correct? Which means in the second stage the volume occupied is equal to m ice by density of water plus m inclusion by density of inclusion. Actually, equation 2. In this case, this is the volume occupied by this DO. In this case, the volume occupied by this DO is this. If you compare these two, in which case the volume is high? First case or second case? Sorry. First case or second case the volume is high? Any one of you? Out of the DO, in which case the volume is high? So let's say, for example, density of inclusion. Okay, so let's say for density of inclusion is greater than density of water. Okay, density of inclusion is greater than density of water. First case it is high, correct? Depend on O inclusion, and I have given O inclusion for example. Okay, you have rho inclusion greater than this OW. Okay, now in this case, so ultimately this implies volume occupied is, if rho inclusion is high, then this term would be low compared to this, so is less than V submerged. What does this tell you? Normally have these questions, no, in your schooling. You know, there's a boat, inside the boat there are some wooden sticks, one fellow simply putting that wood into water, what happens to the water level in the river? These kind of questions we used to mug up a lot. Okay, so but if you see, volume occupied in the second case is less than volume which is displaced by the this ice and metal DO in the first combination, okay, before the melting. So after melting, if they are occupying a less volume, what happens to the water level? Okay, after melting, this DO has DO, okay, means ice plus this inclusion, whatever we have, they are occupying lesser volume than previous submerged volumes. Then what should happen to the water level? It will fall. Okay, okay, because steel has high density. Then clear? Fine. Did you all understand the logic behind it? It's a very conceptually crystal clear thing if you learn properly. Many times in schools I have seen this. See, this is not a very big concept that cannot be understood by a 11th class or 12th class kid. Okay, but many times I have seen people ask them to mug up. Okay, there are some, in one question they'll give boats wood in the boat. So if you throw wood is lighter than water, so water level will increase. Okay, then in the second case they give you bricks. Brick is heavier than water, so if you put bricks, the water level decrease. All these questions are there. Okay, so clearly you can see. Guys, something is happening, just a second. Okay, yeah, nothing is happening, everything is fine. So in the initial case, this is the volume which is displaced by this ice and steel ball combination. Okay, after melting, this is the volume which is occupied by the ice and again the ice equivalent water and the steel ball combination. Okay, so compared to this volume is less if density of inclusion is more. Okay, so after melting, if the combination is occupying less volume, then definitely initially some volume which is occupied by this ice and steel is now not occupied, so water will come into that volume which is not occupied, so as a whole the water level will come down. Okay, fine. So as a whole the water level will come down. Now similarly, if you have air, this is a very straightforward thing. You have a air bubble, so once this melts, this air bubble will escape outside. Okay, understood? Like how here this steel ball after melting it came and occupied some volume, little volume. Similarly here also this, once this ice cube melts, this air bubble means the volume which is occupied corresponding to the bubble, that volume will not be occupied now because the air bubble will go up. Okay, it will just go away, so the water level will again decrease in this case. Got it? Initially whatever the volume change, displaced because of the presence of the air bubble, now that volume won't be occupied by any substance. Okay, because that bubble will escape once the ice melts. Clear? So that's how you have remains same, decreases and decreases again. This question was asked in aerospace in 2018-19 somewhere. They have asked this, or 20 I think. I don't remember the exact year, but it's a aerospace question, PYQ. See how much concept is there. How many of you enjoyed this question? Tell me. कितने लोगों को मजा आया था इस क्वेश्चन सॉल्व करने में? करेक्ट, काफी कॉन्सेप्चुअल है ना? इंटरेस्टिंग क्वेश्चन, रियली एंजॉयड. Yes. Good. So then fine. So let's go to the case of stability of submerged bodies. For a submerged body to be stable, okay, so for a submerged body to be stable, बस सेकंड में कंफ्यूजन था. हाँ करेक्ट. डाउट इज देयर. या सी अगर आपको कुछ डाउट्स है तो इमीडिएटली आप पूछ लीजिए चैट बॉक्स में. ठीक है फाइन. So let's see, for a submerged body to be stable, then G lies below B, correct? So G is centered of the body, and B is center of buoyancy. B is center of buoyancy. Okay. So anyway, I hope you know this again. So if you have a body, generally if it's submerged, then you make the body bottom heavy like this, so that in the initial stage this buoyancy and weight, they lie along the same line of action, but when you give a small disturbance, okay, when you give a small disturbance, so then the buoyancy force will be acting here and the weight will be acting somewhere here. Okay, so that's what. And if you see the line of action of these two, there is a slight difference, eccentricity. So the couple is, since if this has to be in stable condition, okay, buoyancy should be always equal to weight, Fb into E gives the restoring couple back. If volume occupied by air escaped, then it will be less than the volume of submerged as first case, obviously. So that's why the water level is decreasing, no, finally there also. See, initially because of the presence of the air has some mass density, okay, so definitely that will also contribute for the volume displacement in the initial stage. Now once this ice cube melt, this air will no more occupy space inside the liquid, it will fly away, okay. So which means initially whatever the volume that's displaced because of the air molecule, now that will be occupied by the water which is inside the container. So as a result, the full water level come down, okay, that's all. Then stability of floating bodies, we all know what is metacenter. So metacenter, obviously this is instantaneous center of rotation of the body, okay. So this is instantaneous center of rotation of the body, and I hope it's clear. Siddhant, yeah, it's okay now, I hope it's clear. So chalo, metacenter, instantaneous center of rotation of the body. Now in this case, this is point of intersection of line of action of buoyancy force with axis of rotation, with axis of the body, you can say with axis of the body actually. So with axis of the body, and normally if you see the condition, we have G B, sorry, yeah, it's this better, this is B, center of buoyancy, sorry, B, then G, and here it is M, let's say metacenter, okay. Then this BM is called metacentric radius, because obviously this is the center of rotation, and your FB, which is acting here, is responsible for the stability. So FB into this length, whatever that B to M you have, is the radius of rotation, obviously. Okay, MGB Mahatma Gandhi baniye first table, is it good? Okay. So then you have GM, which is the metacentric height. Okay, and for stability, of floating bodies, M lies above G actually. Okay, so this is the condition, and this implies your GM should be positive. So this is for stable equilibrium. So how do you calculate the metacentric radius? Again, I'm not deriving right now, but I'll show you. This BM is nothing but I moment of inertia about the YY axis by volume submerged. So what is this YY axis? That's the important question now. Okay, so if you see, slogan by Sandeep sir. अच्छा ठीक है, संदीप साहब बोला क्या, महात्मा गांधी बनाओ, बनिए for stable equilibrium. Good. ठीक है. So let's see, if an object is floating like this, ठीक है, the water level is up to here, maybe ship or whatever, you have some object, so which is floating like this. Then if you make a cut, so ultimately you have the buoyancy force depending upon the centroid, and you have the weight maybe somewhere here. So let's say you have some weight which is acting like this. Okay, so FB is equal to W, because body should float definitely. Condition for floating. Okay, condition for floating. Now if you have this condition for floating, okay, then if you make a cut exactly at the water line, this is called water line. Okay, so this is water line. So अगर आपने यहाँ एक कट मारा तो let's see, fine. So if you make a cut at this section, definitely you'll see some cross section there, correct? So you will see the cross section at that point. So this line of action about this. Okay, so if you see the centroidal axis, this is centroid of this. Okay, so if you have that as centroid, clear? So if this is a centroid, then if you make a cut at this point and the top view of the cut surface, okay, and this is the line, then this axis is nothing but YY axis. Y, and this is volume submerged, you know this. Okay, so this is volume submerged. So BM is given by IYY about this axis of this cut surface by volume submerged. काफी टाइम लोग ने एक मिस्टेक कर सकते हैं यहाँ. नॉर्मली अगर आपकी सॉलिड रेक्टेंगुलर या लेकिन स्क्वायर टाइप सॉलिड है तो कोई दिक्कत नहीं है. क्यों? यहाँ जो क्रॉस सेक्शन दिखते हैं ऊपर से सेम क्रॉस सेक्शन होगा यहाँ वाटर लाइन पे भी. बट मान लो कि आपको कोन दिया था, ठीक है. सो इफ यू हैव ए कोन लाइक दिस and let's see if this cone is floating about this line, then the cross section at this point and the cross section here is not same, correct? बट मान लो कि आपके पास एक रेक्टेंगुलर प्रिज्म, एक वुडन रेक्टेंगुलर लॉग ऐसे चीज दिया तो ठीक है. बट इन दिस केस you see the top cross section and the water line cut cross section are not same, correct? Now can you all understand this? Yes or no? So that's why it's very important that you should make a cut at the water line and take the momentum the moment of inertia about that axis for this cut surface IYY actually. Okay. So then obviously B and G are just geometrical concepts, so we can do. So tell me one thing, for a cone if you have a cone like this, okay, I just want to ask you something. If you have a cone like this, ठीक है, and मान लो कि सेंटर्ड यहाँ है G, this total height is H. ये कितना होगा from the base? Any idea? The height of the centroid of the cone from the base कितना होगा ये? H by 3, 3 by 2. मैंने दिया कि ये पूरा height H है, height of the cone. Then centroid of the cone will be at what height from the base? H by 3 actually wrong answer है, ठीक है. So this is H by 4. ट्रायंगल में H by 3 होता है, बट लेकिन कोन में H by 4 होता है, ठीक है. Fine. Is this clear to all of you? You'll have H by 3 only in case of triangle, not in case of cone. Cone में H by 4 होता है. Fine. Normally you can do this. It's a very simple thing. Hardly takes 2-3 steps to show that the cone has H by 4. Centered at a location of H by 4 from the base, or maybe 3H by 4 from the vertex. Actually, okay. So just write. It's a very simple thing. Then let's solve some questions again to understand this. So solve this question. I'll give time again. A wooden cylinder of specific gravity 0.6 of length L and diameter D floats in water. Find out the minimum value of D by L for which the cylinder floats with its axis vertical, okay, in stable equilibrium. 3 minutes. Come on, start. Okay, done. So 2.5 to 2.5. Okay, let's check solution. A wooden cylinder of specific gravity 0.6 and of length L. So what is the specific gravity? It's 0.6. Okay, diameter D and length L, floats in water of density 1000 kg per meter cube. So you have a cylinder which is very clear in this, and you have some water line up to this point, let's say. Okay, so this is water. So which means if you take the projection of that surface at the water cut, fine, so you will get a cross section like this, which is rectangular cross section again. Okay, so first let's see what is this height h. Okay, this is of diameter D, it's a cylinder, fine. Okay, so it's a cylinder, then okay, it's a cylinder, so the cut would be a circle. So this is a circle, sorry, yeah, it should be a circle. Okay, because it's a cylinder, so if you cut, it should be a circle. Then this is diameter D, length L, and some submerged volume of H. So first, for floating of the cylinder, density of this cylinder into G into volume, which is pi by 4 d square L, should be equal to, then buoyancy, density of water G pi by 4 d square into H, correct? This is what you have. So weight is balanced by this buoyancy. H is 0.6, sorry, H is 0.6. Okay, maybe let's see, we'll work out. So G and G gets cancelled, this pi by 4 d square, pi by 4 d square also cancels. H is equal to specific gravity of the cylinder, which is equal to 0.6. Good. Then how do you calculate this metacentric height? Okay, because first stable equilibrium, metacentric height should be positive. So let's say G is maybe somewhere here, B somewhere here, and M maybe somewhere here. Okay, so let's say M, G, B, Mahatma Gandhi bani hai, theek hai? So then if H is equal to specific gravity of the cylinder, for stable equilibrium, Gm is Bm minus Bg. So what about Bm? Let's see, Iyy by volume submerged minus Bg. So this should be greater than or equal to 0. Okay, so which tells you Iyy. So Yy is basically this axis, yahi hai. So this axis is a Yy axis. So if this is Yy, pi by 64 d power 4 is the moment of inertia. So pi by 64 d power 4 by volume submerged pi by 4 d square into H. This is volume submerged minus Bg. So this should be greater than or equal to Bg. So what should be Bg value? Look, if this is the height of submersion, this B from the base is at a height of H by 2. Okay, and if this is centroid, then from the base it's again L by 2. So clearly the difference between B and G is L by 2 minus H by 2. So which is half times of L minus H. इस क्वेश्चन में यहां तक सबको क्लियर है या नहीं? If this is done, then it's just a matter of simplification, that's all. ठीक है? But is it okay to all of you till this point? Yes? 1.38, 0.3, we'll see. But is this okay to all? This should be greater than or equal to 0. So definitely the first term should be more than or equal to the second term, that's all. Okay? So now if we simplify this, d square, pi by 4, this becomes 16 actually. Okay, so d square by 16 times H should be greater than or equal to half times of L minus H actually here. Okay, Now you need D by L, correct? What minimum ratio of D by L should be there? So guys, just a second. This L should also be there here, okay? 0.6 times L, that's what I was thinking, because H can't be dimensionless, no? So this is cylinder into L, because this L is still left. So 0.6 times L is the value which is here. Yeah, 0.6 into L should be there. 0.6 into L. So if you solve this, then H is 0.6 into L, and if you bring this L here, D square by 16 times L square, or H is 0.6 times L should be greater than or equal to half into L minus H clearly. So this 2 can cancel this 0.3 times maybe. So if you bring one more L common, so D square by L square should be greater than or equal to 16 into 0.3, 4.8 into 1 minus H by L, and this 1 minus H by L is 0.4, because you see H by L is 0.6, okay? So you see here H by L is 0.6, so this value is 1 minus 0.6, which is 0.4. So D by L should be greater than or equal to square root of 4.8 times 0.4, that's all. So 4.8 times 0.4 and square root of this 1.385. That's the ratio of D by L such that the cone will, this cylinder will float in equilibrium, stable equilibrium actually. Okay, so 1.385 is the actual answer. Got it? So 1.385 should be the round off to 3 decimal places. So 1.385. What's the fourth decimal? 6. So 1.386 maybe. Okay, that's all. Clear? It's a simple concept, but you should be thorough with the application. That's all. Okay. So then let's go to one more question. Maybe we can do one more question actually. So solve this question. After this, we'll start your lovable topic. So rectangular boat 6 meters wide and 15 meters long, dimension perpendicular to the plane of the figure, has a dot of 2 meters. The side view of the boat is as shown in the figure. The center of gravity of the boat is at free surface. The metacentric height of the boat is dash. Come on, do this. Dinner? Okay, fine. So anyway, solve this question. We'll decide then. So someone said, can you confirm IXX? I mean, can you confirm IXX? That's a different story, but actually the IYY is this. Okay, normally during the derivation also we'll get this moment of inertia. The minimum IXX is for something different, which I'll show you. Okay, so solve this question. Maybe I'll give you some 2 minutes of time. Metacentric, we'll see what is that. Okay, normally there is something called, some concept called stability of ships, which right now okay fine, I'll cover, no issue. We'll see something called the concept of radius of gyration, all these things. Okay. B maybe, let's see. So this is 2. meters and this is 6 meters. So then when you make a cut at the water line, so what is the length? So if you cut at this section, then you will see length of the boat will be generally big. So this is 6, and what about this length? This is 15 meters. Is it? That's what they have given you. 15, no? So 15 meters long, correct. Dimension perpendicular to the plane. Good. The center of gravity of the boat is at the free surface level. So this is G. It's at free surface level. The metacentric height of the boat in meters is dash. Okay. So boat in meters is, let's see. So let's try to solve this question. So if you have 15, then the moment of inertia would be something like this here. Why? Now you have the depth as 6. Okay. So GM has to be greater than or equal to 0 clearly, and if you want to calculate GM, metacentric height GM is equal to G is at this point, then B is somewhere here, M is somewhere here. Okay. So BG, so what is BG actually? So this is like a rectangle, so B would be at 1 meter height. Okay. So this is 1 meter clearly, because that's the center of buoyancy of the submerged part, so half of the draft. So 1 meter, and G is here, so BG is 1, BM minus BG, and clearly you figured out this is 1 meter. Okay. Then BM, so how do you calculate this BM? Let's see. IYY by volume submerged. Okay. And what is IYY? This is a rectangle, clearly this depth is 6 and breadth is 15, and you are taking moment of inertia about this axis. Okay. So 15 times 6 cube by 12 into volume submerged is 2 into 6 into 15 deep inside. Okay. That's all. So if you simplify this, 15 and 15 gets cancelled, then 6 will cancel this 36 times, then 12 table, 6 can cancel this 2 times, 6 can cancel this 6 times. Okay. Or basically 3 table directly. So 1.5 meters. So BM is 1.5 meters. So therefore GM is 1.5 minus 1, which is 0.5 meters. That's all. Okay. So 0.5 is the correct answer. Good. Okay. Yeah. So 0.5 meters is the metacentric height. Now since some of you are asking, so before I move on to this, I just spent 5 minutes on why minimum area is important. Okay. Normally if you look at stability of ships, there is one beautiful concept called stability of ships. Okay. So normally if you take ships, the ship length is very large generally. Okay. So something like this. Okay. So something like this if you are watching it from the top view. Then if you take the axis, okay, then any oscillation about this axis is called pitching. Okay. And any oscillation about this axis is called rolling. Okay. So pitching is okay because many times you might have seen in oceans and all, ships go by very high amplitude pitching. Okay. Which is okay. Okay. If you take a small area here, for example, this is dA. If you call this O, X and Y, integral y square sorry, x square dA is nothing but Iyy in this case, correct? Or Ioy, whatever. Fine. Ioy. Moment of inertia about this axis, where there is x here and there is y here in this case. Okay. Now, moment of inertia leads to the physical significance of moment of inertia is resistance to the rotation, correct? So this is resistance to rotation. Okay. Now, if you compare this quantity and if you with this, can someone tell me where this is x and this is y? Which would be, what would be the sign in between? Greater than, less than, something? Greater than, less than, something, some idea? What should be the signature in between these two? Looking at this diagram. It should be less, correct? So because at any given point, this value of x all over compared to the length of the ship, that would be lesser. So which means moment of inertia about this axis, so x square dA is Ioy is less compared to Iox. Okay, which tells you that if this moment of inertia is high, okay, this moment of inertia Iox, okay, y square dA is high, then even the ship is trying to tilt, there is no much effect on the ship. But since this is minimum, when some external wave come and hit, okay, this resistance is low, so ship easily gets tilted, it won't come back. Got it? Can you all understand this? When the moment of inertia about this axis Ioy is less, when some external disturbance come and hit the ship, then definitely it will offer very least resistance to the rotation, so it tilts basically. And that's why all the failures you will see are the rolling failures generally. Pitching happens very rarely, but rolling failures are the major failures. Okay, where ship gets tilted by some amount and it won't come back. Okay, because once it tilted, it doesn't have any resistance to the rotation. Of course it has, but very small, so it's difficult to bring back the ship to its original form. Okay, and normally the time period of oscillation about this, okay, if the ship is rolling with small amplitudes, we have simple harmonic motion. Okay, so theta double dot plus W by GM into what is this expression, theta double dot plus W into T is equal to 2 pi root I by W into GM. Okay, so this is what you have. So therefore omega T equal to 2 pi by omega, so omega square is W into GM by I, correct? Okay, so this gives you theta double dot plus W GM by I, moment of inertia theta is equal to 0. So this is the simple harmonic motion with which the ship rolls. Okay, yeah, that's why we'll design the for safety with respect to the rolling axis, not with respect to the pitching axis. Got it? So theta double dot plus W into GM by I is equal to 0. I is the moment of inertia about the center of rotation, so this I can be written as mk square, radius of gyration, all these concepts can come. Okay, but anyway, there are no questions on this, but this I have heard that people in L&T interviews, they will ask on this. Okay, so you should be careful. Okay, so fine. In this diagram, XX is pitching. Yes, correct. Okay, okay, the thing which all of you waited for. Just a second. Yeah, you want some break? This chat box every time it closes. So So you want some break now? It's been 4 hours. So okay, then fine. Go and have lunch. At what time shall we meet again? 9 o'clock. It's 8:38. So 22 minutes. Okay. I'm not as very strict as an army person, but 22 minutes. Okay. Fine. So come back, then have some dinner, come back, and then we will talk some nice things about differential analysis, all these things. Okay. 9 o'clock. Chalo. So class. Okay. So once you come back, we'll start some maths. Your favorite topic. Okay. Hello. Bye. Have dinner and come back. We'll continue the session at 9 o'clock. Okay. Good. Okay. Come back at 9 then. So welcome back. Welcome back, students. So shall we continue? I think some charts are going down. Excuse me. Yeah. Okay. Ready? Good evening, everyone. So fine. So let's start the session then. So differential analysis of fluid system. So the name itself tells you when you have a flow, okay, then to understand this flow, what we do is we pick a small element, okay, and we try to analyze what's happening with that element. Okay, so since you are picking a small differential element to analyze this complete flow, so जो analysis मैं इस chapter में कर सकता हूँ, so उसको हम differential analysis of the fluid systems करेंगे. ठीक है, and to analyze the flow, there are two important approaches which one can obtain. Okay, so Lagrangian approach and the Eulerian approach. So what is Lagrangian? This is particle based approach actually, and Eulerian is basically the position based approach. Position based approach. Okay, so how do we do the particle based approach actually? So if you have the fluid column, okay, so if you have this fluid which is flowing, then you spot a particle, okay, so you spot this particle x0 at some location t and then follow this particle, okay, so that's one way. But in case of fluid mechanics, first thing, you have large number of particles, and also secondly, this particle's movement is continuous, okay, whereas in case of solid mechanics, what happens, the particles will definitely deform, but they have some finite deformations, but whereas in this case they have very long, very infinitely they keep deforming. So therefore in fluid mechanics, majority of the times we go for position based approach. Okay, so what is position based approach? You fix a point here and then you observe the particles, different particles which are coming to that location actually. Okay, so here you have the coordinates which is x0, y0, z0, and with time t you will keep, so here this is x0, y0, z0, and with time t you will observe what's happening actually. Okay, so Eulerian approach is like you fix a location and then observe all the particles which are causing that particular position. Okay, whereas in case of Lagrangian approach you follow the particles. Okay, we can also say space based, right? Yeah, basically this is position, and position is given by coordinates in space. Okay, so these are the two approaches. In fact, this is one of my ISO interview question. Okay, they've asked me what is the difference between Lagrangian and Eulerian approach. Okay, so definitely you know one is particle based and the other is position based approaches. Then let's see the concept of total derivative, or it's also called as material derivative. When you apply it for materials, this is material derivative. Then generally, you know, if you have a function, okay, so in general, if you have a function which is and so on xn, okay, so it's depending on n variables in general. back mein sir, nahi bhai, back have resigned long back. Okay, when are you joining? So let me decide. Okay, then chalo, if you have a function which is sum of n variables, then if you want to differentiate this function, df is nothing but summation I equal to 1 to n dou f by dou xi into dxi. Correct? You know this. Like normally this is called the chain rule of differentiation. Okay, so this is called chain rule of differentiation. Clear? So if you have chain rule of differentiation, okay, क्वेश्चन किसमें पूछा था सर आपको ये BRC के ISO? I cleared both actually, but I did not get your question. क्वेश्चन किसमें पूछता सर आपको ये? अच्छा, this question was asked to me in ISRO. Okay, so anyway, this is the chain rule. So basically all of you might have seen this. Like for example, df is equal to dou f1 or dou f by dou x1 into change in first variable plus dou f by dou x2 into dx2 and so on, dou f by dou xn into dxn actually here. Correct? This is how you differentiate a function. And sabko pata hai na? You all might have seen this chain rule of differentiation. Then if you divide with dt on both sides or whatever the variable, for example, so if you divide with dt, then you have dt in all the terms. That's what you get. Okay, then this is the total derivative of the function. So this is the total derivative of the function actually. Okay, and once you fix the function, okay, then we can have the differentiation. Now if you fix a point, for example here, okay, so let's say at this point you have some velocity vector. Okay, so the fluid is flowing at certain velocity. So let's say this is the velocity vector, and this velocity vector can keep changing with time, of course. Okay, so let's see, for velocity vector which is given by ui plus vj plus wk, I am telling it in Cartesian. Okay, where u is the x component of velocity, v is the y component of velocity, and k is the z component of velocity. This w is the z component of velocity. You know, this u can be a function of x, y, z and t, because in general normally if you are dealing the space as 3D, okay, space can be treated as any dimensions, but if you take for simplicity as 3-dimensional, then this u can depend upon the point. Like for example, मान लो कि यहाँ मेरा flow है and I have a point here x, y, z. Whatever is the x component here need not be the same x component at some other location. Okay, also at the same point, whatever is the velocity at time t equal to 5 seconds need not be at time t equal to 10 seconds. Okay, so therefore there is a difference. Hi Akash, Sidhu. So v is function of x, y, z, t, and w is also function of x, y, z, t. Now you know acceleration is nothing but dv upon dt. Okay, so since this I, j, k are constant vectors, they are constants in both direction and magnitude, this can be written as du by dt I, dv by dt j plus dw by dt k actually here. Okay, and since this is the acceleration vector, this part is nothing but the x component of acceleration, this part is nothing but the y component, and this is the z component. Okay, and since u depends on 4 variables actually, so ax can be written as, like you see, du by dt. So if you write du by dt actually, then you would get dou u by dou t into dt by dt plus dou u by dou x into dx by dt plus dou u by dou y. I'm just expanding one term so that you can see the things, and dou u by dou z into dz by dt. Okay, so this is what you get. So this is 1 anyhow. So dx by dt, rate of change of x coordinate with time, is u, v and w. Okay, so you have dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Okay, so this is the x component of acceleration. Similarly you have the y component, and similarly you also have the z components of accelerations. Okay, now let's see Once you have the acceleration vector, then ax I cap, ay j cap plus az k cap actually, okay, and you can calculate the magnitude of this vector definitely, root of ax square plus ay square plus az square actually here. So this is how you get in case of Cartesian, okay, and similarly in case of polar, if you need, acceleration is given by ar er cap plus a theta e theta cap plus az ez cap, okay, where this radial component of acceleration is dou vr by dou t plus vr dou vr by dou r plus v theta by r dou vr by dou theta plus vz dou vr by dou z minus v theta square by r. This is what you have the radial component of acceleration, and theta component is dou v theta by dou theta dou t dou vr plus this v theta by r dou v theta by dou theta plus vz dou v theta by dou z plus v theta vr divided by r, and acceleration the z component, this is usual like how you have in the Cartesian, same thing. So these are in the polar coordinates, okay. So in case if someone give you the velocity profiles in the velocity profile where v r, v theta and vz are there, means if they give you the velocity in case of polar coordinates, then this is how you do the r theta and z coordinates actually, okay. So normally I use them every day in my research, so I just remember them, okay, but in general you need not mug up, okay, them, but you can actually you know, if you keep using them you will get familiar soon, okay. So let's see, this is how you calculate the acceleration. If you write this acceleration in vector form, see, in fluid mechanics it's better to write as many equations as possible in vector form. Q, because if you see, if you have a velocity vector, you can write it as ui plus vj, or you can also write it as vr er cap plus v theta e theta cap, okay. So I'll tell you why coordinate system is important. So if you have this xy, okay, अगर आपके पास एक velocity vector है, ठीक है, then many of you write this as v and u, so that you have x component plus y component, okay. The same velocity vector, this same vector, I can also write it as vr v theta, okay. So I can write vr and v theta, of course. Now one thing you can understand here is this vr v theta or uv, they obviously u is not same as vr, v is not same as v theta, okay. But in both the cases, one thing, whatever the coordinate system you choose, the vector which is same is this vector, correct. Only depending on your choice of coordinate system, this components comes up, okay. But in reality physics, this vector remains there, okay. So that's why writing vector equations is very nice, because they are independent of the coordinate systems, okay. You can apply them in Cartesian, in polar, in any coordinate systems actually. So this acceleration dv by dt can be written as dou v by dou t plus v dot del operating on velocity vector, okay. So this is your acceleration, of course, and this part whichever is here, a very straightforward thing, because you see this, or here also if you see, this term can be written as dou u by dou t, maybe I'll plus c. Can I write this as u into dou by dou x plus v into dou by dou y plus w into dou by dou z operating on u, of course, okay. So this u into dou by dou x plus v into dou by dou y plus w into dou by dou z can be written as v dot del actually, okay. Then this operating on u. So if you multiply I cap to this, similarly if you write y component of acceleration, z component of acceleration, all this stuff, you will end up with this equation, okay. And in this equation, this part dou v by dou t, which is here, is called temporal acceleration. and this is called convective acceleration. Convective means with respect to position. You may think, how can things accelerate with respect to position? If you have a nozzle, okay, like this, then even though if you have a steady flow inside the nozzle, but compared to this location, the particle should accelerate here. Okay, so that's how acceleration can take place. Now, steady flow implies only dou v by dou t is 0. That's all. This is what steady flow tells you. Okay, steady flow need not mean that this full acceleration is 0. Okay, because काफी बार लोग क्या सोचते हैं कि like acceleration is derivative of time, and if things are not changing with time, it is 0. No, this is the temporal of time and this is the total derivative. ठीक है, and मान लो कि अगर flow steady flow है तो सिर्फ यही term 0 होगा, not the complete term. Got it? And so steady flow, uniform flow, then you have your v dot del operating on v is equal to 0. Okay, so therefore if flow is both steady and uniform, only then the total acceleration will be 0, or else in case of unsteady and non-uniform there is a possibility, but this is the main condition for total acceleration to be 0 actually. Okay, is this clear to all of you? Is this equation okay? And if you split this in Cartesian and polar coordinates, you'll have these equations whatever I have given you. Okay, everyone clear? It's just based on the chain rule, that's all. Okay, and normally I am not showing you why this v theta square by r, v theta vr by r comes up in polar coordinates. Normally using complex numbers you can show that, but right now I'm not doing it. Okay, it's a simple thing but not a very complicated one. I generally show many times in crash courses, in full comprehensive courses and all, but today let's not do that. Okay, because time is short. Fine. So if things are steady, only this temporal part is 0, and if things are convective, if things are uniform, then only this part is 0. If steady and uniform, then both will be 0. Okay, then total acceleration is 0 in that case. Chalo, let's try to solve one question, because काफी लोग lunch करके आए थे, sorry dinner करके, so let's not make them sleepy. So solve this question. An idealized velocity field is given by v is equal to 4tx I cap minus 2t square by j cap plus 4xz k cap at the point minus 1 1 0 and at time t equal to 1. The magnitude of the material acceleration means the total acceleration. Since it's called the material derivative, so total acceleration vector of the fluid element is dash. Come on, solve this question. Okay, 3 minutes you take because some calculations are there, so but do it correctly. Okay, no calculation mistakes. Come on guys, quick. -2, but magnitude of the vector will be positive, no? Even the magnitude of the total acceleration vector of the fluid element, and if you calculate magnitude of any vector, it will be positive. How can you get -2? 20 maybe. See, that's what I'm telling. When you solve any numerical answer type question, when you get some value, try to make it physical in feasible with the given question. Okay, chalo, let's see solution. So given, because I was not able to see the velocity profile, so given v is equal to 4tx I cap minus 2t square y j cap plus 4xz k cap actually. Okay, so this is u ultimately 4tx minus 2t square y 4xz. Okay, then if you calculate the acceleration in the x direction, ax du by dt, which is 4x plus u into dou u by dou x plus v into dou u by dou y, dou u by dou y, so which is 0, plus w into dou u by dou z, this is also 0. So this term gives you 4x if you take common, then 4x if you take common, 1 plus 16t square, so 1 plus 4t square, sorry, yeah, so 1 plus 4t square. This is the value of x component of acceleration, correct? How many marks we can expect from this chapter? Generally 2 to 3 marks. Yeah, okay, so let's see 4x into 1 plus t square, right? So if you take 4x common, 1 plus 4t square, ay is dv upon dt, so which is dou v by dou t, which is minus 4ty plus u into dou v by dou x plus v into dou v by dou y, which is minus 2t square, plus dou v by dou z, there is no involvement of z, so this is 0, so this term is also 0, minus 4ty minus 2t square y, so minus 4ty minus 2t square y, of course. Okay, then az acceleration dw by dt, which is equal to, so dw by dt if you simplify, we have dou w by dou t, there is no involvement of t, plus u into dou w by dou x, there is no involvement of y, plus w into dou w by dou z, which is 4x. So if you simplify this, 4tx 4z, 4xz 4x, so if you take 4, okay, if you directly let 16xzt plus 16xzt plus 16x square z, so these are the components. Okay, so now if you substitute the value of, so if you now substitute the value of -1 1 0, so -1 1 0 and time t equal to 1 second. Okay, so -1 1 0, so minus 4 times of, at t equal to 1, this is 5, so minus 20. Good, so this is minus 20. Similarly here, if you put -1 1 0 and t equal to 1, let's see, -1 1 0. Okay, so -1 1 0, so this becomes -4 minus of, again y equal to 1 and t equal to this, so this is 2, -6. Okay, and z is equal to 0, so this term will go to 0, so this is 0 actually. Yes, ay is -20. So 4t plus 4y, where minus 4ty, okay, plus this is correct, so this should be plus this component. See, these things happen, we should be careful. So plus 4t power 4y. Excuse me. So plus 4t power 4y. So then this is minus 4 plus 4. This is 0. Clear? So anyway, we have only ax in the field. So therefore, acceleration is equal to minus 20 times I. That's all. So magnitude of acceleration is 20 units. That's all. Okay. So this can be 20 units. Clear? So in fact, it's not only about velocity. Okay. It's not only about this one particular velocity. You can have this function to be like temperature, any scalar function, any vector function, and all. So basically the idea is when you have this derivative, okay, when you are doing the total derivatives, like in this case, this is the total derivative. In fact, instead of velocity, you may have some scalar field like pressure, temperature, whatever you have. Okay, so they can ask you questions based on any parameter at this point. But this is how you calculate the total derivative. Okay, then you have the flow visualization lines. So the first one is streamline. Okay. So in general, well, V is equal to Ui plus Vj plus Wk. The streamline is given by dx by u is equal to dy by v is equal to dz by w. Okay. So in general, you can have this. Can you explain derivative just a little? How did you derivation? Which one? This one. So this is dou u by dou t. Likewise for all the terms. Okay, one. Fine. That's how I've done it. Clear? So let's so this is the streamline derivation. Actually, you're asking me for this. Are you asking how did I do this? Is your question about this? How did I write this equation? Is that the idea you're asking about? Hello. No? Yes? Fine. Anyway, it's very simple. So what's the streamline definition? Normally if you have the stream function, for example, so streamline is nothing but the locus of the curve such that at any point if you take the tangent, you will get the velocity vector. Correct? This is what you know. Fine. So then if you take a small elemental length on the curve, which is ds, okay, then clearly this element and the tangent are almost parallel to each other. Correct? So therefore, if you see v cos ds is 0. That's all. So this gives you this, where ds is, this can be resolved into components dx I cap, dy j cap, dz k cap, these things, and velocity can be written as ui plus vj plus wk. Now from the definition of this streamline, that streamline is the locus of all those points. At any point if you draw a tangent, the tangent gives velocity. So the tangent and the curve will be almost at 0 inclination to each other. So v cos ds has to be 0. If you do the cross product of these two equal to 0, you'll get this equation. Okay, that's how. Right. So this is how you get the streamline. Now streamlines cannot intersect, you know these things. Streamlines can't intersect, and also a streamline can't intersect with itself also. Can't intersect with itself. Okay, so a streamline can't intersect with itself, because when you intersect a streamline, okay, then physically at a given point you'll have two velocities because two tangents can have, okay. Like if you see, if a streamline is intersecting like this, then at this point this is one tangent and this is one tangent, okay, which tells you physically a point can have two velocities, okay. Tomorrow how many hours will you take Maha Abhyas to plan my routine according to that? Good. I'm happy that people are there to plan their daily routines. So maybe hopefully like 3 hours, 3.5 maximum, okay. I'm planning to solve some 22 questions so that on an average 5 minutes for one question, or 6 minutes you take, 22 into 6, so 132. But definitely it will take beyond that, okay. Each question take 10 minutes, let's say, so 10 into 22, 220, so 3.5 maybe. So clearly at this particular point you have two velocities, but physically a particle can have only one velocity at a given time, and this is instantaneous streamline, instantaneous concept, okay. So this is the concept of streamline. Then we have path line. Over a period of time. So you take a particle and record its movement, that's all, okay. So at time t equal to 0 you identify some particle, and this can move what all way it want. In turbulent flows especially this can move in any way. So t equal to t1, t equal to t2, okay, then t equal to maybe t4, t3 and so on. This particle can move in any path, okay, and the path line can intersect because a particle after crossing a position it can come back to that position after some time, okay. So this is path line. So how do you do the path line equations? That's the question, okay. In tomorrow's class we'll again solve some good questions on this. So for V, ui plus vj, okay. So for V is equal to ui plus vj, u is equal to dx by dt, okay, and v is nothing but dy by dt. In general, if you take 2D for example, for 2D u is function of x comma y, which is dx upon dt. V is also function of x comma y, which is dy by dt. Now when you are doing with integration with respect to space domain, then this x, solve this dE, solve the dE by taking y as constant, okay, and solve this dE using x as constant. X as constant. Anyway, I'll solve a question tomorrow on this, okay. So treating x as constant. Now here you will have some function of x comma y comma t is equal to constant, basically some function of x comma y comma t equal to 0. Here also इसका loop बोल बताया था आपने सर, yeah, correct. People fall in trap at some points, okay. So if you solve this you will get one equation which is some function of x y t is equal to 0, and if you solve this then you will get some other function of x y t is equal to 0. Now from these two eliminate t, that's all. From these two eliminate t, that's all, okay. Then finally you will have the equation only in terms of x comma y. Then this implies some function of x comma y is equal to 0. This is the path line equation. This is path line equation actually, okay. So I have confusion in examining steady flow, uniform flow and all flow equations is given. Sorry, I have confusion in examining steady flow, uniform flow and all. If flow equations is given, please explain. See, if flow equations is given in the components u, v, w, if there is time involved anywhere, okay, then it is unsteady flow. Clear? If there is some time involved, then it's unsteady flow, and if time is not there, okay, if you have only xyz, then it's non-uniform, that's all, okay. If you have only time and no xyz, then it's uniform. Clear? Fine. So that's how we have. Similarly, you get the streak line. So what is a streak line actually? Streak line is basically the locus of all the points in the flow that have passed to a fixed point a fixed point. Like for example, if you have an injector, okay, so if you have an injector, so let's say this is path line of one particle, okay, then this is path line of the second particle, and then you have path line of the third particle, okay, and path line 4. Then let's say the first particle is somewhere here, second is somewhere here, third is somewhere here, fourth is somewhere here, and fifth, sixth, all these things will come here. Finally, if you draw all these points, okay, definitely every point on this line have passed through this point, correct? So that's called a streak line. If you have all constants, steady and uniform flow, obviously, okay. Steady and non-steady is depending on involvement of time, okay. So if you have time involvement, it's non-steady, sorry, it's unsteady unsteady, and if there is no time, it's steady flow, okay. So this is streak line, and so obviously, you know, in case of steady flow, okay, so in case of steady flow, all the path line, streamline and streak line become identical. Streak line become identical. Okay, so they become identical actually in case of steady flows, okay. So maybe I have some question to show, okay. So anyway, we'll see questions in tomorrow's class better. So continuity equation, so which is conservation of mass, of course, okay. So if you look at continuity equation, again it is basically dou by dou t plus divergence of rho v is equal to 0. That's the continuity equation. And if you have steady flow, then only this part is 0, so divergence of rho v is 0 actually here, okay. So this implies for steady flow, dou rho by dou t is equal to 0, and this implies divergence of rho v is 0 actually here, okay, which tells you dou by dou x of rho x rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0, of course. मुझे लगा सर आज 4 बजे 4 बजे, let it be. What song? Tomorrow you don't have Maha Revision, no? See, if I want to teach the same things, I can teach in 4 hours. By night 1 o'clock I can close everything. Do you want me to do that? I can do, obviously. It's difficult to teach something new, but if you want to skip something which you know, it's easy, right? करेक्ट ना. मान लो कि अगर कुछ आने वाले कॉन्सेप्ट को स्किप करना है तो कितना आसान ही है ना, बट आई डोंट वांट टू डू दैट, ठीक है, क्योंकि आई ऑलवेज हैव दिस इंटेंशन इन माय माइंड एज अ फैकल्टी व्हेन एवर आई टीच समथिंग, ओके. डेफिनेटली हर एक फैकल्टी ऐसे कोशिश करता है कि पूरा सिलेबस को कवर करना पड़ेगा, ठीक है, But let's say you teach 99 points and if you skip 1 point for example, and मान लो कि बाद में क्वेश्चन वही एक पॉइंट से आया था, then it's not a very positive thing. Okay, so that's why. Hello, let's see, this is for steady flow, so divergence of rho v is equal to 0, and this same equation can also be written as dou by dou t plus rho times divergence of v is equal to 0. It's just based on the chain rule actually. Okay, so this is based on the chain rule, of course. So if you expand this dou by dou x plus dou by dou x of rho u plus dou by dou y of rho v, all these things, del vector or vector c explains our thoda. Sorry, which one? Del vector or vectors, vector c. What is vector c? Optical language. Del vector, del is basically this. Del is dou by dou x I cap, dou by dou y j cap plus dou by dou z k cap. Okay, or in polar dou by dou r e r cap plus 1 by r dou by dou theta e theta cap plus dou by dou z e z cap. That's how. Yeah, PDF provide कर सकता हूँ पक्का. Okay, vectec v. What is vectec v? Okay, vector v. V is the velocity vector, no? Okay, v is velocity vector, that's all. So this equation can be written as this. Now for incompressible flow, in fact this point is a bit important. For incompressible flow, this d rho by dou t is equal to 0, and this implies continuity equation becomes, continuity equation is divergence of velocity v is equal to 0. Okay, so this divergence of v is equal to 0 is valid for both steady and unsteady incompressible flows, valid for both steady, unsteady, incompressible flows. Okay, so that's what you get. JEE students देख सकते हैं क्या? I don't suggest generally, maybe for the first 4 chapters you can see, not first 4, no need to first, second, fourth, buoyancy and flotation, that's all. Maybe dimensional analysis if you want you can see. Okay, chalo. This is valid for both steady and unsteady incompressible flows. Okay, because this total derivative is 0, and if total derivative is 0, then density into divergence of v is 0, but density is non-zero. Clearly, you know, for any physical system you have the density, so इसके वजह से divergence of velocity is 0, of course. Okay, and obviously if you want to expand it in you know, this Cartesian and polar systems, so for incompressible flow, divergence of velocity is equal to 0. So this implies for Cartesian v is ui vj wk. This implies del dot v is equal to dou e by dou x, dou v by dou y plus dou w by dou z is equal to 0. So this is the continuity equation normally in Cartesian coordinates. Okay, and if you look for polar, then you know, for polar v is given by vr er cap plus v theta e theta cap plus vz ez cap, and this implies divergence of velocity is dou vr by dou r plus v r by r plus 1 by r dou v theta by dou theta plus dou v z by dou z is equal to 0. Okay, so these are the two equations. Okay, so you see this is for Cartesian and this is for polar. coordinates. Okay, so these are the two equations in Cartesian and polar for continuity equations. Okay, and applying these equations will yield any velocity profile. If you have incompressible flow field, then you should satisfy this equation. Similarly, if you define in polar coordinates, it should satisfy this equation. Okay, so let's solve some question, and obviously, you know, anyway, so continuity tells you that mass flowing through one section should be same as mass flowing through other section. This chapter is very confusing, very straightforward in fact. Okay, till now I have taught you only three things. One is total derivative concept, one is flow visualization lines, and one is basically continuity equation. That's all. Okay, if you feel confusing, then just let me know what are the points you felt confusing. We can correct it. Okay, just a second, let me close this pop-up. This pop-up keeps coming up every time. Fine. Okay, so then let's see. Fine, if you have continuity, then let us solve one question maybe on continuity, because things, okay, first solve this question. Yeah, solve this question, it's a nice question. I'll give you 90 seconds to solve this. Chalo, solve this question. -5, is it? So see here, solution. It's a steady and incompressible flow field, okay, and 2D. So dx by dt is equal to ax and dy by dt is equal to by. So these are the path lines, okay. So different path line equations. So dx by dt is nothing but x component of velocity, and this is y component of velocity. So u is equal to ax and v is equal to by, okay. Now if this is incompressible flow field, this should satisfy the continuity equation, okay. So for incompressible flow field, divergence of velocity, which is dou v by dou x plus dou v by dou y, in this case you have only two components, is equal to 0, okay. So what is dou v by dou x in this case? Dou u by dou x is a plus b is equal to 0. So b equal to minus a, and so b is equal to -5. That's all. Okay, so -5. Very straightforward question. Okay, nothing to worry about. So -5 is the correct answer. Then solve this question. Water enters a two-dimensional square channel of a constant width h is equal to 75.5 mm with uniform velocity u. The channel makes a 90 degrees bend that distorts the flow to produce the linear velocity profile at the exit. If V max, so this is V max is equal to 2 times of V min. Okay, if U at this point is 7.5 meters per second, the value of V min is dash. So what is the V minimum here? Okay, so you have a linear velocity profile at this point. So you know continuity, like basically rho into A V should be constant across the sections. Okay, if there is no unsteadiness. Clear? So, and of course it's a steady flow. Clearly things has to be steady because this channel cannot hold some mass. So solve this question. This V max is 2 times this V min. Don't worry, like we can talk about the extra topics of XC once the mechanical exam is done. Okay, even for thermodynamics. Three 3.75. Potential flow not in mechanical, sir? No, generally not the superpositions and all, but normally you can have some part of velocity, potential, stream function, these things. Okay, but not for the superposed flows and all. Okay, yes. If it's English batch, then I have taught all the things which are necessary. Okay, you can check the syllabus. If it's English batch, then I have taught mechanical plus XC syllabus completely 100 out of 100% for thermodynamics, even for fluid mechanics. Okay, these years turbulent flow, one question 100%, maybe. Let's see. Hello. So V max, V min and U. So solution, whatever the flow that's happening here, the same flow should come out. Okay, and since the velocity is linearly changing, let's see if you pick the average velocity at this point. Okay, so if you pick the V average, okay, V average, so V average, since it's a linear velocity profile, this is half times of V max plus V min. Okay, so we have half into V max plus V min. Then blunder questions, this one. Okay, let's see. So this is the case. Now clearly the area of the flow is uniform throughout. Okay, you can see it, water enters a two-dimensional square channel of constant width, h is equal to 75.5 mm with uniform velocity u. The channel makes a 90 degrees bend that distorts the flow to produce linear velocity profile. Okay, so clearly if you call this section 1 and if you call this section 2 in the flow path, then rho 1 A1 V1 is equal to rho 2 A2 V average. V average 1 is equal to rho 2 A2 V average 2 actually here. Okay, but one thing you can observe, it's a square duct and this H is uniform all over. Okay, so if H is uniform all over, then you can cancel this A, and water enters the two-dimensional flow. So generally if the velocities are within this range of 7.5 meters per second and all, it's subsonic flows, so you can, it's incompressible flows actually, so we can delete these densities. So V average at section 1 should be same as V average at section 2, so half into V max plus V min, and V max is 2 times of V min, so this is 3 times of V minimum here. Okay, and here the velocity is uniform, so the average velocity at this point is just capital U. So V min is equal to 2 by 3 times of capital U. So 2 by 3 into what is capital U? 7.5 meters per second. Okay, so obviously this is 2.5. So that's all. Okay, so you have 5 meters per second is the V min. And to apply this formula for the mass flow rate, for m dot is equal to rho AV, the condition when you can apply that is when this A and V are perpendicular to each other. Okay, the velocity vector should be exactly perpendicular to that area, like in these cases, otherwise you cannot apply that formula. Clear? Rho AV you can apply only if the velocity is normal, perpendicular to the flow area. Okay, so 5 meters per second, that's all. So let's see, let's go to further things. Translation, deformation and rotation of fluid elements. Okay, the is everywhere, we can get average out velocity like in pipe flow, etc. Generally, yeah, definitely average velocity is a hypothetical concept in fact. Okay, every fluid physically has viscosity and there exists some velocity profile definitely. Okay, then let's see translation, deformation and rotation. So for the velocity profile involving Ui plus Vj plus Wk. Okay, so case 1, for pure translation, okay, for pure translation, U equal to constant or U equal to constant and V is equal to constant actually. Okay, then in that case the fluid element just translates. Okay, and case 2, for U being function of xyz and V being function of xyz, W also being function of xyz, you have normally, if you in case if you write the strain tensor, okay, strain rate tensor, for example strain rate matrix, which means you have linear strain rate gamma dot xy, or in fact I just write it in a single way, xy, xz, yx, yy, yz, zx, zy, zz. Okay, and you can see these are the strain rates, and if both the subscripts are same, it's the normal strain rate, and if both the subscripts are different, it's a shear strain rate. Okay, like how we have gamma dot xy. Of course in cases you can denote this as gamma dot xy and all. So if you see epsilon dot ij in this matrix is nothing but half into dou ui by dou xj plus dou uj by dou xi in fact. Okay, so which means if I is equal to j, it just becomes dou e by dou x. So these terms, in fact if you write them, you have epsilon dot xx is equal to dou u by dou x. Okay, and okay fine, let me first show you the actual shear strains, and then we'll see it in terms of the convergent form, okay, or basically in the stress tensor form, sorry, the strain rate tensor form. So epsilon dot yy is dou v upon dou y, epsilon dot zz is basically dou w by dou z, okay. So these are the general strain things, and gamma dot xy is equal to 2 times of exy, which gives you dou u by dou y plus dou v by dou x. Similarly, and gamma dot yx, obviously this is also same, because if you see, if you interchange x with y and u with v, things remain the same. Similarly here, gamma dot yz, gamma dot zy is equal to 2 times of epsilon yz, which is dou v by dou z plus dou w by dou y actually, and gamma dot xz, zx to epsilon dot xz, which gives you dou u by dou z plus dou w by dou x. So these are the shear strain rates in reality, okay. So gamma dot xy is given by this, which we have seen in the xy plane. So if you don't have any v, then that's dou u by dou y. In the first chapter we have seen today in the beginning, and if you write it in the matrix form, and if you write as individual elements, this 2 comes up. Why this 2 comes up is again calculation depending on the movement of the fluid and all, which we are not doing right now. But in general, you can keep these equations, which can be helpful to you. Okay, so the shear strain rate in the xy plane is given by this, shear strain rate in the yz plane and shear strain rate in the xz plane actually, okay. And if you look at the angular velocity, similarly this gives you half times curl of v, okay. So this is the angular velocity vector which the particles undergo at any given point depending on the velocity profiles, okay. So many times it happens that a question comes from this, whatever I have written on the board, okay. Majority of the questions basically in the differential analysis comes from one of these things, okay. Again, I'm not deriving all these things. If we have time, we'd have derived. So half wala कब use करेंगे? Every time, okay. Omega is always half times of curl v, okay. In fact, this curl of v is called vorticity, and half of the vorticity vector is the angular velocity vector, okay. Fine. Half भी use होता है shear stress में. That's what I was telling you. When you write it in this matrix form, this is the shear strain rate matrix, okay. When you try to write elements in this case, then they'll use this half definitely, okay. If they don't use this notation, and if they write direct shear strain rates, then there is no half, okay. We can actually derive all these things. For if you have gamma dot, then there is no half here in this case. Vorticity is 2 omega, yeah, of course, correct. Okay, so vorticity is 2 times omega, which is curl v. You can check clearly others. When they try to write directly, okay, then you don't have any half. Clear? So these are the linear strain rates. And these are the shear strain rates, okay. For irrotational, omega is 0, yeah, of course, this curl becomes 0. Yes, if you have an irrotational flow, then definitely the curl becomes 0, okay. And what is irrotational? Particles do not rotate during the motion of the flow, okay. So during the flow, for irrotational flow, particles do not rotate about their axis. During the flow, and curl V. That's all. Okay, and again in this case you have something called uniform translation or rigid body rotations, all these things which we will deal using examples in tomorrow's class. Okay, but this slide, whatever is there right now, is very important. Many times you will see questions from these things. Okay, rotation and evolutions both are same, both are confusing. It's very simple. See, evolution about some axis, you will, like Earth revolves around the sun. Okay, but during the evolution it also rotates about its own axis. Okay, rotation is obviously done by the body about the body's own axis, and revolution is about some different axis. So that rotation should not be there. Okay, is this clear to all of you till this point? Whatever we have done on the board, those things are really important. Okay, normally it comes up from the rotations, and using Taylor series, linear expansions, all these things can be derived, but right now I'm not doing it. Okay, when you write the shear strain directly, the shear strain rates directly, there is no half. Okay, so please make sure. But when you write it in the tensor form, you will get a half, which that's the way how these elements inside the tensor are defined. Okay, these elements are not again same as the gamma or the direct shear strain rates. Okay, so please be careful. Fine. Then uniform translation of fluid systems is equal to 0 incompressible, is dot is equal to 0 incompressible, and curl is equal to 0 irrotational. Correct. Okay, if divergence is 0, then definitely it's a incompressible flow field, and if curl of velocity is 0, it's irrotational flow field. Okay, yeah. So let's see uniform translation of a fluid system, or sometimes in some books you will also read this as rigid body motion. Of fluid systems actually. Okay, so it's a very simple story. Like if you have a vehicle, for example, okay, or some facility, and you have some fluid like this. So normally if this tank is static, okay, so if you have this tank, so if this tank is static, then the level of the free surface will be horizontal. Correct. So now when you accelerate this tank, let's say this tank is supposed to some acceleration. Okay, then physically there is no flow of the fluid inside the tank, but depending on the tank motion, this complete fluid will also follow the motion of the tank actually. Okay, so individually the fluid do not set up into motion inside the tank. Okay, so this cases the fluid also moves exactly like this tank, and it's like a rigid body motion. Okay, so in this case if you see, we have del P minus rho x bar, or you can say rho x bar, the equation of motion. If you derive using differential element, you will end up with the equation of motion as rho x bar minus del P is equal to rho times acceleration. Okay, but this acceleration is not of the fluid because there is no flow inside, it's just the tank's acceleration. So A of the tank actually here. Okay, so this is A of the tank, and A of the tank, let's say you have Ax I cap, Ay j cap, and Az k cap generally. So normally you have the right handed coordinate system x, y, and z. Okay, so this is the coordinate system. So if you expand again, x bar is the body force per unit mass, then del p is the gradient, okay, and rho a of the tank. So if you expand these quantities, you will observe dou p by dou x is equal to minus rho times ax, dou p by dou y minus rho times ay, dou p by dou z. The pressure difference in this case is minus rho times g plus az. Okay, so this is what you would get. And normally if you take only x and z directions into consideration, let's say the tank is enough wide, so no changes in the y direction is observed. So if you take a coordinate system at the center, and if you try to analyze this x and z directions, means basically taking the tank as 2D, you will observe the line of constant pressure is inclined. Okay, the line of constant pressure is inclined, and this inclination theta, okay, so this is the original surface, and if you have for example the x direction motion, okay, in this sense, which is ax for example, okay, then this angle theta by which it has rotated, or if this is theta, then tan theta is modulus of ax upon g, where theta is acute. Okay, so theta is acute. Like for example, if this is theta, then this small part is 180 minus theta. So tan 180 minus theta is minus tan theta. If you apply a bit of small trigonometry, you will observe finally, if the tank is accelerating forward in the forward direction at an acceleration ax, then this line of free surface will tilt by an angle theta, where theta is given by this equation. Okay, like you can see, generally it's very simple to see. P is function of x comma z. If you delete y, no variations in the y direction. So dp is dou p by dou x, so which is minus of ax into dx, plus dou p by dou z, so minus of times g plus az into dz. That's all. Okay, and if you want a line of constant pressure for p equal to constant, so this tells you dz by dx. Okay, and for the time being, if you make az is 0, if the tank is only purely translating along x direction, then this equation directly gives you dz by dx is equal to density of fluid cancels up because one side it is 0, so minus ax by g. That's all. Okay, this is what you get. So that's how this dz by dx is nothing but, if this is z axis and this is x axis, angle made by the line with x axis is slope, I mean the tan of that angle. So tan theta is minus ax by g. That's all. Okay, and if you want theta to be acute in general, you can write mod ax by g. Okay, so that's what you have. Clear? I'll tell you one very nice case. Normally we have dou p by dou z is equal to minus O times of g plus az. Okay, imagine if the tank is falling freely. Okay, if the tank is just falling freely like this, if I leave the tank with some water, then for az is equal to minus g. What is dou p by dou z? Can anyone tell me? In this case, what is dou p by dou z in this case? 0. So what does that mean physically? So this is 0. Okay, so if that is 0, what does this tell you? If you have a line like this, in this case the pressure at all these points is same. Normally in many interviews I have seen people ask you, like, everyone has this intuition that in a static fluid, here the fluid is relatively static with the tank. Okay, so in a static fluid, normally if you go deep, the pressure increases in general. Okay, but can you tell me a case where even if you go in the z direction, pressure do not change? They can ask you this question. Okay, so this is the case where even if you move along this direction, pressure do not change. Many times you might have seen experiments on YouTube. You have a glass, okay, paper glass. They'll put a hole, they'll fill water, okay, and they'll close the hole, and then they'll leave the cup. they'll shoot the video and then they'll show you in the slow motion that when the cup is falling, water do not come out of the cup. Okay, physically what happens when water is coming down with an acceleration g, the cup also comes out with an acceleration g. So at every point the water is covered by the cup, so physically you don't see any fluid coming out of the cup. Okay, so that's basically this case. Okay, there's no pressure gradient which drives the flow. Clear? So let's see, let's solve one question again. Oh, it went so long, I think. Just a second, guys, it went so fast. Yeah. So let's see, the tank 1 meter wide, so basically 1 meter width into the paper, is filled with water and has a vent hole at point A. So this is a vent hole, so definitely here pressure is 1 atm. Inside the tank, a 10 centimeter balloon filled with helium at 130 kilopascals is tethered centrally by a string. Okay, so we have a string actually here. This is the string. The tank accelerates to the right at 5 meters per second in rigid body motion. How much tilt will the balloon have? Okay, so this is moving at 5 meters per second square. So definitely, you know, buoyancy acts perpendicular to the line of motion, perpendicular to some constant pressure. So definitely you'll see this balloon will tilt depending upon the high pressure. So what is the angle of tilt of this balloon actually? That's the question. Come on, solve this. Okay, I'll give you 3 minutes. If you want, you can think. Hey, no need of 3 minutes. Okay, so 2 minutes is enough. All. Option D, 27 degrees maybe. Let's see. So let's see, in this case, ultimately the line of constant pressure, if you take this as the midpoint for example, okay, of course it need not be, but it's okay. Let's say if you take, then the line of constant pressure would be something like this maybe. Okay, the lines of constant pressure may be something like this. So if that's the case of line of constant pressure, so obviously the balloon will be pushed towards right. Then in that case, this balloon will take new configuration, which is something like this. Okay, so the balloon tilts. Now, how much tilt will the balloon have? So what is this angle? Theta. Correct? That's the tilt the balloon is having. Chalo. Now let's see. if you want to know this angle, let's see what is this angle. Okay, what is this angle theta? Okay, because if you see this angle theta is same as this angle, correct? Why? You have a horizontal and an inclined, so angle between two lines is same as angle between the perpendiculars. So this string will be exactly perpendicular to the lines of constant pressure because of the buoyancy, and this is vertical line. So if this is theta, this is also theta, which you can figure out. So now tan theta is equal to ax 5 divided by g, that's all. So what is theta? By 9.81, 5 by 9.81, okay, degrees tan inverse 27.007. That's all. Okay, so once you know this, you'll get this. But the conceptually you should know that buoyancy doesn't always act. You should know why balloon will tilt. Okay, balloon will obviously tilt because compared to the hydrostatic head here, see, if more fluid is on this side and less fluid is on this side, definitely there is high hydrostatic pressure at this point, so they can push the balloon towards right. Understood? Conceptually, did you understand why balloon gets pushed? Did you all understand why balloon gets pushed actually? Because on this side you have a high pressure head and this side you have a low pressure head. So definitely the pressure acting on the left face of the balloon towards the left is high. So as a consequence, balloon gets pushed physically. Okay, and balloon makes a tilt, and the angle theta is exactly the same as this angle theta. Good. So who all has marked D? It's correct. These kind of questions can come in GATE exam. Okay, you see, hardly they take not even 1 minute to solve, but conceptually you need some clarity. Okay, so let's see Euler's equation of motion. Then, you know, basically this Euler's equation is momentum equation of an inviscid flow. Momentum equation of an inviscid flow actually here. Okay, so if you have this inviscid flow, what is the meaning of this inviscid? No viscous effects. Okay, so no viscous effects in the flow. Then again, if you see, if you have a flow at any point, okay, so at this point if you take a small element and if the velocity is given by vector v, whatever, it can be in Cartesian or polar depending on the case. So rho x bar minus del p is equal to rho times dv upon dt. So this is the Euler's equation. Okay, so normally if you take this fluid to have zero acceleration, this is the fluid is static, okay, or basically the fluid is moving with uniform velocity, means constant velocity. In such cases this becomes zero, and again you will get back the hydrostatics part. Okay, so x bar is body force per unit mass, pressure gradient, and acceleration, which is known to you. Okay, so in general, like if you see the Euler's equation, so this Euler's equation is very straightforward thing. So many times they will give you neglecting body forces, they want you to calculate pressure gradients, all this basic stuff they'll give you. Okay, but it's a very straightforward equation. Okay, normally you can derive it using many techniques. There are plenty of techniques to derive this Euler's equation. One technique is again like the differential element, the common element, and apply the force balance in x, y, z directions. You will end up with this. Okay, so for gravity being the only body force, for gravity being the only body force, we have, for gravity being the only body force, rho times minus g k cap minus pressure gradient. So dou p by dou x I dou y j dou z k is equal to, you know how to calculate acceleration, we have just seen. So rho times of dou v by dou t. That's how you'll get this. Okay. Navier-Stokes derived formula? No. Actually, Euler can be brought from Navier-Stokes if you want. In Navier-Stokes, once you derive the Navier-Stokes equation, if you make the viscous term 0, then you can figure out. Okay. But you can see this rho of minus g k cap minus of these quantities is equal to rho dv by dt, and that's the Euler's equation actually. Okay. And if gravity is not playing any role in the flow, then you can neglect this quantity. Okay. If this is not playing any, let's say this is not responsible for the motion of the fluid. Okay. Then you need not put this. Only these two terms balance each other. Pressure and inertia terms balance each other. Okay. Then Bernoulli's equation. Bernoulli's equation. So if you apply Euler's equation along a streamline, you will get Bernoulli's equation. Okay. Applying Euler's equation along a streamline gives Bernoulli's equation actually. Okay. So this gives you the Bernoulli's equation. And one interesting thing here is, so normally many of you know, like for study inviscid flow, dp by O plus vdv plus gdz is equal to 0. Okay. You know this, that this is the Bernoulli's equation. And if you integrate, you will get P1 by OG. For incompressible flow, if you integrate, P1 by O1g plus V1 square by 2g plus Z1 is equal to P2 by OG. You have this equation. Okay. And normally in this case, the assumptions is study inviscid, means no friction basically. Okay. If you use the same assumptions, you can even derive this equation from thermodynamics. You know this? Like, have you seen deriving Bernoulli's equation from thermodynamics? Means basically the same equation. Deriving this from the thermodynamics, have you seen? It just takes two, three steps from the steady flow energy equation. Yeah, of course. From the steady flow energy equation, you can derive this. Yeah. Okay. So if you apply steady flow energy equation and if you make these assumptions like no friction, they're adiabatic. Okay. So no friction, reversible and adiabatic. No, in this we don't consider any heat interactions. So for reversible adiabatic process, the steady flow energy equation can be again shown as this equation. Okay. So then we can apply this Bernoulli's equation at different points. So this is basically the energy conservation. That's all. Energy conservation is what you have. Okay. So purely an energy conservation equation. And let's see, using this Bernoulli's equation, we can fine, it's okay. We'll solve this question maybe tomorrow. It's okay, fine. So vortex flows and rotating cylinders. This is one important concept again here. So we have the plane vortices. Okay. So plane vortex flows. So we have the plane vortex flows. So we have two types generally. Free vortex and the forced vortex. Free vortex and the forced vortex flows. Okay. So in case of free vortex flows, you know, V theta into R is constant, and in this case V theta is equal to R omega actually. So if you have a vortex flow, so let's see. Number of pairs became big, I think. Okay, this body is not responding faster. Okay. Just a second guys, this board needs some break I think. So ultimately, you know, if you have these things, so x, z, let's say for example, then definitely particles revolve. Okay, now when they are revolving, the nature how they are evolving decides board got tired. Will you teach lift and drag also? Why not? Definitely. Bernoulli equation applications was of important nahi hai. We'll teach. Okay, let them go to the control volume, because there here we have derived only the fundamental possible equations. Okay, then in the applications, like if I am talking about 𝐂𝐴, I'll take the full 𝐂𝐴. Okay, so that comes in the next chapter, control volume analysis. I'll teach all the applications of Bernoulli's equation. Okay, no issues. Then let's see. So definitely at any point you have some radius r. Let's say if this is at radius r and you have v theta at this point. Okay, the particle is revolving at an angular velocity of v theta, for example. Then in case of free vortex flows, this v theta and r are connected like this, v theta into r is equal to constant, and in case of forced vortices you have this. And similarly, when you come to the pressure variation, for free vortex, this P is proportional to minus 1 by r square, and for forced vortex P is proportional to r square actually. Okay, so this is also one very standard understanding, that pressure should be minus 1 by r square and proportional to r square in this case. Okay, one important point here at this configuration is, in case of free vortex flows, you can apply Bernoulli's equation at any 2 points in the flow. There is no restriction. Okay, but when you come to the forced vortex, you can apply Bernoulli's equation only at points on the same streamline. Okay, like physically you'll see, like if you see in free vortex flows, Bernoulli's equation can be applied at any 2 points in the flow. At any 2 points in the flow. So there is no restriction to apply the Bernoulli's equation. So definitely you can apply at any 2 points. P1 by OG plus V theta 1 square by 2Z plus Z1, P2 by OG plus V theta 2 square by 2G plus Z2. So this is what you would get actually. Okay, but in case of forced vortex flows, you'll see in forced vortex flows, you will observe P1 by OG minus V theta 1 square by 2G plus Z1, P2 by OG plus V theta 2 square by 2G plus Z2. Okay, and sorry, this is a minus. Clear? So that should be a minus. And if you apply Bernoulli's, if you try to apply the Bernoulli's equation at 2 points, you actually won't get a Bernoulli's equation. In fact, you will end up with this equation which has a minus sign actually. Okay, so this is at any 2 points in the flow. Valid at any 2 points in the flow, of course. Okay, and this is not a Bernoulli's equation. This is not Bernoulli's equation, of course. Okay, so if you want Bernoulli's equation, then definitely this minus sign should not impact. So on a same streamline, you have V theta as constant. So if you apply for same streamline, okay, so you can see in this case of forced vortex flows, Bernoulli's equation can be applied only along same streamline. Okay, so they can be obtained only along the same streamline. But that's the one of the major differences between the free vortex and the forced vortex. Okay, in forced vortex you cannot apply the Bernoulli's equation at any 2 points wherever you like. You can apply only the Bernoulli's equation. Got it? Yes, is this okay to all of you? Just a second, guys. We'll have some water. So okay, let's continue. Then rotating cylinders, the last part of this chapter. So like, let's see, if you have a fluid, for example, okay, and let's say you have a cylinder. So let's say maybe the cylinder is open to atmosphere. In fact, you have closed cylinders also. So initially, if this is the level of fluid and this is the axis, and if you are evolving this at an angular velocity omega, okay, then hey, what does this emoji stands for? I don't understand this. This fellow was what that fellow is doing? Okay, I understand all of you are putting one emoji. डर लग रहा है, लेकिन क्यों? इस चीज के लिए डर रहा है? Biting fingers. This fellow is biting fingers. Let me watch closely. Is it? Maybe. डर का माहौल क्यों? Why you should get afraid, man? We didn't see the T question before. Okay, maybe that's why. एग्जाम के लिए है, कोई दिक्कत नहीं है, एग्जाम्स आते हैं जाते हैं बस. एग्जाम क्लोज आए. सी आई विल टेल यू वन थिंग, एग्जाम तो क्लोज आते हैं ऑब्वियसली, एक दिन एग्जाम का डेट आते हैं, बट आई विल टेल यू हॉनेस्टली व्हाट्स हैपनिंग. ओके, मैकेनिकल में सिचुएशन ऐसा हुआ कि एक बार जब मैं गेट लिखा था 2017-18 में बीटेक के टाइम पे, उस टाइम पे इट वाज लाइक 1,70,000 1,60,000 पीपल राइटिंग गेट इन मैकेनिकल. ठीक है, अगर आप चेक किया तो भी गेट 2016 में 3 स्लॉट्स में हुआ था एग्जाम, एंड 2017 से 2 स्लॉट फिर. ओके, वैसे हुआ था, एंड 2018 और 19 वाज द पीक ऑफ गेट, बट आफ्टर दैट व्हाट हैपेंड? डिक्लाइन. 2020 COVID, people started work from home, people got habituated for easy money. ठीक है, so then post COVID things changed so much. Okay, they changed to that extent. आजकल सिचुएशन ऐसा कि जब मेरे टाइम पे अगर मान लो कि एक बंदा को 65 मार्क्स आया था, ठीक है, तो 65 मार्क्स में कम से कम रैंक होता है कि 4,000 3,800 वहाँ तक चलता है. ठीक है, लेकिन आज मान लो कि किसी बंदा को 65 मार्क्स आया था, rank is below 200 or 250 maximum, correct na? So situation became very lenient at some places. Okay, so you guys are lucky doing things when competition is slightly less. Mechanical engineers switching to CS, क्वेश्चंस इज हार्ड, कौन सा गेट एग्जाम में आने वाले क्वेश्चंस नहीं. If you look at papers like 2014, 2022, okay, then 2016 is reasonable, okay, but somewhere like 2015, I think, Kanpur again. So these guys rocked, okay. So it's not about how much you get ahead of the exam and all. Don't worry about those things. See, ultimate 2024 इतना tough नहीं है. So, but 6 questions, 6 marks, I think add scores were given at that point. See, many times I see students complain about the formulas. Okay, sir, इतना सा formulas कौन याद रखता है? I'll tell you honestly, guys. ये सब मैं लिख रहा हूँ क्योंकि I use them daily. Okay, every day, every now and then I keep using these formulas. So that's why I remember them so much. Otherwise, you know, even I would not have remembered these things. Okay, and it's not like since I am writing everything without looking at anything, you have to write all these things. No, it doesn't happen. But at some point, I'll tell you one thing: you should develop conceptual clarity on things. Okay, ऐसा नहीं है कि like just you you know, you go for like some exam by hearting formulas. GATE ऐसा exam नहीं है, ठीक है? You see, for example, I did not teach you what is the depth of centroid for rectangle, triangle. कौन याद रहता है? मुझे याद नहीं होता है. And even today, if you ask me like, sir, there is a triangle with vertex maybe touching face surface, then what is the depth of the center of pressure? Then definitely I'll do it. It takes me hardly 1 minute or 1.5 minutes to do it, and I'll do it. But it's not like I try to keep everything in my mind and then go for the exam. It's never going to happen. Okay? Is it okay by revising all these short notes of Maha Revision because full notes are taking a lot of time? Yeah, definitely. Okay. हर एक फैकल्टी डेफिनेटली ऐसे कोशिश करता है कि जो महा रिविजन में क्लास पढ़ाते हैं कोई भी पॉइंट मिस ना होते हैं. ओके. इस बार सर एक्सी कहाँ से देते हो? पता नहीं. Maybe I told this pata nahi till yesterday, but after yesterday I cannot tell this, I think, because admit cards are out now. Okay, I give in Delhi. Actually, to be precise, Noida. Okay. Best combination of XC ऐसा नहीं होता है, आपकी इंटरेस्ट पे डिपेंड होता है प्योरली. मान लो कि मेरा इंटरेस्ट थर्मल में है तो मैं थर्मोडायनेमिक्स और फ्लूइड मैकेनिक्स देता हूँ, लेकिन कुछ बच्चे ऐसा होता है कि थर्मोडायनेमिक्स एंड यू नो सॉलिड मैकेनिक्स देते हैं. सो things happen. Okay, so let's see what happened. There is nothing like best combination. ऐसा नहीं होता है कि एक सब्जेक्ट बहुत आसान आता है दूसरा सब्जेक्ट काफ़ी टफ होता है, वैसा नहीं होगा. ओके, नॉर्मली देयर इज अ बैलेंस बिटवीन सब्जेक्ट्स. एंड अगर आप में भी like even if you see there's like you can sense, like if you are preparing good for mechanical, then you can look at questions of solid mechanics, fluid mechanics, thermodynamics. These things will be like on a same scale. Last year 2-3 साल पहले तक fluid mechanics काफ़ी टफ थे. Okay, but last year 2024 was like the easiest paper of XC in fluid mechanics. Okay, which I almost finished in some 40-45 minutes. I think I have finished all the 22 questions and I got 35 out of 35 in fluid. There's nothing, to be frank, that one can commit mistake in last year paper. Very straightforward questions. Okay, so things happen sometimes, that's all. Okay, very rarely that happens, but not like every time fluid mechanics comes easy or every time solid mechanics becomes easy. There's nothing like that. Okay, fine, but don't get afraid of the exam. See, exam to likhna padega, definitely. There's no other option. So why do you fear? Give your attempt honestly and see what happens. That's all. Okay, chalo, let's see. So you have this omega. Then when this is rotating at omega, you will have this paraboloid, definitely. So you have this paraboloid, and if you see from this point, this is h. So this h is given by, if you have this radius as r, so this h is given by r square omega square upon 2g. It's a very simple thing which you can show up. So h is r square omega square by 2g, and at any point, like for example, if you have a closed cylinder, okay, so you have a closed cylinder something like this, which is filled with fluid. This is completely filled with fluid. Then if you take the axis here such that this is radial location, and from top, let's say this is height z, okay, then if you take a point here at this point such that it is at a depth z and radius r, the pressure at this point is given by two parts, okay. Pressure is a scalar, and the two parts which gives this pressure, one is the vortex plus other is the hydrostatic part, okay. So this is how you get the total pressure at this point. So this is due to the vortex if you are rotating this at some angular velocity omega, okay, and this is hydrostatic head, okay. And obviously if you want to calculate the force acting on the side walls of the cylinder, you take a small height of dz, and if you put r is equal to capital R, then you will get the pressure acting on the interface at this point, okay. So that P into 2 pi r dz, integrate it from z equal to 0 to h. Maybe this is z equal to 0, z is equal to h, whatever you take, and you can integrate the things. Clear? That's how you calculate the force acting on the surface, bottom, everywhere. So force acting on the bottom, for example, F on bottom a surface is equal to, so ultimately the weight of the complete fluid, rho F g pi r square into total height h, this plus integral r is equal to 0 to capital R rho r square omega square into 2 pi r dr. That's all, okay. So you see, this is the pressure at this point, and if you take the elemental radius, you'll have 2 pi r dr. So pressure into small area gives you force, okay, and you are integrating from small r to capital R, and this is the hydrostatic part. That's all, okay. And at any intermediate point, if you want to do this, instead of this z, you'll have h, this is z, okay, basically the length. आप तो एग्जाम से पहले रिवाइज भी नहीं कर सकते हैं ना. To be frank, no, I don't even get time to revise. Hardly I revise all the maths. I basically look at my own notes, okay. I look at my own notes and just go like that. Just some 5-10 minutes I'll look at the notes and go. That's what it, because इस साल मैंने fluid mechanics like almost 1, 2, 3, 4, 5, 6 times I've taught, okay, this year, this single year. So obviously you see now I was able to write all these things without, I don't have any reference near me, but it can happen, okay. When you keep teaching things many times, obviously like you write ABCDs without seeing anywhere, same thing, okay. So this is the case that you have, and that's the bottom surface force which is acting. Clear? So with this I formally close this 5th chapter, and let's move to the 6th chapter, control volume analysis of fluid systems. Okay, fine. Guys, just a second, this pop-up again and again it's coming. Let me, why this pop-up is coming every time now and then? This fellow don't have any worker. Where is this charts? Yeah, good, I did not miss. So 5 chapters done, the majority, like the 50% or 55% almost is done. Next 2 chapters are the hectic chapters, and after that things are a little easy. Okay, chalo, let's see. How many of you know this? Okay, how many of you don't know this? Tell me. How many of you don't know this? How to apply and where to apply, what to apply? Knows, good. Okay, few people know it. इसमें बहुत confusion है. Force on plate plus what is it? Plus or I know, knows, I know linear momentum equation. That's it. Known but forgot. Okay, good. Anyway, सो यू टॉट इन फ्लूइड मशीनरी. अच्छा हाँ करेक्ट, हिंदी बैचेस में मैंने आपको टर्बो मशीन्स पढ़ाया था, सो उस टाइम पे मैंने इंट्रोडक्शन दिया था. ठीक है. या नेक्स्ट चैप्टर, दिस इज नेक्स्ट चैप्टर, कंफ्यूजिंग हाउ टू अप्लाई. ठीक है, काफ़ी आसानी चीज़ है, इतनी टफ नहीं है एक्चुअली. तो लेट्स सी. ओके, एनीथिंग दैट यू वांट टू आस्क? सबसे इजी चैप्टर है ये ऑब्वियसली. We have spent some 2-3 lectures na on others when we are talking fluid mechanics. This is one of the like feasible things which can be done. Okay, so anyway, let's see. Again I'll just give you the equations. Force on the fluid में कब प्लस लेना कब माइनस लेना. ओके ठीक है, so सब चीज़ हम क्लियर करेंगे इस टॉपिक में. So let's see Reynolds transport theorem obviously. So I just give you some idea. So if you have a control volume, okay, and if fluid is entering and leaving this control volume, then definitely depending on what's happening inside the control volume, the properties of this fluid will change. वो स्प्रिंकलर तो माइंड गोस. इट्स ओके, एक स्प्रिंकलर क्वेश्चन भी है, सॉल्व करेंगे. ठीक है, कोई दिक्कत नहीं. सो रेनॉल्ड्स ट्रांसपोर्ट थियरम ऑफ कोर्स. नॉर्मली अगर आपके पास टाइम है तो मैं एक चीज़ दिख सकता हूँ आपको, डाउनलोड्स. तो या आई थिंक I have called out it in the previous lecture. So okay, so normally I'll just show you the things you can understand. This is the derivations for what all I have given you the points. Okay, the rotation, angular velocity wala, everything. This is from Cengel, the diagram is from Cengel book. So that's what rotation is actually. Okay, if some of you did not understand, this is evolution. Okay, and you see this particle is not rotating. Okay, everywhere it has the same configuration, but then if you move into vertex flows, forced vertex flows. Okay, so if you move to forced vertex flows, then they rotate. Okay, the particles will rotate. But anyway, this is the Bernoulli equation showing and all. So these are the rotating cylinders, what all you have. Then the force acting on the side wall, all this stuff. Yeah, this is RTT. Okay, so the Reynolds transport theorem basically, the complete derivation, because sometime I think I have shown to some of the paid batch class students. But normally Reynolds transport theorem, if you have the system which is defined by set of particles, and you'll see this fixed plate we have seen, and we have done some analysis, some simple analysis, so that we figured out this equation finally. Okay, this equation. So this is the Reynolds transport theorem equation. So anyway, right now we don't look at all this stuff, but I'll just give you the formula, and more than formula, I'll make you understand how to write that plus minus signs, how to properly solve the questions using this Reynolds transport theorem. So these things we will focus. Okay, so let's see Reynolds transport theorem. So this tells you the weight of it connects, basically it connects a rate of change of quantity of a system, which is defined by set of particles. Okay, so this system is defined by set of particles. Okay, so this is defined by set of particles to the change of quantity of of control volume. Okay, to change of quantity of the control volume actually. Now let's see if you understand. Where do we get these notes? These notes will be uploaded in the Telegram channel. Okay, I have posted my Telegram channel, so there I'll upload the notes. Okay, no issue. Yeah, so let's see. So if you write this into equation form, for any quantity B, extensive property or extensive quantity, capital B with corresponding intensive quantity beta with corresponding intensive quantity beta this is given by dB by dt of the system is equal to dou by dou t of integral over the control volume beta times rho dV plus integral over the closed control surface beta times rho v bar dot n cap ds. Okay, so this is what we have. So in general, if you look at a small surface, for example here, and you have the outward normal as n cap, and if the relative velocity of the flow is something like this, so this is VR for example, okay, and that's the ds, the small elemental area, then the change of this quantity B, like quantities can be anything like linear momentum, angular momentum. Let's say for example if this is a combustion chamber, okay, then if fluid enters inside, then because of the combustion the linear momentum of the particles will change, okay, or if there is a lawn sprinkler, then the angular momentum of the liquid will change. So depending on what is this control volume, this system means the mass which is going inside will definitely suffer some changes, okay. So what is the change of that mass, and because of the change in mass, what is the change in quantity of the control volume? So these two are connected, okay. And normally for steady state, again the partial derivative with time goes to 0, so this is 0 for steady state. Steady state, okay. Then this VR dot n cap, okay, at all inlets, see you can break this into two parts. Firstly, dB by dt of the system is equal to, see this cyclic integral takes care of all the points at the surface. Like for example, you see this is 1 point, second, third, fourth, fifth, and so on. You can have n number of points, okay, but all these points can be classified into two parts. One is one set of points where fluid is going inside the control volume, one set of points where fluid is going out of the control volume, okay. So that's the points. Now at all the points where fluid is going out of the control volume, angle between n cap and VR is positive, so that's why this dot product becomes positive, okay. Density is just a scalar, so this dot product becomes positive. At all points of inlet, the outward vector and V bar has an obtuse angle and the dot product becomes negative, so that's why all the positive points corresponds to the outlets of the flow, and all the points correspond to the inlet of the flow are negative. So you can break this into two parts. Summation of all the points V dot n cap or ds, whatever, at outlet, summation of V dot n cap at out OVA, you can say maybe, okay. So m dot beta at outlet minus summation of m dot beta at inlet. So that's how this equation can be modified, okay. So this is at all the points. You break it into two parts, clear? You break that into two parts such that one set of points where all the points has the interaction as outlet, and the second set of points where all the points has interaction as inlet, okay. So like for example, you see in this case here the fluid is going in, so V bar is in this direction, n cap is somewhere in this direction, so the angle between them is obtuse. But if you take somewhere here, okay, where the fluid is going out, for example somewhere here, the n cap may be something like this, maybe the fluid velocity can be something like this, okay, but still this angle is always acute. So that's why at all outlets you have the V dot R, this V dot n, okay. So this term becomes positive, so that's why it has positive sign and negative sign at outlets and inlets, okay. Now depending on whatever the quantity you take, you'll have plus minus signs. I'll show you with the help of a simple example, okay, for linear momentum, okay. So let's apply directly to linear momentum. So for B is equal to mv bar, okay, or mvr, relative velocity you can take. Then let's see, this implies beta is intensive, which is just vr, okay. So v R actually. Let's see, for RTT, d by dt of mvr of the system, which is the set of particles, is given by summation. Now this m dot is just a scalar and beta is the quantity. Okay, so we can write m dot vr at out minus summation m dot vr at inlet. This is what you will get. Will you all agree with this? Because some of you have doubts why you should put plus sign, why you should put minus sign, what all this headache is coming. So we'll go in a detailed way, at least for this particular concept. And angular momentum, okay, it takes hardly 10 minutes, not bigger. Can you all understand that if RTT equation, I'm not deriving RTT equation as of now, okay, but if RTT equation is correct, for example, by some chance, then this gets valid. Yeah, correct. By some chance, if RTT is valid, if that equation what I have written initially is correct, okay, because of some reason, forget about it, then this should hold good. Yes, okay. Then in place of B, I have put linear momentum, so obviously beta becomes velocity. So this, if you write again, I'm writing all these equations in control volume frame of reference. So this is rate of change of momentum of the system, which is the net force acting on fluid. So net force acting on the fluid. So because system is my fluid particles, these are the things which are moving actually. Okay, so rate of change of momentum is net force. So sigma F on control volume. So fluid and control volume are in contact. So definitely by Newton's third law of motion, sigma m dot Vr in minus summation m dot Vr out. This is what you have. Okay, so this is the simple understanding. I'll ask you first, I'll tell you one result, and which many of you know generally. Then using this equation, I'll show you how that result comes up. Okay, let's do it that way. So let me see. All of you might have known this case. If there's a plate, for example, okay, if there's a plate and this plate is moving at some velocity v, for example, okay, or u, for example, then if some fluid jet is coming and leaving like this, let's say initially this jet velocity is v, and you have done the control volume, obviously the location where fluid and solid gets in contact with each other. So let's say this is the control volume. Okay, then when the fluid enters this, if you write everything in terms of this control volume reference, okay, this is my control volume. You all know that if this is x and this is y directions, positive x and positive y, Fx, the force exerted by this jet on this plate, is rho a v minus u whole square. Correct? All of you know this formula, is it? Yes. And if plate is not moving, obviously u is 0, so a v square, whatever you get. Yeah, every one of you know this, but of course people might taught you using different techniques. Many times people without understanding the RTT and all, they're happy to understand that formula very easily. Okay, but conceptually there's a mistake in those explanations. But still, let's see. You all know that for this is what you get. Okay, then let's now apply the equation what you have in this equation. Okay, so in this equation, this is a vector equation. So let's say you are writing it in the x direction. Okay, so by RTT, let's second. So by RTT, can I say sigma Fx on control volume is nothing but summation m dot v relative x at inlet minus summation m dot v relative x at outlet. Correct? I can write this. Now if you see the number of points where fluid is cutting this control volume, I can broadly divide it into three parts. One is this point, second is here, and third is here. So fluid is going in this direction, it's coming out in this directions. Okay, you know this. Now if you break summation of all the inlet points minus summation of all the outlet points, correct? Let's break this so that you can understand things clearly. Sigma fx on control volume is equal to, so if you take the inlet points, okay, this is the only inlet. At this inlet, whatever is the total mass that's going, the full mass is going, so m dot into, see, when you calculate this m dot in this Reynolds transport theorem, you have written VR, okay, rho v dA, n cap dot dA is normally rho v dA. So out minus in or in minus out? In minus out, because we are writing on the control volume, okay. So if you see in this equation, when you have the system, then outlet is positive, okay, system is fluid. Now if force acting on the fluid is F, force acting on the control volume is minus F, because fluid and control volume are in contact with each other, okay. So because of that, we have, this is for the fluid, so for the control volume you will have in minus out. Got it? Yeah. And one important point, when you write the Reynolds transport theorem here in this case, so this is mass based on the relative velocity, okay. So it is based on the relative velocity. So if you substitute here, okay, so first m dot, I'll write split it into more parts, m dot VR in the x direction at section 1 plus m dot, okay, so this is the only inlet, then rest all are outlets, so minus m dot VR x at 2 minus m dot VR x at 3, or maybe if you write all outlet summation, this becomes plus, okay. Then can someone tell me, at section 2 and section 3, is there any x component of velocity? At section 2 and section 3, is there any x component of velocity? No, obviously. So the relative velocity at x direction is zeros, okay. So that's why those two terms are zeros. Understood? Now coming here, m dot rho a into v minus u, this is the mass flow rate based on the relative velocity, because we are writing everything in control volume and reference frame. Now the relative velocity at section 1 is in this direction, and this direction is same as the positive x direction, so it's a plus sign first. Then what is the relative velocity? V minus u, so v minus u. That's how conceptually, if you do everything correctly, you will end up with this formula. Got it? It's clear to all of you? Did you understand? But see, people tell you F is equal to dm by dt and all, but it's okay, fair enough, but conceptually there is a small lag on that, okay, because if you apply force on me, you cannot measure the momentum change on some other body, okay, that's the idea. Okay, yes. Now similarly, if you calculate for the same case, you might have seen Fy is equal to 0, yes or no? Have you seen that? Fy is equal to 0 for that case? Yeah. So let's see how this Fy is 0. Sigma Fy, again the same equation. So sigma Fy on Cv is equal to summation at inlet minus outlet. So summation m dot Vr in the y direction at inlet minus summation m dot Vr y at the outlet. Okay, so this is what you get. Now let's see, at the inlet means at this point you have only one inlet, and here the velocity is purely in the x direction, so there is no y component, this is 0. Minus, now let's see, in this case m dot Vry at the outlet, so you have two outlets, section 2 and section 3, so m dot Vry at section 2 plus m dot Vry at section 3, correct? This is what you get. Understand something carefully, the mass flow at section 2 is half of the full mass which is coming into the control volume, and this m dot is also same. So can I say mass flow rate at section 2 and section 3 are same in this case? Because it's symmetric splitting. So m dot 2 is same as m dot 3. Okay, and this, sorry, excuse me. Then, so let's see, if you have this v r by 2 at this point 2, the velocity, because if there is no friction, if it's coming at velocity v minus u, it also leaves at velocity v minus u, and this velocity at v minus u is in this direction, and the positive y direction is also in this direction. So which tells you this is m dot by 2, the total mass flow rate which is flowing, half of that v r y is v minus u. Okay, because the fluid is leaving at velocity v minus u. Then at this point also the mass flow rate is m dot by 2 out of the full mass flow rate. V r y at section 3. At section 3 the velocity is in this direction, in the y direction. Okay, but is it positive y or negative y? This is the positive y direction, but this velocity is coming in the downward. So should it be positive or negative? It should be negative. Okay, so that's why this is minus of v minus u, and if you add this you will get 0, because both the terms cancel each other. Okay, so since both the terms cancel each other, you will see that sigma fy is 0, obviously. So this is the way how to apply the Reynolds transport theorem. What about gravitational force in the y direction? Generally it can accelerate the flow, but we are neglecting the gravity. Okay, because this splitting is not happening because of the gravity. The fluid is coming with velocity v, but this plate is moving with velocity u. So the effective velocity, how fluid moves, enters, here is v minus u. Okay. Did you get this? It's relative, right? v minus u में u का डायरेक्शन x है ना, sorry, v minus u में u का डायरेक्शन x है ना, यो 0, क्या हुआ, सॉरी, थोड़ा पूरा टाइप कर लो ना एक बार, ऑप्टिमाइज मत करना डाउट में. अच्छा, got it. You want to say it's v plus u, okay? But if bodies are not in contact and if the fluid is trying to enter the control volume, then definitely the difference in the velocities is what you have. Okay? Got it, guys? It's actually v minus u because it's relative, and by that time the fluid is entering the control volume, bodies are not in contact. Okay? So the difference is the relative velocity. Okay? I did not take u in y direction. I have taken v minus u to maintain the continuity, because continuity should hold good, right? v minus u में v axis, v y axis है and u x axis. No, both v and u are in the x axis here, you can see. Okay, don't get confused with the flow parameters. I have told you that this jet is moving in this x direction with velocity v and u. Okay, maybe if you observe vj, vp, okay, velocity of the plate, velocity of the jet. Maybe that's uv has created some confusion, but vj and vp if you take, then vj is the velocity of the jet, vp is the velocity of the plate. Okay, but both are in the x direction. Clear? His doubt is like, see, your doubt is normally we like this. That's what your doubt is, correct? Of course. Two, here I am assuming the fluid is coming at x component in the x direction and plate is also moving in the x direction. Okay, that's all. Fine. Yeah, DSFGH. So DSFGH, basically the line keywords. Okay. So anyway, if you look at the sigma fx, this summation is split basically from the Reynolds transport theorem. What about sine and cos? Everything is purely vertical, no? Here it's purely horizontal and it's purely vertical. Let's see if there is a vane inclined at some angle theta and all. Maybe in tomorrow's class I'll try to solve some questions which you can get them, okay? Where you have the vanes, you'll resolve the component sin theta, cos theta, all these things. Even in today's class we have some maybe, but we'll do them in tomorrow's class, okay? Chalo. Similarly, you can apply for angular momentum. So in this case, you will get the Euler's equation. For B is equal to R cos mv. Okay, so this is the angular momentum. So definitely beta. Yeah, basically in see, as long as the vane is rotating the flow, you cannot have components. Okay, by some source the flow should get rotated. Yes, so this gives you beta is R cos VR. Okay, so beta is R cos VR. Okay, thank you. So this bit, but anyway, we'll take some short break after we finish 8th chapter. Okay, this is 6th chapter. So maybe by 8th chapter we'll make it somewhere like 12:30 or 12:45 somewhere. We'll take some 10-15 minutes break. Okay, one short break, because 9th and chapters are very small chapters. Potential flow I'll give you some just basic introduction. Then compressible flows I'll discuss again in a bit nice way, because हर एक साल question आ रहे वहाँ से. Then lastly we'll look at hydraulic machines. Okay, we'll do it that way. In potential flows I don't teach the complete things, because we'll not cover the XE part today. Maybe we'll cover only the mechanical part. So then after we'll have like some extra sessions for XE after get mechanical. We have 2 weeks this time, so we got enough time. We'll do them. Okay. Yeah. Chalo. Let's see. Yeah. So this is beta. So if you have this beta, sigma, sorry, not sigma, derivative of R cos m v r bar by dt of the system is equal to, again, steady state, assuming steady state and all, assuming steady state. Okay, what is this emoji, this little fellow, Wi-Fi symbol on the head? What is that? I've been seeing these emojis for the first time, man. I know this love symbol Wallah. When I was teaching YouTube math, some people used to do that. Okay, fine. Mechanical Rockstar has come up with a new emoji. What is this? This is telling with a headphone and saying hi. Good. Playing, huh? Cool. Even I love to play. What to do? ये क्या है? Clock. Okay, man. Enough of emojis by now. Chalo. Let's solve these questions. Okay. So yeah, this is for the system. So this again can be written as summation m dot times R cos VR at the outlet minus summation m dot R cos VR at inlet. Okay, so this is for the system. Vortex motion important है क्या गेट एग्जाम के लिए? Normally yes, because काफी बार क्या होता है कि वो रोटेटिंग सिलेंडर्स वाला क्वेश्चन आता है कभी कभी, and more importantly they can ask you theoretical questions. Okay, so in vortex flows, which will take some time. So chalo, this is m dot obviously, and if steady state, summation of m dot out is equal to summation of m dot in. Okay, and about, so this implies this is net torque, correct? So this is the rate of change of angular momentum. So net torque, so sigma torque on control volume, like on the sprinkler, whatever, is summation m dot R cos VR at the inlet minus summation because I have it in control volume. Okay, so m dot r cos VR at the outlet. Okay, so that's the outlet. With respect to tornado spins and all, yeah, there are some theoretical questions as well in the past. Okay, so in this case, so about z-axis, sigma t torque on control volume about z-axis is summation m dot, because tangent and radius are perpendicular to each other, so cross product just gives the product of the magnitudes. So m r vw is summation at inlet minus summation m dot r vw at outlet. Okay, so this gives you Abhias batch of 1500 series K questions. दो बार enough है ना sir? 60 plus clear, yeah, enough. Okay, मत. So we have this as the talk. So let's see. Let us solve some questions now based on this. Then we'll go for one last part of applications of Bernoulli's equation. But उससे पहले एक दो questions solve कर सकते हैं. So let's see. Water flows through a circular nozzle. It's a question again from Frank M. White, obviously. So water flows through a circular nozzle and a mercury manometer of specific gravity 13.5 is attached to the nozzle. Okay, so to the nozzle there is a manometer. Water exits into the air as a jet and strikes a plate and splits it into two jets as shown in the figure. A force of 70 newtons is required to hold the plate stationary. Which of the following statements is or are correct? Assume, study frictionless 1D and neglect minor losses, of course. So what are the points? Exit velocity of the water in the nozzle. So first is, what is the velocity here at this point? Second, the mercury manometer reading H lies between. So you see, you need the concept of manometry, RTT and some other things if you need. So I'll give you 3.5 minutes. So try to solve this. So one thing, the velocity at this point, and what is the deflection H? This is the manometric deflection H. Okay, between mercury and water. Water at 20 has 1000 degrees, 1000 kg per meter cube. I'll display the options in the last 30 seconds, maybe, or last 1 minute. So the points of interest are the velocity here and this deflection. Chalo, do this. Okay, so let's solve these questions. Options, okay, fine. So I'll display the options. Get something. Okay, nothing. Got nothing from the options. Okay, AC. Okay, maybe let's see. So first, if you know this velocity, okay, so let's say if this velocity is known to you, then ultimately the force exerted is rho a v2 square, correct? And clearly the restraining force is F. So what we can have is for the plate to be stationary, okay, so for the plate to be stationary, sigma F on plate in the x direction whatever is 0. So this implies the F whatever you have is rho a of the jet into v3 square, v3 or v2, whatever is this. This is okay. One more slide. So v2 square, okay, rho a2 v2 square is what you should get. So rho a2 v2 square. So this is what you get. So now F is known to you, and so obviously you can get v2. Okay, so let's see how we can get v2 square. VC, AC, okay, fine. Let's see. So v2 square is equal to F by rho a2. So this can be written as 4F by pi rho d2 square. Okay, so this is what you have for the v2 square. So let's see, v2 is equal to 4 times. So what is the force which is required to hold that? 70 newtons, no? So 4 into 70 by density 1000 into pi into d2 square. So what is d2? d2 is 3 centimeters. So 0.03 square, and this whole power half. That's what we have. So this gives you v2 in some meters per second. Okay, so v2 is some meters per second actually. So let's calculate 280 by 1000. Anyway, this job is done. So 280 by 1000, so 0.28 divided by pi into 0.03 square. So this is the value, and take a square root of this. 9.951 meters per second. Okay, so that's the velocity. Water strike का है mercury नहीं, obviously. अच्छा, density 30,500. See, this is water. Okay, you can see this is water. Water is flowing in this. Okay, water is going and striking the, this plate, not the mercury one. Okay, so 9.951. So 9.95 is not here, obviously. So this is 9.95. So B is correct answer and A is wrong. Okay, then mercury manometer reading H lies between dash. So what is the mercury manometer reading? Let's see. So at this point, if you apply hydrostatics here, if you apply the hydrostatics here, then you call this points A and point B, for example, and this point is point 1 and this is point 2, for example. Okay, so till here, again, if you take this distance as x, so this OWGX cancels on both sides. So from manometry, PA is equal to PB. So from manometry, PA is equal to PB. So this implies P1 plus rho WGH is equal to P2 plus rho mercury GH. This is what you would get, correct? Because you see this fluid length gets cancelled, then this is water column and this is mercury column, definitely. So rho water GH and this is 𝐂𝐚𝐿, okay. But you don't know what is P1 and P2, okay. How do you get this P1 and P2 difference? That's the question, okay. So let's see. H is equal to P1 minus P2 into G by rho Hg, sorry, I think G should be in the denominator. So rho Hg minus rho water times G. This is what you get, okay. Now you know these two things, but you don't know what is P1 minus P2, okay. So let's see how do you get this P1 minus P2, or else, you know, if you take rho water common, then you have P1 by rho water G minus P2 by rho water G, this term divided with specific gravity of mercury minus 1, okay. Maybe I'll write it in the next part. So if you take density of water common, and if you keep it in the denominator, we have 1 by specific gravity of mercury minus 1 into P1 by rho water G minus P2 by rho water G actually here, okay. So this is what you get. Now how to get upon rho G? Yeah, of course, the same thing. Then how do you get these quantities? We can apply the Bernoulli equation, okay. So apply Bernoulli equation between these 2 points. Clearly it's a horizontal you know, pipe with a contraction. So definitely P1 and P2, if you apply the Bernoulli equation, P1 by OG plus V1 square by 2G is equal to P2 by OG plus V2 square by 2G. So this P1 minus P2 can be written as, so therefore H is equal to 1 by specific gravity of mercury minus 1 into P1 minus P2 can be written as minus V1 square upon 2G, okay. Now you know V2, we have calculated. What is V1? Let's apply continuity, okay. So A1 V1 is equal to A2 V2. In fact, D1 square V1 is equal to D2 square V2. So what is V1? D2 by D1 whole square times V2. So if you do squaring, okay, anyway, let's calculate V1. D2 by D1. So D2 is 3 centimeters and D1 is how much? D1 is 10 centimeters, okay. So this is 10. This is 0.3. So 0.3 whole square, 0.09 times V2. So 0.09 times V2 actually, okay. So this is the case, and V2 is known to you. So what is V2? 9.951. So let us save this into 0.09. So 0.895 meters per second. It's the 0.895 meters per second is the velocity of V1. 0.896 let's take, okay. 0.896. Okay, so that's V1. So let us substitute here. 1 by specific gravity of mercury. So density of mercury is 13, specific gravity is given 13.5 minus 1, 12.5 V2 square, okay. So what is V2? 9.95136. So 9.95136 minus 0.896 square upon 2 into 9.81. That's all. But this would be in meters, okay. This in meters, you can convert to centimeters. See, to solve this question, you need manometry, you need RTT, because you know OAV square, you need Bernoulli equation, and you need continuity equation. So these things, that's how some nice questions can be set, okay. Do this. So way of this subtracted from, okay. So let's see, where minus is 0.896 square, 0.896 square actually, okay. So this divided by 2 into 9.81, okay, 5, and 5 divided by 12.5, 5 divided by 12.5, 0.40, 0.400, so 40.0 centimeters, 40.05 centimeters, yeah. So that's the deflection in the manometer. So it's almost like 40 centimeters. Okay. Very lengthy? No. You see, this is not very lengthy. I have done steps bigger. That's all. Otherwise, 3-4 steps hardly. Okay. So 40 centimeters around. So which is somewhere in between. Yeah. This is not the case. D, B and D. Many of you told C is the answer. B and D are the correct answers. Okay. It's a very straight thing. B and D are the correct answers. Okay. So yeah, we have more questions, but we can do them tomorrow. But let's see certain things where you have applications of Bernoulli's equation. So applications of the Bernoulli's equation, of course. So you have the benchiometer, let's say, applications of Bernoulli's equation. Fine. So if you see, this is benchiometer, so definitely have a converging section, third and diverging section. But of course, in this diagram, it looks very unfair, to be frank. But in reality, you have the converging part more converging than the diverging section. Okay. So this is how a benchiometer looks in reality. Okay. So this is converging part. Then you have the third and diverging section. Okay. So once you have this, okay, so converging part and the third and the diverging section actually, then clearly we get the discharge of the benchiometer if here if the pipe diameter is A1, I mean D1, whatever. So this is D1 and this is the third, which you have D2. Then you have A1 A2 times square root of 2GH deflection in the manometer by OF minus 1 upon root of A1 square minus A2 square, right? So this is what you would get actually. Okay, so that's how we get the, so directly we कह सकते हैं ना, V is equal to root 2GH. V1 is because too small. V1 is generally too small in this particular case, but in reality we cannot neglect V1 always. Okay, here the diameter is almost like 1/3, so that's why things became simple. But in reality that need not be the case always. Diverging part की length ज़्यादा क्यों होती है? Can you explain once again in short? See, I'll tell you. Normally this is the flow direction, okay, upstream direction. Now if you have a higher cone angle, okay, if you have higher cone angle, then the convective acceleration of the flow in that part is high. Okay, so if the convective acceleration of the flow is high because of the flow geometry, then in this question it happens, okay, but normally it need not come. मान लो कि काफी कुछ क्वेश्चंस में रेंज काफी कम दिए थे, तो then it will be a hectic issue. Okay, so let's see if this is D1, okay, and if you have a higher converging part, means the nozzle in the converging section is very steep, okay, then it highly accelerates the flow in the forward direction, so it facilitates the flow. But whereas in this case if you have a higher diverging section, okay, in this case if you have a higher diverging, means if a sharp divergence is there, then definitely the pressure gradient will be adverse and there can be chances of flow reversal. So smoothly we elongate to the pipe diameter. Okay, so we know this, like applying Bernoulli's equation from the manometer, everything we do this. Similarly for orifice meters and also like the pitot tubes, we does the calculations. Okay, so in tomorrow's class, what we'll do, we'll see lot of applications of Bernoulli's equation basically. Clear? Like the orifice meter, if you see, again the streamlines will smoothen up like this, giving a location for the vena contacta. So this is vena contacta area. Vena contacta, and you can see like again if the deflection is h, here also you have q is equal to q actual is equal to CV into A1, it's not CV, sorry, it is coefficient of discharge. Okay, so CD into A1 A2 by root of A1 square minus A2 square into root 2GH, where H is the deflection again, so M by rho F minus 1. Okay, and this CD is nothing but CV into coefficient of contraction. Okay, so here we have CC square also here. Okay, so CC into this, so yeah, CC into AV, so CC into A2, correct. Okay, so this is what you would get, coefficient of, and everything has an analysis. Okay, again you can apply the Bernoulli's equation at these 2 points, like for example here and at this location of vena contacta, like in fact in this diagram it's wrong, so vena contacta should be exactly here. So if you look at the vena contacta, it looks something like this. Okay, so this is how you should have the vena contacta exactly at that point where you connect the manometer limb. Okay, so similarly we have the pitot tubes, lot of applications and number of applications where we'll solve some questions tomorrow, like in tomorrow, and also basically in the PYQ class we'll solve questions based on the pitot tubes, venturimeters and all things. Okay, so one thing which I would like to do at this point is this projectile motion, like the last part of this. Yes, so if you have a fluid jet, for example, okay, so this is a fluid jet, let's say, this fluid jet is going up at a velocity v and this is theta, then you should always measure any coordinate with respect to the point of projection as origin. Okay, so if you take this point of projection as origin, then ultimately you have x and y directions. So because of this x and y directions, then we have y is equal to tan theta into x minus g by 2v square cos square theta into x square. So this is the equation of the projectile. Okay, and if you do a horizontal projectile, like let's say if the angle of projection is 0, if theta is 0, this equation, this is the general projectile equation. General projectile equation, and for theta is equal to 0, you have, for theta is equal to 0, we have y is equal to minus g by 2v square into x square. Okay, so this is how we get the things. Water hammer in mechanical syllabus? No, not in gate syllabus. Okay, you have in XE, if they want they can ask you water hammering effect, but in general in mechanical it's not there. So this is the projectile if you have theta is equal to 0. So let's say if you have a tank, for example, where, okay, so there is some tank, let's say. Again, tomorrow we'll have questions on all these things, of course. So when you have the free surface of the water, and if you have an orifice here at this point, okay, so at this point if you have an orifice, and let's say if fluid is coming like this, okay, so fluid is coming like this, then clearly here you can calculate the velocity and you can calculate the range of the projectile. Okay, so you can calculate the range, and how do you get the velocity? By applying the Bernoulli's equation at this point and at this point. So generally when you have large tanks, this V1 is going to be very small. Like even in your home, this water filters, if you see, if you just open the filter, then what happens? Fluid comes up at very high speed from the tap, but compared to the liquid level in your this water filter will actually come down very slowly. Okay, so that's how this V1 can be approximated as 0, and if you apply Bernoulli's equation depending upon this height h. Okay, so if this separation is h, for example, or this is small h, for example, this is h minus h, let's say, and this is h, this is small h, then your V is square root of 2g h minus h from the Bernoulli's equation. Okay, and if you substitute in all these cases, like for example with respect to this point of projection, this coordinates are r comma minus h. Okay, so once you have the velocity, you substitute r comma minus h in this equation, you'll get what is the range. Okay, then if you want like maximal conditions, minimal conditions, you can do all these things. In general, for r max, these are one of the standard questions in some exams. So this h by h should be equal to 2. Okay, means this orifice must be exactly like the half of the capital H. If you are maintaining a level of capital H in the tank, then capital H by small h is equal to 2. So these things comes up, and the tanks and all basically from the continuity equations we work out. Okay, like the emptying of the tanks, each and everything. Clear? So we have this lawn sprinkler question which we'll solve tomorrow. I'll take this question for tomorrow, the Bernoulli's equation questions and all. So in fact you can maybe answer, before we go, answer this question: which of the following statements regarding a venturimeter is or are correct? Tell me. Emptying tank approach. Okay, I'll tell you. Fine. Okay, answer this question, then I'll teach you the emptying tank approach. But that's just based on the continuity equation anyway. I'll teach you. So enter the answers in this case. It's a MSQ. Okay, there are more than one correct options. In the direction of the flow, it consists of a diverging section, a throat, and a converging section. B, please be side. Yeah, okay. Now you can answer. A, C, and D. Correct. Okay, so basically in the direction of the flow, it consists of a converging section, a throat, and a diverging section. So this is correct. Okay, but this is wrong because first you don't have the diverging section, you have a converging section first. Okay, so statement A is correct. Then it used for flow measurement at a very low Reynolds number. Normally it doesn't have any limitations. Like in case of turbulent flows, we cannot use venturimeters very effectively, but as long as the flow is laminar, okay, and even if the Reynolds number is low, we can calculate the flow measurement we can do, and obviously is also correct. Pressure tappings means basically the manometric locations. Okay, the points where the manometer is connected will do just upstream of this venturimeter starting and at the throat. Okay, coming to emptying tanks approach, like which we can see. So if you look at emptying tanks, okay, Like for example, you see you have this tank, okay, and let's say here you got some orifice, or else let's say here time for emptying, no. So let's say some fluid is coming up, and let's say here you have so let's say this is the initial water level, okay. So this is the initial water level, for example, and this initial water level is H, okay. This area of the tank is capital A, and this orifice is of area small a, okay, and this tank is of area capital A. Normally people in aptitude and all, what we do generally, if you know the flow rate, then we divide total volume of the tank divided by the flow rate, you will get the time. But in reality that's not the case, because the flow rate keeps changing with time, because this velocity which is coming with which the fluid comes out changes, okay. So if you have this velocity v at this point, by mass balance, you see m dot in minus m dot out is equal to d by dt of mass inside the control volume, correct. That's what you have, okay. वेंचुमीटर में सर लॉसेस किस तरह से होते हैं, फ्रिक्शन in general, okay, because obviously venturometer is also having a solid fluid contact when fluid pass through venturometer, so there are losses, but there are no sudden expansions and sudden contractions at this point, so that's why we don't generally consider them, okay. Fine. So let's see, in this case, if you take this tank as the control volume, so if you take this tank as the control volume, for example, then let's see, this m dot in is 0, correct, because clearly you cannot see there is no mass which is coming in. What is mass leaving out? Minus density into pi by 4, or you can say A, which is this area, into velocity. So this is the mass which is leaving out, is equal to d by dt of mass at any point inside the control volume is density into volume, which is capital A into h, let's say, okay. So at any instant, this height is, let's say, h of t, for example, at any given point of time, so it is height h. So then if you cancel this density, ultimately v, so what is v? V is nothing but root 2gh at any given point of time, okay, because if you apply Bernoulli's equation, here the tank is open to atmosphere, here also it is open to atmosphere, so pressure term gets cancelled, then v1 is 0 again if you taking A to be very large, A being very large than A, then means generally you have a small orifice and you have a very big tank, so A is much larger. In that case, then v1 can be approximated to be 0. So if you take v1 to be approximate to 0, this v becomes square root of 2gh from Bernoulli's equation, okay. So if you substitute, minus A times of square root of 2gh is equal to d by dt of A can be taken out because that's the area of the tank which is constant, okay. So you can see minus A by A into square root of 2g into dt is equal to 1 by square root of h dh, that's all, okay. So now we can do the integration, okay. So you can do the integration now. If you integrate it, this A, capital A, root 2g, everything is constant. At time t equal to 0, this h is capital H, and at the time of emptying, this h is 0 because everything in the tank will come out, okay. So you can see, if you simplify this, minus A by A root 2g into this time integration gives you capital T, integration of 1 by root h is 2 times of root h, but if you do the integration, we'll get minus square root of h, okay. So then this 2, sorry, not 2, this minus and this minus gets cancelled, So you can see T is equal to this 2 can cancel this square root of 2. So root 2 by G A by A into, so this is h power minus half now. So we have root h. That's all in this case. Okay. So this is how we work out the time. Basically, the velocity keeps changing because of the change in height actually, and that's how you get the time required for emptying the tank. Okay. Now if they give you this capital A, small a, all these diameters, you can put the numbers and do the simplifications. Okay. Yes. Fine. Then let's go to the 7th chapter, which is the incompressible internal viscous flows. Okay, this is again one of the biggest chapters, like 4, 5, 5, 6, 7 are the big chapters. So after this, the rest of the chapters are small, no issue. Okay, we'll finish somewhere between 2 to 30. Okay. Clear to all of you? It's okay. I see every day I'll rest maximum. Okay, but if you're understanding the things, that's okay. Are you all okay? Let's have some water meanwhile. Are you all okay? Yes. The exact solutions. I taught you only 3. Okay, I generally teach 4 sometimes. The one reason why I don't come up with a PPT, like PPT in the sense like most points I write with hand, is because when I write, you will also get time to write. Okay. Clear? Because now if I just put it on slides and just put the points, then again it will be like just an information for you. But if I write points, then you will also get time to write and you can have some benefit out of it. I couldn't sit any longer. But definitely people who does it will definitely have benefit. Okay, just a second. Yeah. Fine. Let's finish this chapter, then I'll give you break for 15 minutes. Okay. Hi Prakash Mahakul. After this chapter, I think we have taken break at 9 o'clock now. So 4 to 9, 4 to 8:30, so 4.5. So we started at 9. So let's see, maybe it's 12 now. So till it will take just some 40 minutes maximum. Okay. So 3 solutions on this, so 40 minutes. So then I'll give some break. Okay. Maybe let's say 12:40 we'll take, then some 15 minutes break. Then I'll start at 1 o'clock. Okay. Then hopefully by 2:30 or 3 we can wind up the things, because turbulent flows, dimensional analysis, these are very small chapters in fact. So we can do the things. Okay. Hello. Let's start. So again, this Navier-Stokes equation is again the momentum equation. For viscid flows. Okay, so you take viscosity into the picture and we model the viscosity, something like this. Okay, so we model this viscosity minus p times of I, identity matrix, plus 2 mu epsilon plus lambda times divergence of v I. Okay, so this is how we modulus. And normally for incompressible flows this term becomes 0. Okay, boundary layer theory cover hoga kya aaj pakka? Why not? We'll finish full syllabus, man, before this video ends. Okay, after this we have only like, yeah, almost like 6 chapters, but after out of them 4 chapters are very small chapters. Okay, maximum it will take only 1 hour 20 minutes for finishing those 4 chapters. Okay, fine. So let's see, this is how you have the stress distribution, and this is the Stokes hypothesis. This is called as the Stokes hypothesis. Okay, Stokes hypothesis. So minus pi plus 2 mu this strain rate tensor plus lambda times divergence of V into I. Okay, normally I'll just show you the brief of this derivation, which, because some of you might be looking at it for the first time, the Navier-Stokes equations. Yeah, here you can see where I have done the Navier-Stokes equation. So basically we have taken a small element of fluid in this case, and then analyzing the fluid motion. Okay, so we have taken the stresses in the x direction, then applied the Cauchy equations. Okay, then in the Cauchy's equations we have seen what are the constants we have. Okay, symmetricity. Then we came up for the Stokes hypothesis, where this is the stress variation which I have written, and finally after a bit of understandings, okay, so this lambda everything if you do, finally you will end up with this equation. Okay, so this is in the x direction in the vector form. This is the equation we have. Okay, so minus del p rho x bar mu del square V plus lambda plus mu gradient of divergence of V, all these things. Okay, so this is the final Navier-Stokes equation, and many times people blame this poor viscosity guy, but this is not the guy because of which this equation is solvable. It's actually because of this. Okay, so this is the actual equation. It's a bit of derivations and all which are involved, which I'm not doing right now, but this is the actual Navier-Stokes equation. Okay, and normally there is an approximation that lambda value is minus 2/3 times mu, but in general this minus 2/3 times mu, because this equation is valid for both compressible and incompressible flows. Okay, but in reality this, when you go for compressible flow regimes, okay, this lambda is equal to minus 2/3 times of mu doesn't hold very, positively for experimental results. Okay, so that's why I generally try to keep this in terms of lambda. So minus del p plus mu del square V. This is a simple equation again. So Navier-Stokes equation, if you write once, you have rho x, this is of the fluid, minus gradient of p plus mu into del square V plus lambda plus mu gradient of divergence of this velocity vector is equal to rho times dv by dt. That's all, which is acceleration. So this is the full Navier-Stokes equation actually for any flow. This is valid for any flow. Okay, so in reality, in general, this lambda, second coefficient of viscosity, is minus 2/3 times mu. Okay, so that's why many times when you add this minus 2/3 plus mu, you will see plus mu by the here. Okay, in some books like Frank and White and all, you can see this. So you can have lambda plus mu, of course. So lambda plus mu gradient of divergence of this velocity is equal to OF into acceleration, but in general for incompressible flow. Okay, so this term is 0 for incompressible flow. For incompressible flow actually here. Okay, so if you have this as incompressible flow, then we have only left with these 3 terms and OF, which is dv by dt. Okay, now let's see, we will apply this equation to solve some simple flows actually. Okay, but of course anyway, not the derivations right now. So if you look at the case of a co-ed flow, okay, In fact, this distance is very small, but I'm just putting them very separated. So this is h spacing. Then if you move this plate at a velocity u infinity, for example, okay, and this is the y direction, x, okay, and z maybe forward, then in this case, if you look at the velocity profile, so firstly here in this equation, so if you see this equation, basically rho x bar minus del p plus mu del square v is equal to, plus mu del square v is equal to rho dv upon dt actually in this case, okay. And you will see, since you have only u, and that u also has the velocity only in the change in y direction, like for example if you see assuming 1d all this stuff, you will finally end up with this fully developed flow, okay. Then v equal to 0, w equal to 0, when you do all these things, okay, so finally you will end up with the pressure balance and the viscous balance actually, okay. So in this flow, pressure force balances the viscous force. Viscous force. And if you solve the Navier-Stokes equation, you will end up with the velocity profile u by u infinity is y by h plus alpha times y by h into 1 minus y by h actually, okay. So this is the velocity profile. Clear? This is the velocity profile, okay. So, and what about this alpha? That's the question now, because y axis is very clear, your y is in this direction, okay, your y is basically in this direction. So what about alpha? Alpha is h square by 2 mu u infinity into minus dp by dx, the pressure gradient, okay. So this alpha is called the non-dimensional pressure gradient. Non-dimensional pressure gradient actually, okay. So let's see, if you have this non-dimensional pressure gradient, then depending on this value of alpha being positive or negative, you have a lot of velocity profiles in between, okay. Normally the intuition tells you that if you have a zero velocity, like for example if you fix this plate, of course you can fix this and you can move this, whatever, one plate fixed and one plate moving, okay. So it's called coed flow. And in this case of non-dimensional pressure gradient, of course, so if you try to look at things where this is alpha, so if dp by dx is positive, okay, then this alpha is negative. If dp by dx is negative, which is generally the favorable pressure gradient case, then alpha is positive. So depending upon that, we have the velocity profiles. I just want to ask you one more thing. If here the velocity is 0 and here the velocity is u infinity, and it's a viscous fluid in between, so you have some viscous fluid in between all over, at any location between this y equal to 0 and y equal to h, so this is y equal to 0 and this is y is equal to h, okay. So between y equal to 0 and y equal to h, can you have a velocity which is more than this u infinity? U infinity is the velocity of the top plate, okay. So if you have the top plate, then can you have any velocity which is more than u infinity in between? Is it possible? Velocity can be max in between u infinity, yes, correct, okay. So velocity can be maximum, it can be there. So basically you can have a velocity which is more than u infinity in between, okay. Mathematically you can show that using derivatives and all. So in reality, if you see, so if you have this flow where you have u infinity, okay, then if you take a section, clear? So this is y, of course. So if you have this y here, then at alpha is equal to 0, you have a linear velocity profile. Okay, so this corresponds to alpha equal to 0. You have linear velocity profile where the velocity here at this point is u infinity. Okay, and here this is 0, of course. So clearly in this expression, if you put alpha is equal to 0, then u by u infinity is just y by h, which is a linear velocity profile. Okay, and if you have alpha being positive more than 1 and all, you will see the velocity profile is something like this, which means the velocity can be more than u infinity. Okay, so u can be greater than u infinity for 0 less than y less than h. Okay, so some layers can travel at more velocity. Similarly, if you look at this is alpha equal to say 2, for example. Okay, similarly alpha equal to 3, you have this velocity profile. Alpha equal to 4, you have this velocity profiles. Similarly, when alpha goes to negative, okay, you will have the velocity profiles something like this, things like this. Okay, so this is alpha equal to -2, -3, things like that. Okay, so alpha equal to -3 has a peculiar speciality. For alpha is equal to -3, discharge at a section, net discharge at a section is equal to 0, of course. Okay, so alpha is equal to -3, you will see the net discharge at the section is 0. Like for example, if you see q, okay, u infinity w into h, where w is width of the plates perpendicular to the board. So w, width of plates perpendicular to board, then this has half plus alpha by 6. Okay, so this is the discharge in this case. So this is the discharge. So if you put alpha is equal to -3, means if you set the conditions h, pressure gradient, in such a way that alpha becomes -3, then at that particular section the net discharge is going to be 0. How you can have a discharge going to be 0? Like if you see alpha is equal to -3 in this case, maybe I'll draw a little convincingly so that you can see. So till this point it has the flow in the backward direction, and in the top part flow has in the right direction. So there can exist a case where net flow across the section can be 0. Okay, and once you have the velocity profile, you can calculate what all you wanted. Like for example, if you have the velocity sorry, if you have the velocity profile, then you can do what all you want. You want to calculate wall shear stress, you can do this dou u by dou y. Anyway, u is changing only with respect to y, so du by dy at y is equal to 0. Okay, so you know the velocity profile, so you can calculate whatever you want. Okay, then the skin friction coefficient, which is tau w by half rho u average square, you can calculate u average. Discharge, you calculate the discharge divided by the flow area w into h, so you get u average. So you can do all the things if you know the velocity profile. Okay, so solving that Navier-Stokes equation to get the velocity profile is the major crux part of this complete thing. Okay, fine. Is this clear to all of you? Like how do you calculate discharge? Integral 0 to h u into dy w. Okay, that's all. Yes, so let me see whether I can give you one question based on this. Solve this question, I'll give you some time. Okay, so neglecting body forces, pressure at the location x comma y, pressure at the location x comma y. Okay, so 6 meters comma 8 meters. So solve this question, I'll give you maybe something like 3 minutes. Okay, simple profile. So 2.5 minutes you take. Okay, so solve this. It's U average. Okay, yeah. It's okay. Yeah, just keep studying. Okay, 75 kilopascals maybe. Let's check it up. Solution. A rotational velocity field in an airflow is given by V is equal to A y I cap plus B x j cap. Okay, so anyway directly we can put the things. So 10 y I cap plus 20 x j cap. Okay, then air density is 1 kg per meter cube. So they want the air density to be 1 kg per meter cube. Pressure at this location is 0, 0. Okay, then sorry, at this location is 100 kilopascals. 100 kilopascals. Then neglecting gravity, pressure at this location 6 meters, 8 meters is dash kilopascals. Okay, so let's see. Let's apply the Navier-Stokes equation. Applying Navier-Stokes equation. So rho x bar minus del p plus mu del square v is equal to rho times dv upon dt. Okay, so clearly there is no way mentioned about the viscosity, so let's delete this. Okay, because nothing is mentioned about the viscous effects, so you delete this. Then neglect gravity, so neglect this as well. So del p is equal to, and rho is 1, so this density is 1, you can take. So del p vector means this pressure gradient is minus dv upon dt. Okay, so how can we do this? V is 10yi plus 20x j actually. Okay, so 10yi plus 20x j, right? So let's see the acceleration. Acceleration is equal to dou v by dou t, no terms, plus v dot del. So v dot del operating on ui plus vj or let's write the profile directly. 20 or 10yi plus 20x j. Okay, so then the acceleration vector is v dot del. So v dot del is u into dou e by dou x, so 0 plus v into dou e by dou y, which is 10. Okay, so this I cap, let me do step by step. Okay, why to rush so much? So ax is dou e by dou t u into dou e by dou x plus v into dou e by dou y. Good. Okay, ay is dou e by dou t u into dou e by dou x, so 10y into 20. Good. Okay, plus v into dou e by dou y, that's all. So this is 200x and this is 200y, of course. Okay, so this gives you minus 200 times of xi plus yj. Okay, so minus 200 times of xi plus yj. Clear? So let's see, 200x plus yj, of course. Then the pressure gradient dou p by dou x I cap plus dou p by dou y j cap is minus 200x I cap plus minus 200y j cap. Okay, so this is what you get. So if you simplify, dou p by dou x is equal to minus 200 x and dou p by dou y is equal to minus 200 y. Okay, so then definitely if you see the case, you have p is equal to, if you solve these two equations, minus 200 xy plus some constant, that's all. Okay, so this is the expression for the pressure if you just solve the partial differential equations, because you see, if you differentiate this with respect to y partially, you'll get this is like minus 200 x plus y. Okay, let's do minus 200 x square plus y square by 2 plus constant. Good, this is what the solution is. Okay, or else you can see 100. So p is equal to minus 100 x square plus y square plus some constant. This is what you have the final pressure distribution. Okay, because if you differentiate with respect to x partially, minus 200 x, that's all. Okay, and if you differentiate with respect to y partially, minus 200 y, that's all. Okay, constant is 0. Now they have given you some condition at pressure to get this constant c. What is the constant c? They have given you 100 at origin kilopascals. Okay, so if this is 100 kilopascals where x and y has, so let's see, at origin p is equal to 100 kilopascals. So this implies your value of c is 100 kilopascals. Okay, c is 100 kilopascals, but x, y, everything is in meters. Okay, so if x, y, everything is in meters, c is given in 100 kilopascals, so this is 10 power 5 pascals. Okay, then let's see at the point 6, 8. Okay, so p of 6, 8. So if you simplify this, p of 6, 8 is equal to minus 100 times of 6 square plus 8 square plus this guy is 10 power 5 pascals. Okay, so this is 100 into 100 is 10 power minus 4, so minus 10 power 4 plus 10 power 5 minus 10 power 4 plus 10 power 5, so 10 power 5 minus 10 power 4, if you do 90,000 something, no, let's do it. Ten power 5 minus 10 power 4, so 90,000. Yeah, of course 90,000, but this is negative. Okay, so 90,000 pascals. So p at the location 6, 8 is 90 kilopascals. That's all. Okay, that's what we have. 90,000, so 90 kilopascals is the pressure at this location. nearest integer. So it's 90, straightforward. Okay. Many times people mess up with the units here. Okay, they'll just put as 100, forgetting that this is in SI units. Then your answer will go wrong. Okay, you have to be careful with the units. It's a simple question. Basically, acceleration is known, and looking at these two, you should be able to solve the question, solve the pressure function. Okay. Clear to all of you? Then let's see. So plane Poiseuille flow. So basically have two plates and both are fixed. Fine. So you have both the plates. Y equal to minus h, y equal to plus h. Okay. So let's say the spacing is 2h. So if the spacing is 2h, I calculated in Cartesian system and made mistake. Yeah, I understand. People does some mistakes with the units especially. Okay. So in this case, I choose my comfort coordinate system as here, horizon x, y. Okay. And so again, assuming fully developed 1D flow, u is changing only with y, all this business, you will see the velocity profile u. Hey, just a second, my fingers are touching the board unknowingly. However, let's see. U is equal to h square by 2 mu minus dp by dx into 1 minus y square upon h square. So this is the velocity profile in this case. Okay. So at y is equal to h, ultimately this velocity becomes 0, because you see y equal to h, you will touch either this plate or this plate, and at both the locations, if y equal to plus h or minus h, this velocity becomes 0 actually in that case. How many people are live? Let me check once. How many are enthusiastic for gate? Okay, good. Chalo, let's see. So this is u, h square by 2 mu minus dp by dx into 1 minus y square by h square. Okay. Then if you check this, u max is at y equal to 0, obviously. Okay. And you will see the relation u max by u average is equal to 3 by 2. Okay. So don't use too much of brain to remember whether it's 3 by 2 or 2 by 3. Okay. If you're at maximum by minimum, it's 3 by 2. If you're at minimum by maximum, it's 2 by 3. I mean average by maximum, it's 2 by 3. That's all. Okay. And again, so here you'll see this skin friction coefficient or the fanning friction coefficient here, you'll get 16, not 16, sorry, here I think 24 by RE, 18. Just a second, guys. Let me borrow some points from my notes. Internal flows 2. Okay, maybe somewhere here I have started. All these questions we have solved. Okay, so this is the case. It's 24 by RE as far as I remember. So solving this equation, see, this is how you get the profile. Okay, after solving the Navier-Stokes equation with some boundary conditions and all, you'll get that. But the skin friction coefficient is 24 by I. Yes, good. So you'll get the skin friction coefficient as 24 by Reynolds number in this case. Okay, and discharge. If you want discharge, then obviously you can do Q is equal to U average into 2h times of W, and so where W is width of the plates. Width of the plates actually here. Okay, and U average is nothing but 2/3 times U max. And what is U max? H square by 2 mu minus dp by dx into 2hw. So you can see this will cancel up this 2 and 2 will get cancelled maybe, or else this 2 gets cancelled. then you have Q is equal to 2/3 into h cube W by mu into minus dp by dx. So that's how you can convert the things. Okay. Yeah. Anyway, this is, in fact, when I'm writing these things, it looks very simple that I'm just writing these steps, but in order to derive them, you need a lot of effort. Like I have shown you in my full notes. Like you can see the skin friction coefficient or the fanning friction coefficient calculations. Then this numbers 24. In case of flow through pipes, you'll get 16 by Reynolds number. So you have a lot of things. Okay. Fine. So next, let's go to the last part of this chapter, which is Eigenpoiseuille flow. Basically, all are derived from velocity profile. Yeah, of course. The wall shear stress, everything is derived from the velocity profiles. Okay. So that's why you not see. You will observe that dou P by dou X is constant actually. Okay. Means the pressure gradient is constant. Means pressure varies linearly. Okay. That's one thing you'll understand when you are solving the Navier-Stokes equation. The second thing is the velocity profile, obviously. Okay. So once you get the velocity profile, then you can do a lot of things. Okay. So this is flow through a pipe basically. Hello. Sorry. Land up Sherpa. Let's see if you have a pipe. Okay. So if you have this pipe, for example, okay, of radius r. Okay. So this is of radius r and z is this direction, let's say. Then the velocity profile in this, obviously that changes with radius. So this is given by r square by 4 mu upon minus dp by dz into 1 minus small r square by capital R square. The profile comes very similar to that of the Eigenpoiseuille flow, but of course it's also the plane Poiseuille flow. So this term looks very similar. This constant changes in this case. Okay. And you can see Vz max Z R is equal to 0. That is at center. Okay. And you'll also figure out something, that V average by V max in this case is half. Clear? So if someone asks you to calculate discharge, Q is equal to V average, which is half times V max, and V max is at small r is equal to 0. So this is V max. So half into V max gives V average into pi r square. So this can give you the flow area, of course. And then you can cancel up terms what all you want. You can calculate the wall shear stress, which is minus mu into dvz by dr at r is equal to capital R. Okay. So that's how we calculate the wall shear stress. Similarly, the skin friction coefficient in this case would be, or the fanning friction coefficient is 16 by Reynolds number. Okay. And if you have 16 by Reynolds number, then the friction coefficient, fanning friction factor is 64 by Reynolds number. Okay. So this is fanning friction coefficient. Okay. And sorry, so dash is friction factor, F is equal to 4 times Cf, and this is 64 by Reynolds number. So that's what you get. Okay. And so obviously then head loss, pressure loss, everything, this head loss in a pipe like 32 mu V average L by rho G D square. Okay. So all these things are very familiar with the series parallel combinations, everything. Okay. Like everything has a simple derivations, not a very hectic derivations, of course, but these formulas you keep using many times in and out. like solving the questions. Yeah. So 32 mu L by OGD square. Then if you have parallel combinations, okay, and series combinations of pipes, then how to tackle this head loss? Okay, so in case of series, this HL is summation of head loss in all the pipes. In parallel, HL is same in all possible parallel paths. In all the possible parallel paths, you'll see the things are same. Okay, and if you want power, like let's say if you are facilitating a flow of a fluid through a pipe, then definitely because of the friction between the pipe and the fluid will actually lose some energy. Okay, so if you want to transmit this fluid from one point to a very larger point, then you should keep pumping the fluid. Okay, means you should keep supplying the power. So what is the power that you need? So power required to pump the fluid A is equal to rho QG into HL. That's what. Okay, because head loss is per unit weight of the fluid. So if you multiply with mass flow rate into gravity, then you'll get the power transmission. Okay, so these are the salient points majorly which we use when we are doing flow through analysis for pipes. Okay, and normally I would like to just teach one interesting thing here. We have something called momentum correction factor. Momentum correction factor, and so this is denoted with beta normally. Okay, and this beta is momentum per second m dot v based on actual velocity by m dot v based on average velocity. Okay, based on average velocity, and in case of m dot v, if you try to simplify the results, you'll see for laminar flow this is 4 by the batteries are out. Okay, now I hope it's audible. Okay, it's audible now. Battery also need food. Correct. Battery khatam. I've replaced the cells. It's okay. Yes, fine, it's okay, no issues. Okay, so anyway, alpha is equal to 2. So normally I'll just show you again some part of what we have done. So this is the Navier-Stokes equation in polar coordinates, and we solve normally in the class. Okay, where we'll get the velocity profile, parabolic, everything. The calculation, the derivation of this, not derivation but a simple analogy of Darcy-Weisbach friction factor. Okay, and pipes in series, parallel, all this stuff, and some questions, of course. Okay, correct. So this is the basic idea of the conversion kinetic energy correction factor. Okay, so holiday kar dijiye. I'll give, definitely. We have some I think 4 more chapters. We'll just slightly finish this. What kind of numericals will come in this topic? Yeah, definitely we'll solve some numericals tomorrow, but for today if you want to solve one numerical, then I would like to give you one question. Yeah, solve this question. Two minutes. Okay, it's a simple question you can solve. I haven't studied these derivations. Is this important or I leave? No, right now you need not do this, but let's say in some places, if they ask you, like if you especially go for some MTech not MTech but PhD interviews and all, they can ask you. In MTech interviews they can ask you little things, not very deep things, in-depth things. Just make some formulas and keep revising Dear Sharma. Okay, that will help you. Piping engineer, generally it's like one of the best piping engineering courses is available in IIT ISM. I mean ISM Dhanbad, of course. Okay, IIT Dhanbad now. So these guys has piping technology and it has good. No, it's a really good piping course in India. Okay, so let's see. Solutions. In a pipe of radius r is equal to 0.125 meters, a fully developed laminar velocity profile is defined as, of course, the velocity profile. The pressure gradient dp by dx is -1 megapascal per meter. Okay. Mu is the dynamic viscosity of the fluid. R is the radial position from the central line. If flow rate through the tube is 1000 mm³ per second, so Q 1000 mm³ per second. Okay, so which means Q can be equal to 10³ or 10 power minus 6 meter³ per second. Okay, you want viscosity, fine. So Q is equal to, radius of the pipe is also given 1/8 meters. So Q is equal to average velocity, which is like half into maximum velocity, r square by 4 mu minus dp by dx into, so half into maximum velocity into pi r square. That's all. Okay, so now you need mu, of course. So mu is equal to pi r power 4 minus dp by dx. Okay, so pi capital R power 4 pi capital R power 4 into minus dp by dx by 8 times q actually. Okay, so 8 times q. So let's simplify. Pi into this radius 0.125 power 4 into 1 megapascal per meter, so 10 power 6 pascals by 8 times q. So what is q? 10 power minus 6. Okay, so this is 10 power minus 6. So looks like it's a very heavy viscous oil maybe. So anyway, let's see the mu. In this case we don't know what is this oil, but let's see. 1 megapascal per meter. Okay, very huge pressure drop. Maybe it's like a very small capillary kind of tube maybe. So anyway, let's do this. Pi into 0.125 power 4, 0.125 power 4 into pi. Okay, so this is the value, into 10 power 6 into 10 power 6 by 8 into 10 power 6. Such a big viscosity. Which fluid has this big viscosity? Somewhere jugaad has happened. I think this is meter cube, 1000 meter cube per second. But this is to 10 power 9 liters. A very heavy discharge. Somewhere something has happened, guys. Otherwise, the values don't come this range. But just for the sake of setting the question, r square, not r power 4, but r square into r square. No, total r power 4 is what you have. Average velocity into flow area. Okay. So something has happened here somewhere in the data. Maybe this question I think I have taken from one of the books again. So let's see. In case of capillary tube, this can hold good. If this is mm, 0.125 mm, let's say, then 0.125 mm if you keep, then this would be 0.125 mm if you have in small capillary cases and all. So 0.125 into, so 125 into 10 power minus 6 whole power 4. Okay, so now let's calculate this. I think this is mm. So 125 by 10 power 6. Okay, so this value power 4. Okay, this into 10 power 12 into 10 power 12. So that value into pi divided by 8 into pi divided by 8 into pi divided by 8. So still somewhere units was wrong. Okay, but don't worry that this is the way of solving this question. Okay, I think somewhere the units has been messed up in the question framing. So otherwise normally mu will come very low. Okay, yeah, इतना कम नहीं आएगा normally क्योंकि this is a pipe of radius and some liquid or something is flowing. No, in this the dynamic viscosity of the fluid, even dynamic viscosity won't be very small. It will be small but not very small as this. Okay, so some units jugaad has happened. Fine. So we'll go for the next chapter, external viscous flows. So we'll take some break till 1 o'clock. Okay, so 12 minutes we'll take break. I'll have some water, relax. Then we'll start at 1 o'clock this boundary layers. It will take almost like 45 minutes again for revising. Then we have the small chapters. Okay, where majority of the things gets finished. Okay, so class resumes at 1 AM. Okay, so some 12 minutes break. Meanwhile, in these 7 chapters, if you have any doubts, you can ask me in the chat box. Okay, okay, fine then. You have one matched out. Yeah, you can ask me. No issues. Dimensional analysis भी करेंगे ना? Yeah, definitely, why not? Match doubt, yeah, you can ask Sharma. So if possible, sir, then please tell the 3 to 4 formula of vector calculus such as divergence of curl, 0, etc. Okay, okay, got it. कब तक चलेंगे ये? मुझे लगता है कि 3 बजे हो जाएगा. Because it's already 1, 10 minutes to 1. मुझे वेंचुरीमीटर की वर्किंग नवी समझ में आई थी सर. Is the Stokes theorem and Gin's theorem same? No, they are different. The venturimeter will connect it in between the pipe. Okay, so because of that, then when fluid is flowing to the venturimeter, okay, because of the manometer what you connect, you can calculate the velocities by which you can calculate the discharge. It's a direct measurement you can do for venturimeter flow measurement. Okay, so let's start. Fine. There are some comments, right? So this venture limit I have cleared. Green's theorem and Stokes theorem, it's okay. And just a second, guys. This chart is again disappeared. Yeah. Okay. So type in the chat box. Come on, guys. Type in the chat box. So shall we continue? Yes. Everyone. Yeah. So let's continue. But this board is not responding. I think you can see the lag, no delay. Sure. Anyway, introduction to the boundary layers. Thank you, Adarsh. Good night. Yeah, of course. Good night. Chalo. Let's start. Let's continue the sessions. Okay. But like I think it will take hardly almost like next. I don't say the time because I think I'm not able. I think I won't be able to finish that by that time. Okay. Chalo. Let's continue. But anyhow, we'll learn some concepts. Okay. We'll quickly revise the things. So boundary layers, like in general, if you have the flat plate, okay, then you see as x increases, horizon x and y, okay, so it will take more time than thermo. Obviously, compared to basic thermo, it's a very big subject, no, fluid mechanics. So chalo, let's see. Introduction to boundary layers. So as x increases, the wall shear stress keeps decreasing, okay, and as x increases, if you have the boundary layer thickness at this section, if you have this as delta, okay, so if you have this as delta, then delta increases, okay, and wall shear stress decreases, of course, which we can explain physically too, because of this plate being effective only in the beginning part. So after that the flow gets slowly retarded. Then let's see. So as x increases, this delta is also increasing. So if you look at the Navier-Stokes equations, normally in the x direction, you have u into dou u by dou x for v into dou u by dou y is equal to minus 1 by rho dou p by dou x plus nu times dou square u by dou x square plus dou square u by dou y square. Okay, so this is the x momentum equation, obviously, and the y momentum equation is, of course, we are looking at steady boundary layers. Okay, so you have u into dou v by dou x plus v into dou v by dou y is equal to minus 1 by rho dou p by dou y plus nu times of dou square u by dou x square, sorry, dou square v by dou x square plus dou square v by dou y square. Okay, so in general, if you see, this dou square by dou x square terms would be much less as compared to dou square by dou y square terms. Okay, normally if you do scaling analysis, you can get all these things. So these are the equations which are to be solved. Okay, but in reality, these equations need not be solved for the complete flow field. Because this, thank you, Kuldeep sir. Hey, Kuldeep sir is up. Hello Kuldeep sir. All of you say hi to our Kuldeep sir. He's on live. He's your information king now. He gives so many updates every day just after the official launch in any website. So all of us, let's say hi to Kuldeep sir. Hello Kuldeep sir. Fine. So good. let's see. So this is the x momentum equation and this is the y momentum equation. Okay, so now if you look at the scaling analysis, so scaling has a very high power where without even solving any of the equations you can still figure out what's important and what's not important. Okay, so you will see from the scaling analysis, if you work at boundary layers, especially where if this is length L, okay, and you have the slender boundary layers, in fact, so this is delta versus x. Okay, so origin x and y, of course. So normally these are called slender boundary layers where delta is much less than L, of course. Okay, so if delta is very less than L, you'll see this u scales to, if fluid is coming at a velocity u infinity, which is the free stream velocity, and infinity generally subscript is denoted for free stream conditions. Okay, so u infinity is the free stream velocity and P infinity is the free stream pressure. Okay, so this is the free stream pressure actually. Okay, so then this u can be scaled to u infinity, then x scales to L, y scales to delta. Okay guys, in many books, especially in some local university books I have seen, they'll make this assumption and they'll scale y to L, which is wrong. Okay, scaling will tell you the order of magnitude, and this y scales to delta is a very appropriate scaling actually. Okay, but if you scale this to L and if you make this assumption delta very less than L, which is blunder, okay, all your results will go wrong. Clear? So then from continuity equation you'll see y can scale to u infinity delta by L, so that's why this v is very small compared to u. Okay, this can be obtained from the continuity equation, and p scales to rho u infinity square. So if you perform the scaling analysis, then you will observe one fantastic result. Out of these two equations, this equation completely gets eliminated. Okay, means since v is very small compared to u, this full equation, when you try to couple it with this equation, you'll get 0. Okay, thanks. Okay, yeah, you're welcome, Aditya. So on scaling, you will see dou p by dou y is equal to 0. Okay, and this is for any boundary layer. It can be flat plate, not a flat plate, whatever you take, this is always definitely 0. Okay, and if dou p by dou y is equal to 0, then you also have the x momentum equation. Now clearly, if dou p by dou y is 0, that this implies pressure, or else you can see if you have y axis like this, then there is no pressure difference at all these points, the pressure is same. Okay, and in the x momentum equation you'll see u into dou y by dou x plus u into dou y by dou x plus v into dou u by dou y is equal to, so this tells you pressure is only a function of x. Okay, so which means you can write dou p by dou x same as dp by dx actually. Okay, so if you write this, then you will see you will get the equation as minus 1 by infinity dp by dx plus nu times of dou square u by dou y square. This is the equation which you will leave. Okay, which you get actually here. So after you perform the scaling analysis, you will figure out that this is the equation, and on scaling you will see delta by x is proportional to or is of the scale 1 by root rex. This is what you will figure out from the scaling analysis. Okay, so whatever the velocity profile you take, as long as the flow is laminar, okay, turbulent boundary layer analysis be pada denge please. Yeah, definitely. Okay, so we'll see. So delta by x is scale to 1 by root rex, and that's why if you do any laminar boundary layer analysis for whatever the velocity profile you take, always you will end up with delta is equal to some constant into x by root rex. Okay, but you can say that this delta means you cannot get the exact constant, but you can compare to boundary layers, and if you can understand the physics, if u infinity is increasing, if density is increasing, then what happens, you can understand from this relation delta by x scales to 1 by root rex actually. Okay, and If you try to look at this geometric parameters, so you might be knowing this delta star, which is displacement thickness. This compensates for the loss of mass. So integral 0 to delta 1 minus u by u infinity dy. Then momentum thickness, this compensates for the loss in momentum because of the boundary layer by dy, and this shape factor h. So shape factor normally right now I'm just telling as a formula, but in aerodynamics this has a very important significance. Okay, so delta star by theta, this has a very great significance when you come to, especially when you talk about the aerodynamic flows. Okay, and this shape factor is h is equal to delta star by theta, of course, and you also have delta star star. This is momentum thickness. Momentum thickness, and this is energy thickness. Okay, so this is energy thickness. Okay, so we have the energy thickness, and let's see, once you have the energy thickness, this delta star star is integral 0 to delta u by u infinity into 1 minus u square upon u infinity square dy. Okay, and this compensates for the loss in the mass flow rate, this compensates for the loss in the momentum because of the presence of the plate, and this compensates for the loss in kinetic energy. Okay, now once you identify geometric parameters, then confused between boundary layer thickness and displacement thickness. Can you help me describe them? Definitely. Look, boundary layer thickness is ultimately the point where you reach this 99% of the velocity. You know this, correct? Where asymptotically you touch. So इसके problems test series में समझ में नहीं आए थे. ठीक है, I don't know what questions has come up because fluid mechanics I did not give this year. So, but anyway, the boundary layer thickness is 0.99% of the phase time velocity. Okay, now what is the displacement thickness is? Let's see, I'll tell you maybe here. Yeah, you have this plate. Okay, and normally if this is the section, about which you have the flow. Okay, u infinity. Ideally, if there is no plate, this streamlines would have continued like this, correct? Ideally, the streamlines would have continued like this. But now what happens, because of the presence of the plate, in order to maintain continuity, these streamlines will take some deviation. They diverge along this path. Okay, so streamlines diverge along the flow. Now, if for example, so you took this earlier, can you please this again? Sorry, didn't get you. So you took this earlier, can you please this again? I didn't understand. Can you type? I think some word is missing. Okay, so let's see, if you have this streamlines diverging. Now for example, let's say this is your delta. Okay, this is your delta at this point. Now if you have this delta, ideally if there is no plate at this thickness, this streamline would have been passing like this. Okay, but now because of the deviation to this, the streamline is getting diverged till here. So the gap by which this streamline is displacing is called displacement thickness. Understood? The distance or the displacement of the phase stream velocity streamline at a given section is called the displacement thickness. That's all. A piston cylinder arrangement contains 0.535 meter cube at 50%, 50 degrees Celsius. Question earlier, can you please explain it again? In this question, you assumed air as perfect gas. How? Piston cylinder arrangement contains 0.35 meter cube of air at 50 and temperature. Pressure. The air is isentopically compressed to 0.71. The isentropic bulk modulus is dash. You have the volume change and also you have the pressure, no? So then you can do this. Anyway, we'll look it towards the end. Okay. Avan, got it? Yeah, so it is basically the displacement of the free streamline. That's why the name itself is displacement thickness. It tells you by what thickness the streamline gets displaced. That's all. Okay. So then once you have the geometric equations, we'll look at the von Karman's momentum integral equation, because this is the equation which helps you actually to solve the profiles. Okay. So if you look the von Karman's equation, the wall shear stress by density is equal to d by dx of u infinity square theta plus boundary layer thickness this displacement thickness u infinity d u infinity by dx. So this is the actual von Karman's momentum integral equation, the full equation. Okay. Now in case of flat plate, what happens? Flat plate has a separate speciality. Okay. See, what is the speciality of the flat plate? For flat plate, this u infinity is constant, but whereas in case of other boundary layers, like in case of flow past a sphere, flow past a cylinder, you don't have a constant u infinity. U infinity keeps changing. Okay. But here in this case, for flat plate, this u infinity is actually a constant. Okay. And if u infinity is constant, then first thing, you can pull this u infinity out of this differentiation and this term will go to 0. Okay. Blasius is more accurate, no sir? Blasius is more accurate, but at the same time, Blasius has numerical methods. It depends. Okay. Blasius, whatever the 5x by root r ex you have, that's a very naive approximation. Okay. For 0.99% of the velocity. In fact, if you go for 0.999, that constant phi will go to somewhere 6.87, things like that. Okay. So I'll show you anyway the functions. So d u infinity by dx is equal to 0. Okay. Also for flat plate, pressure is constant at all the points in the flow. At all the points in the flow actually here. Okay. Then this terms, if you make 0, then for flat plate, tau w by rho u infinity square is equal to d theta by dx. This is what you might have seen, at least for flat plate. Okay. So this is the von Karman's momentum integral equation for flat plate. Anyway, this is the full equation, but if for flat plate, it's a special case where this term is 0. So this term goes to 0 and you can bring out this u infinity square out. So you get this equation. Okay. Then what is good approximation for velocity profiles? Okay. So for eta is equal to y by delta, we have u by u infinity as some function of eta always. Okay. So we define this as some function of eta, and one very better approximation for this is polynomials. Okay. So if you see a0 plus a1 eta plus a2 eta square and so on. Okay. So this is polynomial approximation. Polynomial approximation. Okay. Now once you have this polynomial approximation, depending on boundary conditions, you can get, let's say for example I want up to second degree. Okay. Then I need 3 boundary conditions. What are the 3 boundary conditions? Firstly, at y equal to 0 means eta equal to 0, my velocity is 0 because I have plate, so because of no slip. At eta equal to 1 or eta tending to 1, where y is tending to delta, I have u equal to u infinity. Okay. Similarly, at eta equal to 1 means at y equal to delta, dou u by dou y is 0 because velocity has reached its maximum. Okay. So further it won't be any change in the velocity in the y direction. So like this, if depending on the accuracy you want, you will specify the number of boundary conditions and you get this constants, like up to first degree or second degree or third degree you'll get. Okay. And sometimes people write this in some sign summations, cos summations. So u by u infinity is equal to some constant plus amplitude times sine, okay, some constant alpha into eta. So they write this. Okay. So where again alpha is just a constant. So there are plenty of things which you can express this. Okay. And all these profiles will definitely satisfy all the boundary conditions physically. Okay. Now what is the advantage of having this von Karman's momentum integral equation? You can actually solve the boundary layer equation and get the result. Okay. Like for example, okay, if you have u by u infinity is 2 y by delta minus y by delta whole cube. Okay. So let's say you have this square, I think. Okay. So y by delta whole square. So let's say if you have this equation for example, then with this equation if you solve, tau will get theta. You know, you can perform the integration, it's a single variable integration, you'll get 2 by 15 times delta, of course. Okay, so everything theta, delta star, delta double star, these things will be only in terms of delta, but you don't know what is delta physically. Okay, because you may know the plate geometry, you may know the fluid conditions, you may know the fluid properties, everything, but you don't know what is the delta value actually. Okay, so to get this delta in terms of known parameters, you need the this boundary layer. So this von Karman's momentum integral equation. Okay, like you can see tau w, you know, you can calculate now. This is known. Now tau w by O is equal to u infinity square is equal to d theta by dx. Okay, now this is a differential equation, a differential equation in terms of delta. So if you solve this, you will get some constant into x by root ix. Okay, so this is what you would get, where k is some constant depending on profile. Constant depending on the profile actually here. Okay, so that's why this equation is very nice equation, where you can get delta in terms of every known quantities, and Reynolds number involves everything known quantities like u infinity, x by nu, these things. So you will be able to figure out all the necessary things using this equation. Okay, is this clear so to all of you? Everyone just comment in the chat box, is this okay to all? You know this in terms of delta. तो ये ऊपर के इक्वेशन को सॉल्व कैसे करते हैं? कौन सा? इसको या इसको? This one. This is the one you're talking. Adarsh. It's a first order differential equation basically. Okay, and normally in all the cases it's done in this equation. See, for example, if you take a0 plus a1 y by delta, or a1 eta plus a2 eta square. Okay, you thought of doing up to second degree accuracy. Okay, now you have three constants a0, a1, a2, so you need three boundary conditions. So how do you define? At first y equal to 0, that implies eta equal to 0, eta equal to 0, let's say. So eta equal to 0, u by u infinity is equal to 0. This condition gives you a0 equal to 0. Okay, at y equal to 1, oh sorry, y equal to delta, eta tends to 1, u by u infinity tends to 1. So in the remaining parts, if you put a1 plus a2 is equal to 1, you'll see 2 minus 1 will be 1. Okay, so you'll get the coefficients. Third, at y equal to delta, eta tends to 1, dou u by dou y equal to 0. So three equations where three unknowns you can solve. Okay, and if you want the fourth one, then again at the bottom at y equal to 0, dou square u by dou y square is 0. Okay, because that's the location where dou u by dou y is maximum. So dou square u by dou y square is 0. That's how. Okay, we'll go up to cube profile. So three equations, three unknowns you can solve, and you can get a0, a1, a2 values and profile. Okay, chalo. So let's see skin friction coefficient. This fellow is there So Cfx is tau w by half rho u infinity square. Okay, so the skin friction coefficient again tells you the intensity of the wall shear stress. That's all. Okay, so this tau w is half Cfx into rho u infinity square, and obviously Cfx is going to be some function of Reynolds number. Okay, like how we have seen the case of Reynolds number in all these, you know, what are these things in all these plane Poiseuille and Huygens Poiseuille flows. So like that we have even the case here. If possible, can you give the value of displacement, momentum and energy thickness for different profiles? Normally in GATE exam, as far as I have seen, maximum they'll ask you either linear profile or not even this, some simple profile they'll give you, because they don't expect you to mug up the formulas. Okay, see, really if they ask you what's the time you will take to calculate displacement and momentum thickness, normally they never ask energy thickness for very large profiles, because they just take time. Okay, they don't want to test your single variable integration skills. Okay, clear? That's what I'm telling. Don't try to make a table and start mugging up the things. You will never remember. Okay, in fact, see, if you want to give, even I want to derive the things, or I should take a textbook and maybe copy it down. That's all. Okay, GATE never want to test your single variable integration skills. Okay, everybody know that you have to do single variable integration, and it's a simple thing. Okay, like let's see, if I give you a profile, integral 0 to delta 1 minus u by u infinity. So let's say sine pi by 2 y by delta, for example. Okay, you have done much complicated integrals than this, no, in maths. Then there's nothing like you need to form a table, then mug up the table, nothing like that. Okay, to be frank, even I don't remember, but without remembering these things, I'm teaching all this fluid mechanics and I got all India rank 4 in XE. Okay, that's good enough. I cleared ISRO, BRC, all these things without mugging up these things. Okay, so don't worry, there never comes a necessity in your life. People want you to know, if you go for an interview, people expect you to know how to do that. Okay, like let's see, if they give you a velocity profile, they test you whether you can calculate the displacement thickness or not. If they give the velocity profile, they don't ask you, okay, if I give you sine profile, what is the value, tell me. Nobody asks this. Okay, please trust me, I've done all these PSUs, good enough. So please don't do this by hearting business. Okay, at least for some days. Chalo. So this is skin friction coefficient. So if you want to calculate the drag force acting on the plate, okay, so this is skin friction coefficient. Okay, and this is local skin friction coefficient. So if you have average skin friction coefficient, so this is CFL in general. So 1 by L into integral 0 to L CFX dx. This is how you calculate the average, correct? You have some value and you just do the mean calculation. Okay, so this is the average calculation. Clear? Then, so how to calculate the drag force? It's a very simple business. So let's say if there is a plate like this, okay, this is x is equal to 0 and let's say x is equal to L, and this thickness of the plate is B, for example. Okay, then you take a small strip of length dx. Now everybody know the small elemental drag force is tau w into b dx. Okay, and what about tau w? You know, you can replace with this half CFX rho u infinity square into b dx, or if they give you the velocity profile, you can calculate all this CDF and all. So you will just integrate it. X is equal to 0 to x is equal to L. In fact, after doing the full integration, you will figure out FD is proportional to square root of x. This is what you will learn after doing the integration. Okay, so FD is proportional to square root of x. So if you keep increasing your plate, then the F value, the drag force, keeps increasing at a rate of square root of x actually. Okay, so similarity solution is basically something which is, to be frank, not can be done in this class, honestly speaking. because I cannot, even though if I bring the equation, I cannot solve the equation. Okay, so even if I bring the Blache's equation by doing the similarity variable and the stream function analysis and all, I won't be able to solve that equation in the class. I need a tool to solve that. Okay, in fact many times I do it in Python. Shall we do it in Python? Let's have some fun for 5 minutes. How many of you know how to do things in Python? Shall we try something new? ओके कुछ नहीं आता है पाइथन में सर. ओके ठीक है, हेलो वर्ल्ड टाइप करना ही आता है सर. आई विल टेल यू. काफ़ी लोग मैकेनिकल में ऐसा होता है कि जिनको कोडिंग बिल्कुल भी नहीं आते हैं. ठीक है, आई हैवंट यूज कंप्यूटर सिंस 10th. गुड. लेकिन क्या कहते हैं भाई, मान लो कि CFD में मैंने थोड़ा अच्छा क्वेश्चन दिया था, तो देन व्हाट डू यू डू? ओके, टू ऑल, सिंस यू आर awake till 1:30 listening to these classes, I'll give you some nice thing, okay, which generally more people, at least in the local colleges, they have no idea. Okay, I'll tell you. You know, there is something called Google Colab. Okay, collaborative of Google. So just you can type Google Colab. Okay, so Google Colab, this chashma wala picture aata hai. Okay, it's actually CO in merged. So you click this. ओके, मान लो कि आपको बिल्कुल भी आइडिया नहीं है कुछ प्रोग्राम लिखने का. ठीक है, सो इट कम्स अप. सो लेट्स ए न्यू नोटबुक. फाइन, आई टेक द न्यू नोटबुक. सो यू हैव सेल्स नाउ. लेट इट लोड. I think it's taking a while to load. Yeah, it got loaded. Okay, so each of these is cells. Now let's say I have given you an assignment where I asked you calculate the Carnot efficiency of a engine. Okay, for example, let's say I want you to calculate the Carnot efficiency of an engine. Okay, and using a coding, but let's say you don't know what to code and how to code. Okay, ChatGPT भी है आजकल, लेकिन थोड़ा सा important और practical चीज़ बताता हूँ. देखिए, I hope all of you can see this. Okay, fine. Okay, dialog box. Then let's see. First, any comment in this Python starts with hash. Okay, if you write hash, it will never take as a code line. Okay, it will just take as a comment. Okay, so let's see. Writing a program to calculate, I'm just writing a comment. Okay, to calculate Carnot efficiency using temperature inputs. Okay, I have done this. Now I'll click enter and wait for some time. Okay, then if it's not generating anything, so let's say, okay, now let's see. Fine, so TL for example, so let's say I'm defining some parameters. T, don't worry, I'll show you something nice. So TL equal to float of input of T. There's a prompt which has come up. Okay, because I have defined here using temperature inputs, this fellow recognized that I'm going to type something. Did you all get this? I did not type, actually I don't know what is the syntax. Okay, fine, let's say even if you don't know this, you'll see how to overcome. But when I have defined this AI, it has, Google Colab has AI inbuilt in it. So when I write this comment, it understands that okay, this fellow is trying to code something to calculate the Carnot efficiency. So immediately it has given this. So your job is just click tab. Okay, then these two lines got printed, no effort. Then again click enter, then wait for some more time. Okay, so Carnot efficiency eta is equal to, okay, so eta is equal to 1 minus, you know the formula, so just write it. So 1 minus, maybe my internet is little slow, but normally it doesn't take this much time. Okay, so TL by TH. Okay, so you see TL by TU, print the Carnot efficiency is, it has understood. So you come till here. Okay, then eta. That's all. Execute this code, run. Some error, we did not close this. Okay, sometimes this gives you less things, so run now. Okay, lower temperature, let's enter 250 Kelvin. Okay, for the time being 250. Enter the upper temperature. So what is the upper temperature? Let's say 750 for example. Then the efficiency is 2/3. Okay, that's how it comes up. So let's say even you don't know even this. Okay, for example, you don't know how to put in numbers TL, TU, you don't know, you have zero idea. Okay, then what you can do, take a new cell, so code. So initially here I have just taken some idea. Okay, but let's say I have zero idea, I don't know anything about this coding business. Okay, what I can do is click on this generate. Initially I clicked here and started to code with my knowledge what I have. Okay, but let's see if you don't have this knowledge, generate. Okay, so generate, immediately AI comes into the picture. So a Python program to calculate Carnot efficiency by inputting temperatures from user. Okay, so let's say I have done this, I have typed it, I have prompted AI. Okay, enter, bus, it is working. So you see it has given a beautiful code actually, completely it has given. Okay, just run this, it will ask for the values, that's all. Okay, let's say I want to calculate some boundary layer thickness. Okay, and I don't know how to code for example. Okay, then you know, code, generate a code to calculate boundary layer thickness, boundary layer thickness using Shear solution for example. Okay, so let's say I have typed Shear solution. Okay, I have typed this, enter, it's generating some code. So let's see, it has used some numpy arrays, it's asking for some distance from the leading edge of the plate. You can see this. Okay, maybe this is not okay, so let's see, I hope you can see this now. Distance from the plate, phase time velocity, kinematic viscosity, Reynolds number is equal to ux by nu, which is, I hope all of you can see these prompts which are here. Okay, so I hope all of you can see this. Reynolds number is equal to ux by nu, delta is equal to 5 into square root of x by nu x. Okay, done, clear. So once I run this cell, then definitely it'll ask me for some inputs, whatever I'll give, this gives me the boundary layer thickness. Okay, but in fact you don't know what is this arguments, returns, calculus, syntax, nothing is known to you, but you got the answer. Okay, so at this point your knowledge should come. Let's say instead of 5 the code has taken 4 by default, then you should know that in Shear solution it's not 4, it's 5. That knowledge, technical knowledge you should have, but nowadays no need to struggle to get things coded or done something. Okay, but of course this processor can work only for college assignment levels, that too normal assignments, and professors at IITs and all are very clever. Of course 70% of the times it helps very good, but 30% of the times it fails. Okay, where then we should start our own business. Chalo, anyway, let's continue our story. So similarity solutions. Okay, so if you look at similarity solutions, we define this variable beta, which is y by delta. So this scales to y by x into root rex. Okay, and this u by u infinity is some function of eta, is what we'll define. And I haven't coded anything, our college never asked for, but you should know things. Okay, at this point of time. Chalo. So if you see the equation, whatever you have, u into dou y by dou x plus v into dou y by dou y is equal to nu into dou square u by dou y square for flat plate. Okay, so this is for flat plate. For flat plate actually here. Okay, then if you solve this equation using this anomalies, you can convert this equation to f table dash of eta plus 2 times f double dash of eta. Okay, so half, not 2 here, it's half times f double dash of eta is equal to 0. And finally, after solving this using numerical methods, solving this using numerical methods, basically the shooting method. I know the code for this, but manually cannot do it now. Okay, I know how to code for this equation and solve this, but right now let's not do that. Okay, so shooting method, so you will see this eta which is equal to 5. Okay, so this gives you delta by x into eta x is equal to 5. So delta is 5x by root ix approximately. That's what the Blasius solution tells you. Okay, so this equation is called the Blasius equation. And this is the Blasius solution, of course, eta equal to 5. Blasius solution. Okay, so eta is equal to 5 is what you'll get. RK method, yeah, generally in the initial, to make the initial guesses, you'll use RK, but later we do something called shooting method where we guess the value and again come back and reiterate the results. Okay, so but anyway, right now let's stick to this. Okay, so this delta is equal to 5x by root ix. Okay, and so okay, so this is the last topic on this. Okay, last but one topic. So drag and lift on bluff bodies. So basically, if you have a 3D body in big, so how to calculate the lift and drag? Okay, so normally first discuss about this drag. You have two forms. One is form drag, or it's also called as pressure drag. And the second one is the viscous drag. Okay, so viscous drag. So obviously, form drag and viscous drag together will contribute for the total drag acting on the body. Okay, but in general, if you see, we combine the effect of these two. We define something called coefficient of drag, which corresponds to this and also this. Okay, and in reality, determination of this coefficient of drag is as tough as getting the heat transfer coefficient, to be frank. Okay, so that's why at least in the gate examination level questions and all, they'll give you what is CD, but in reality, to calculate the CD, it's a very big procedure. Okay, like the same as it's equally difficult as getting the heat transfer coefficient in case of heat transfer problems. Okay, so this is CD plus CV, and if you look at this drag force FD, this is half CD rho fluid AP U infinity square. Okay, so this tells you, in fact, you can say U relative square here. U relative square. So what is AP? AP is the projected area of the solid onto a plane perpendicular to flow of fluid. Plane perpendicular to flow of fluid actually here. Okay, so once they give you Stokes law, then Stokes law is of course one simple case where you have the sphere and all, but in general for any geometry, this is how you calculate the drag force. Okay, I'm again just revising the most frequent topic that comes up here in this case. Okay, so like for example, if you see like in last 2024 XE, one question has come up. So if you see, this is the flow, and let's say you have some airfoil kind of thing, then the drag and lift are basically given by, this is the flow, so you have drag in this direction and lift in this direction. So this is drag and lift. So drag will be along the flow and basically lift will be perpendicular to the flow, of course. Okay, so yeah, that's what this event tells you, perpendicular to the flow of the fluid. And similarly for the lift, we have similarly for lift we define CL. Okay, so we define the CL, of course. So we define CL, and that's how basically you calculate the drag forces. And normally in case of spheres and all, you have for every geometry it's a function of Reynolds number, and in case of spheres and all, it's 24 by Reynolds number is what you'll have actually. Okay, then coming to boundary layer separation. So when you have adverse pressure gradients, so what is the meaning of adverse pressure gradients? Normally dp by dx is positive, okay, along the flow. So x is this flow direction, so along the flow direction your pressure is increasing. Okay, so how will you mathematically identify that the flow got separated? That's the question, because physically you cannot verify at any number of points. So what we can do is we can actually generate this, we can actually calculate this dp by dx is positive, and normally at flow separation du by dy is equal to 0, and this is at the wedge of separation, at flow separation. Because if you see, if you have a some solid, and if the fluid is in contact till this point, then till that point dou by dou y is positive. Okay, dou by dou y is positive, but once you cross dou by dou y, then what can happen is at this point, once the flow gets separated, then there is a reversal of the flow that happens. Okay, normally if you look at profiles, you will see some profiles like this and all. So there is a reversal of the flow at this point. If you look at dou by dou y, okay, then at this point the dou by dou y is 0 because the contact is lost. So tau w is equal to mu into du by dy, or in fact dou by dou y if you generalize. So this tau w is 0 because there is no fluid solid contact, and clearly this is non-zero, so this has to be 0. That's what you'll have. Okay, and we generally experience after separation, we have dou u by dou y at y is equal to 0, sorry, because at the wall you will talk. So at y is equal to 0, this is after separation. At y is equal to 0, this is negative, and before separation it's positive, clearly. So this is how mathematically you check whether the flow got separated or not. Fine, so this is positive. Okay, fine. So then we'll solve the questions tomorrow, maybe, because it's getting delayed. So introduction to turbulent flows, of course. Okay, so any questions till this point you can ask me quickly. Any questions till this point you can ask me. Anything that you can ask, or is everything okay till this point? On X for AP, didn't get you. One example for AP, if you have a sphere, then sphere becomes a circle. Okay, if you project it, that's all. Anyway, in tomorrow's class when we solve problems, we'll see a lot of more things. Okay, so time average constant. So what happens in a turbulent flow? At a given point, obviously there is nothing like a steady turbulent flow, everything is changing. Okay, so at any given point, if you observe parameters with the time, if you look at a parameter phi with the time, for example, so origin and time, and let's say the value of that property phi, maybe velocity, pressure, x component of velocity, y component of velocity, say something. Okay, then this can fluctuate a lot like this. Okay, so what we define something called the time average constant, so the time average things. So this is the time average value. Oh, okay, phi average, maybe, let's say. Okay, so phi average, and above this we have phi dash till this point, phi dash. Okay, so phi bar is nothing but 1 by t. So let's say this is time t equal to 0, and you have observed up to time t, for example. Okay, so 1 by t integral 0 to t phi dt. Okay, that's how we will calculate the statistical average, of course. Then this phi is called time averaged parameter. Time averaged parameter, and this phi dash is called the fluctuating component. Is called the fluctuating component, of course. Okay, compressible flow taught us tomorrow in the first mind, because that is the most important for exam. Okay, we'll do one thing, or else I'll teach still dimensional analysis. Okay, so we'll break there. Hydraulic machines I'll teach like from like what you say, like the potential flow some part and the compressible flows part, and this hydraulic machines whatever I have to teach, I'll teach tomorrow. Okay, last 3 chapters. Okay, we'll finish till dimensional analysis at least. Okay, fine, because anyhow these 2 are very small chapters, they'll finish up in next half an hour kind of thing. Okay, because I understand listening continuously for 10 hours is hell. I do get it. In fact, tomorrow morning I have a conference to attend at 9 o'clock. Okay, so but it's okay, that's not the case. Chalo, we'll do that. Please complete machinery. Yeah, definitely. Okay, we'll finish machinery and potential flows a bit and compressible flows. Okay, yeah, so let's see, this is the time averaged components. Okay, so this is the fluctuating component. So let's see, if you for example calculate the time average of fluctuating component, which is something like 1 phi dash bar is 1 by t integral 0 to t phi dash dt. Okay, because clearly you see phi at any point is given by phi bar plus phi dash. Okay, so phi bar plus phi dash. I no issue here, tomorrow we'll deal complete machinery. Okay, no issues. So phi bar plus phi dash, so phi dash I can write it as integral 0 to t phi dash can be written as phi minus phi bar dt. Okay, I can write this. So if you consider this quantity 1 by t into integral 0 to t phi dt minus 1 by t integral 0 to t phi bar dt. Okay, and you observe something in this complete profile, at any point you have a fixed value of phi bar. Okay, so if you have a fixed value of phi bar, then this is nothing but again phi bar, this completely minus 1 by t into this phi bar can be taken out as constant, then this integration will be once again t. So clearly this t and this t cancels up, and phi bar minus phi bar will give you 0. So therefore the time average of fluctuating component is always 0. Okay, so the time average of the fluctuating component is always 0. Got it? And let's see. So therefore anywhere you take, okay, for any parameter like u dash u fluctuating component velocity, this is 0, v fluctuating component bar, this is 0, pressure fluctuating component at that point, so this is 0. So whenever you take the mean of the fluctuating component, that would be definitely 0 at any given point. Okay, clear? Then let's see, we discuss something here, the turbulent shear modeling. Abhi dekh ke sir डर लगा. Okay, but these are small things, man, it's okay. Chalo. How many of you do work in CFD? How many of you work in computational fluid dynamics? Any one of you? None. Everybody is happy with definition of fluid. Okay, ANSYS, nice. Devesh works in ANSYS, good. Anyway, so let's see turbulent shear. So if you have turbulent shear, okay, then basically if you have a boundary, okay, so this is boundary, then you can split this into parts. One is the laminar sublayer, then this is the overlap region, and this is the outer turbulent region. Outer turbulent region. Okay, so if you have outer turbulent region, okay, you have worked 3D modeling, good. So outer turbulent region. So what happens here? The viscous forces are very highly dominating here, and here viscous and turbulent shear is also dominating, and here turbulent shear dominates very much. Okay, so you have a lot of models again. So like Bosnesque model, which tells you that tau t is eta into du bar upon dy. Okay, so this eta which is here is called eddy viscosity. This is called eddy viscosity. Okay, but in reality this eddy viscosity did not very much helpful. So later Reynolds has come up with a model. So Reynolds modeling. So this is basically based on tau t is equal to rho u dash v dash bar. Okay, so product of this components, fluctuating components, and whole average. It's not the individual averages. Okay, so individual averages are zeros, but rho u dash v dash whole square. Then lot of experimentations and all we do. So these stresses are called Reynolds stresses. Okay, and then by doing the final results, we'll see the velocity profile in case of a turbulent flow is actually logarithmic in nature. Okay, and in this part it's a laminar layer, because obviously in this region the viscosity, it's a very small region, very thin region of course, and within that thin region you have this viscous shear stress, and if tau v is very small, then we have a linear velocity profile in that. Okay, like if you in general look at turbulent flows, velocity profile in pipe. Okay, so yeah, so here in a pipe, so if you see the velocity profile, inside sublaminar, we'll have a linear velocity profile. Okay, but of course this is very, very small. General velocity profile is logarithmic. Okay, like for example, if you take a pipe like this, okay, fine. So if you see, so this is the normal pipe that you have. Okay, so very thin layer would be present at this point. Okay, in fact, to make you understand, I am drawing this very big, but in fact this layer would be very thin. Okay, in fact of few microns, that's all. Okay, so at any section, if you try to draw the velocity profile, you'll see in this sublaminar region you'll have a linear velocity profile. Okay, linear, and then after it's almost like a logarithmic, and here it's more uniform, of course, in this case. So you'll see this is logarithmic. If they don't mention anything, if they just ask you what is the velocity profile, okay, then we will have logarithmic profile. But if they mention in the question that sublaminar layer, then it's linear. Okay, so which is linear in this case. So you have the linear velocity profile, and of course logarithmic in this case. Clear? Then, and normally the transition Reynolds number is a transition in the internal flows is around 2300. Okay, it's not again a very standard value, it's a very naive value. So transition is 2300 for the profile change. Okay, so you have the logarithmic velocity profile here. 10 hours is done. Okay, good. Fine. So let's look at this turbulent boundary layers. A very small idea, that's all. So it increases transition and then it moves further. Okay, so this is laminar regime. You have the transition and turbulent. So generally this transition happens at critical Reynolds number of 3 into 10 power 5 in general. Okay, and within this turbulent region, yeah, 10 hours completed, right? Okay, so here you'll see delta by x equals to 1 by Ix power 1 by 5. Okay, so 0.2 is what it scales to generally. Okay, so these are some nice insights which I thought of giving you in case of turbulent boundary layers. Okay, because again the questions and all will be based something like this. They'll ask you to calculate head loss. Okay, the only thing, if flow is laminar, then F is 64 by RE directly. Okay, but if flow is not laminar, they'll give you some function of Reynolds number by which you have to calculate the Reynolds number. So these by which you have to calculate the friction factor. Okay, so these things they keep asking you. And one thing which I would like to give at this point, I forgot. So when you are doing this derivation, you will get this. In fact, so this U star is called shear velocity. Okay, shear velocity, and you'll see they talk it as U star is equal to square root of the wall shear stress upon density. Okay, so if they can give you those values and if they can ask you some formula, Divakshaya. So let's go to silly. बहुत हो गई पढ़ाई. Yeah, of course. Dimensional analysis will take last 10 minutes. Okay. Head loss is same as Hagen-Poiseuille. Generally not. They'll give you some relation for F so that you can substitute your Reynolds number and get the things. Okay. Fine. So let's look at something nice. Similarities between the model and the, it's a very small topic. Okay, just 10 minutes we'll finish it off. Yeah, because you already know many things about this, so just a quick revision, last 10 minutes sort of. Okay, then we'll end for today. I understand, I take your concern. Okay, so let's see. So you know, you do modeling, so definitely what are the similarities your model and prototype should have? First thing is geometric similarity. Geometric similarity. 2, we should have kinematic similarity, and we should have dynamic similarity. So what are these similarities? What do they mean actually? Okay, so in case of geometric similarity, you'll see that corresponding dimensions should be of a fixed ratio. जो लिखा होगा नहीं, जो पढ़ा होगा वही होगा. ठीक है, you just discuss something in the chat box. Okay, so this tells you that geometrical similarity means basically if you have a, like for example, if you are trying to model a sphere, okay, the drag force acting on a, my mouth is also staggering. Okay, so let's see. Geometric similarity. Okay, so if you wish to test a sphere in a fluid, for example, to analyze the drag force acting on a fluid, then हासिल है सर को. हाँ, obviously 10 घंटे पढ़ने के बाद सबको आएगा. So let's see. So when you have this geometric similarity, na, if you are trying to test a sphere in a flow, then the model should also be a spherical object. Okay, it's not like if you want to test a sphere, then you will make a cube and test it. Okay, you should not do that. So corresponding dimensions ratio should be constant. Should be constant. Okay, then what does kinematic similarity tells you? This tells you like V radial component of the model by V radial component of the prototype should be same as theta of the model, V theta of the prototype should be same as Vz of the model by Vz of the prototype actually. Okay, and this dynamic similarity tells you like inertia force of the model by inertia force of the prototype should be same as, let's say for example, lot many forces, it depends on the physics which governs, F viscous, F gravitational, okay, then F surface tension, let's say if that's important at some phenomena. Can you observe something guys? When I'm writing, the board is not able to catch very fast, it's taking some time, it needs rest. Okay, and so on. This can go on actually. So when you try to model some experiments, okay, you'll make sure that these things should get hold. Okay, but writing these equations is very easy, but in experiments maintaining that is very, you know, difficult to be frank. Okay, so anyway, let's see. Then we have something called principle of dimensional homogeneity. So what does this tell you? If you have for any physical quantity y, for any physical quantity y, depending on n physical quantities, x1, x2 and so on xn. Okay, x1, x2 and so on till xn. For y is equal to some function of x1, x2 and so on xn, both should have same dimensions. Okay, confusion in model, in numerator or prototype, it doesn't matter. Okay, if you write model by prototype of one quantity, also write model by prototype of the second quantity also, it doesn't matter. Okay, so this implies the dimensions of y should be same as the dimensions of x1, x2 and so on xn. Okay, like for example, if you have something like t is equal to 2 pi root L by G, one simple example I'll give you, the dimensions on both the sides should be same. Okay, so similarly, if you have something like delta is equal to some constant into x by root u infinity x by kinematic viscosity, all this stuff, but the dimensions on both the sides should match. This is what it tells you. Okay, then let's see how to perform this dimensional homogeneity. Wallis method is the first method. So for y being function of x1, x2 and so on xn, what we choose is this function is a obviously that can have n number of functions which are possible. Okay, but we choose a particular function such that in Wallis method we choose y is equal to x1 for alpha 1, x2 for alpha 2, x3 for alpha 3 and so on xn for alpha n. This is what we choose. Okay, means basically this function where alpha 1, alpha 2 they belong to real numbers. Okay, so they belong to the real numbers. So we choose this function in this particular form and then apply the dimensional homogeneity on both the sides. But now the issue is at maximum you have number of fundamental dimensions is 7. Okay, that's the maximum you have. Max number of fundamental dimensions is 7. Okay, so if number of variables, that is x1, x2 and so on xn, is greater than 7, then we can't solve the equations. So that's drawback number 1. Okay, MLTK are more useful for us, not for everyone, but this chapter has a very good significance in all other domains of engineering. Okay, so that's the issue here. Okay, so to overcome this effect we come across this Buckingham-Pi theorem method, which is one of the most powerful technique in fact. So in this, let's say let x is some function of x1, x2 and so on xn minus 1 for example. Okay, so let's say we have the function of xn minus 1. Buckingham, no, it's not Buckingham, Buckingham. Okay, Buckingham-Pi theorem method. Is it Buckingham? Did I write wrong all these years? Let me check somewhere. Let's Google this. Of course I have the smart board, but still let's see. Buckingham. Yeah, it's Buckingham-Pi theorem, man, not Buckingham. Yeah. Yeah, it's not Buckingham, it's Buckingham. Okay. Yeah, it's correct. I know very little English. Okay, don't confuse me. I'll forget that also. Fine. So Buckingham-Pi theorem method. Clear? So then this can be written as, this is also a variable. So let's say xn is some function of this. So we can write x1, x2, x3 and so on xn is equal to 0 actually. Okay, so because like you have y equal to ax square, y equal to ax square for example, if I have, then I can write y minus ax square is equal to 0 obviously. Okay, then Who told Buckingham? Nidhi. Acha. Okay. So this is the function. So let's say you have n variables involved in this case. N variables. Now using these n variables, you can have plenty of experiments. Okay. Like for example, if you change any one quantity at a time, you will conduct n minus 1 experiments or n experiments, of course. Okay. Then if you do 2, if you change 2, so you can have again many experiments. So basically, if you try to model this using n variables, you have to conduct a lot of experiments. So what we do, Buckingham-Paite method decreases the number of variables by forming certain dimensionless groups actually. Okay, that's the technique. So this is n variables involving m fundamental dimensions, then this can be modified as some function of pi1, pi2 and so on, pi n minus m is equal to 0. Okay, so when you have each pi is a dimensionless term. Each pi is a dimensionless term, so we reduce it. Okay, sorry, autocorrect. Yeah, it's okay. No need to saw here, so just listen. So each pi is a dimensionless term actually here. So you have out of n variables involving m fundamental dimensions, you can figure out the complete variables into n minus m fundamental dimensions. Okay, then if you figure out to n minus m fundamental dimensions here, then let's see pi 1. So out of n variables, we choose m repeating variables. Okay, mic sound again. Mic sound is, I think somebody else is also there in this room. They're disturbing the signals. Okay, fine. Now it's okay. Okay, good. So let's see. So we choose m repeating variables, and how do we choose them? Such that they involve kinematic conditions, dynamic conditions like the pressure, whatever the quantities, and one fluid property as well. Okay, so one fluid property, one geometrical because fluid properties are the one which decide the dynamic conditions. So one fluid property, one kinematic condition like speed, velocity, acceleration, something like that, and we'll also choose one geometrical parameter which governs the flow. Okay, so these m variables involve geometric, kinematic and physical variables. So then you can reduce this n terms into n minus m dimensionless terms, of course. Okay, fine. So that's what you have. So pi n minus m is equal to 0. So basically you will reduce this. So then after, for I is equal to 1 to n minus m, what we do, x m plus i is equal to what are the values you have chosen, x to the power alpha 2 and so on, xm for alpha m into pi I is equal to x m plus I. That's all. Okay, so finally you will end up with xn terms. So you will get n minus m dimensionless combinations. That's all. Okay, that's how we define the pi terms actually. So I goes from 1 to n minus m. So we have n minus m pi terms such that out of these repeating variables, then you will take every one repeating variable, of course. Okay, so again in tomorrow's class when I teach hydraulic machines, I'll try to do one good thing actually, which or at least I'll try to post the notes for that in the Telegram channel, so that you will understand how Buckingham by theorem can be done much effectively. Okay. Clear? So then so this finally gives you n minus m dimensionless terms. So this is one last thing, but anyway, yeah, that's the last slide which I'm supposed to teach today. So important dimensionless numbers. So we have seen the dynamic similarity, something like this. Dynamic similarity tells you that F inertia of the model by F inertia of the prototype is equal to viscous force of the model by viscous force of the prototype, gravity force on the model by gravitational force on the prototype, let's say, elastic force on the model, means in case of some compressibility effects and all, okay, pressure force on the model by pressure force on the prototype, let's say surface tension is also there by surface tension of the prototype. So let's say you have this equation, for example, okay, but maintaining this equation is very, ridiculous, to be frank, in experiments. So what we do, depending on the physics which is governing the problem, like let's say for example if a ball is moving inside a fluid, okay, then there is no effect that you feel much compressibility or you feel much surface tension. So these things are not very important, okay. So what we do, depending on the physics, we segregate certain important combinations. Like for example, in internal viscous flows, okay, or viscous flows, these two are dominating. For applications where inertia and viscous are dominating, viscous are dominating, okay. So if you equate these two, somebody asked, no, model by prototype or prototype by model. Now you see inertia of the model by inertia of the prototype is equal to viscous force of the model by viscous force of the prototype. So now if you swap these two, okay, you will get inertia by viscous of the model is same as inertia by viscous of the prototype, okay. And normally if you look at the scalings, F inertia scales to rho L square V square and F viscous scales to mu V L square, okay. So mu V L is what you will get, correct na? So mu V L, yes, of course. So inertia by viscous gives you a Reynolds number. Inertia by viscous, this scales to, okay, so this scales to rho L square V square by mu V L. So V L and this gets cancelled, so you have rho V L by mu. So this gives you a Reynolds number actually, okay. So likewise, similarly you will get other numbers as well, like in the cases where inertia and gravity are important, like in the case of like free surface flows like boats, in all these cases, okay. So here, especially when viscous forces, if viscous is there, then definitely this works out. So in free surface flows, in free surface flows, okay, so in free surface flows, what do you have? Inertia and gravity are dominating, okay. So F inertia by F gravity of the model is same as F inertia by F gravity of the prototype actually, okay. And what does this scales to? गजब का लैब है ना, लैग है ना, तो ठीक है, चले. F inertia by gravity, this scales to rho L square V square by gravity, mass into acceleration, that's all, okay. So this gives you L, so V by root GL whole square, okay. So then this is a dimensionless combination which is called as Ford number. Fine. So like boats, dam spillways, in all these cases. Okay. Similarly, the pressure force will scale to inertia by pressure force. This scales to rho L square V square by P L square. So this gives to V by square root of P by गजब का लगा ना. You're writing in 2x board and it's working in 0.5x. Yeah, correct. So let's see. Even I'm getting laugh for the same. Okay. So this V by root P by O is called Euler number. Okay. Similarly, inertia by surface tension, if you scale rho L square V square by sigma into L, so this can be written as V by square root of sigma by rho L whole square. Okay, sigma by rho L whole square, and this is Weber number, and you know Mach number, inertia force by elastic force. Okay, so that's the Mach number. Normally where the compressibility effects are high. Okay, so then we'll do one thing. I'll delete this 3 chapters in this PPT and put it in the next PPT, like so that we can. So tomorrow, you know, we have this. $7 p.m. only, no? Yeah, 7 p.m. Many times I confuse between AM and PM. Okay, so but we'll solve the questions. Velocity by speed of sound. Yeah, correct. Velocity by acoustic velocity. Anyway, in tomorrow's class, I'll talk about compressible flows. There I'll talk about Mach number. Okay. नहीं कल 2 बजे तक नहीं चलेगा. ठीक है. Will there be XC level problem? Yeah, definitely will. Have warm water. Actually, I want to order something. I did not had my dinner. Okay, in the 20 minutes break, it's good enough for me to search Zomato in between. Okay, but I was not able to order. It's okay. I'll order some hot food and eat. Chalo then. Take care. We'll meet tomorrow at 7 p.m. and yeah, 7 p.m. and we'll solve some good questions. Hope you enjoyed this session. I feel myself embarrassed to say this after keeping you for so long, but of course definitely this will pay off. ठीक है. कल सर कितने बजे तक चलेगा? 7 to maybe like 10:30, 11. That's all. Okay, not beyond that. But definitely this session, whatever you have attended today, many of you might have learned some new points. So this will definitely pay off. Okay, within next 20 days, 20-25 days. चले? तो ठीक है. बहुत अच्छा लगा सर. Definitely. Fine. Okay. Thank you all. Good night. We'll meet tomorrow at 7 p.m. for the Abhyas. We'll deal this chota mota cheese and then we'll start solving some questions. Okay. Good night, all of you. Thank you all for attending here. Thank you then. Okay. So don't miss tomorrow. Whatever the topics I have taught you today, we'll practice some questions on them. Okay. Good night. Take care. Bye, all of you. Sleep well. Okay. Don't watch your mobile and all now. Sleep. Bye. Good night.